Right? I'll go share up the live the live link so people
I
will
don't
know.
look into that already.
Okay, nice. Okay, we live there. Let we go, guys. Let we go. Let we go. Oh, yeah, I eat some food and thing, and I ready for action. I ready to knock this physics out of the park. All right, so the first thing we're gonna look at is gas laws. Let me run through that quickly. Okay, who here has problems with the gas laws? Talk to me fast.
I mean,
Me, sir.
Me, sir.
All right.
Me.
But here we go and start off with Boyle's law. What does Boyle's law say? It says for a fixed mass of gas at constant temperature, the pressure is inversely proportional to volume. And what does that mean? So, like, let me explain something, right? Imagine you had a Lay's bag of chips. You know that's just been mostly air. You know how it is go, right? If you squeeze that, right? If you apply a pressure, what happens to the volume? Does the volume get bigger or smaller?
Smaller.
More.
Smaller. So if you understand what Boyle's law says, Boyle's law says that the pressure is inversely proportional to the volume. So if you apply pressure to something, if more pressure you apply, what happens to the volume?
It would get
That's
bigger.
small.
It would decrease.
It would decrease because you're compressing it, like, you're making it smaller. So the pressure would increase, but the volume would drop. And Boyle's law is given by P1 V1 is equal to P2 V2. So again, you have to know this. So Boyle's law says for a fixed mass of gas at constant temperature, the pressure is inversely proportional to the what? Pressure is inversely proportional to the?
The volume.
Right. And what's Boyle's law? Tell me the formula. Tell me the formula.
P1,
P1 V1 equals P2 V2.
Yeah.
Cool. So the volume will decrease and the pressure will rise. If you need to, or you can take a screenshot of this fast. Boyle's law. So you're going to use Boyle's law anytime you see a change in pressure and volume. But what has to remain constant? If the pressure and volume is changing, what is remaining constant?
The temperature.
Temperature still.
Right, it's always pressure, volume, and temperature. If pressure and volume changing, temperature remain constant. If volume and temperature changing, pressure remain constant. Anybody can tell me the rule with volume and temperature? Which one is that?
volume is V.
Charles law.
T.
Charles.
That's Charles' law.
Oh.
That's Charles' law. Yeah. All right, cool. I'll have a screenshot, right? I'll move on.
Sure.
So that's what Boyle's law says. These are what the graphs will look like in case you want to know. Because they are inversely proportional, if I were to plot pressure against volume directly, it's going to give me this graph over here. However, if I were to graph pressure versus 1 over volume, it'd be a linear graph. So this is what Boyle's law. Take out a screenshot, have it locked in. Let's move on. So the next one we're going to look at is pressure law, also known as Gay-Lussac's law. So this one says for a fixed mass of gas at constant. Okay. Before we even do anything, you're saying constant volume. If the volume remaining constant, what are the other things that would change?
Pressure and temperature.
Pressure and temperature. Now, before we even do anything, what do you think is the relationship between pressure and temperature? Just think about a pressure cooker. A pressure cooker relies on what? What does it rely on?
High temperature.
Temperature.
Temperature. So guys, as the temperature for the pressure cooker rises, what happens to the pressure on the inside as the temperature rises?
Increases.
It also increases.
It increases, and this has to do with the kinetic theory of matter. Remember, if you supply heat energy to particles, they would gain kinetic energy, and it's how to move vigorously and violently, and they will hit against the outer walls, exerting a force, which would increase pressure. So what does pressure law say? Pressure law says for a fixed mass of gas at constant volume, the pressure is directly proportional to the absolute temperature. Here what I'm saying, guys. If you forget what it is in the exam, you could think about it in a way that makes sense. Guys, when I say directly proportional, I mean that when one goes up, what I'm saying the other one?
It goes up as well.
Up as well.
Right. That is what directly proportional means. It means that if one goes up, the other one.
Goes up.
It goes up.
Okay, I'll have that, right? That makes sense.
Yes, sir.
Yes, sir.
Other people. Until they understand with a pressure cooker, if it increases the temperature, the pressure does increase as well. So one going up and the other one going up. Now, pay special attention to something. I'm saying to the what? I'm saying to the what? To the what?
Absolute temperature.
Absolute temperature.
Temperature.
If you see absolute temperature, are you going to be working with degrees Celsius?
No,
Yes.
sir.
No, sir.
No, you're not going to be working with degrees Celsius. Let me explain something really, really fast. Imagine you had a graph of volume, and they expect you to know this. Imagine you had a graph of volume versus temperature, and your temperature is in degrees Celsius. Now, if you were to plot this graph, you'd actually get this. Tell me something, guys. Does this graph hit the origin?
No,
No,
sir.
No, sir.
No, sir.
This is the origin here, it doesn't hit it. So you know what they do? You know what they decided to do for it to hit the origin? Instead of starting from 0, you know where they start at?
Minus 2.
Negative. Negative.
273 or something. Yeah.
Yeah. Because if you were to take the graph of volume versus temperature in degrees Celsius and you were to pull it back, it would hit the temperature axis at minus 273 degrees Celsius. So at minus 273 degrees Celsius, theoretically, the volume is what? What do you think the volume is?
Zero.
0, because if I ask you to read off this point, how would you read off that point?
Minus 273. Zero.
0.
3, 0. So the temperature will be minus 273 degrees Celsius and the volume would be what?
0.
0. So this is actually referred to as absolute 0. I'm not sure if any of you guys know that, but this is absolute 0, and it's it's like the coldest temperature known to mankind, and it's the temperature where all particle movement ceases, like it stops. It stops. But theoretically, we could say that, but it's not possible. It's not possible. Yeah, guys, could you? I'm asking you something, right? Imagine you have a foil, right? Imagine you have like a foil, and you guys, when you're bored, you might roll up the foil and you might squeeze it to make a ball. You know what I'm talking about?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Do you think you could compress that till the volume becomes 0?
No.
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 sir.
Nah, so that isn't possible. But theoretically, theoretically it is possible. But under all means and purposes, like practically, it's not possible. So you guys will see this minus 273 degrees Celsius brought up a lot. So what exactly is absolute temperature? Absolute temperature is the temperature in Kelvin. So you would see that to convert something to Kelvin, we would have to add to it
273.
273.
273. And remind me, guys, what was absolute 0? Absolute 0 occurred at what temperature in degrees
Negative
Celsius?
273.
73 degrees.
So check this out, guys. Check this. I want you to check this out for yourself. What is minus 273 plus 273?
0.
0.
Right, so you know how we have 0 degrees Celsius? Is 0 degrees Celsius the coldest temperature?
Nah.
No.
But you see, 0 Kelvin is the coldest temperature known to mankind.
Because
It is, like, according to
Because it's in
physics,
the
it is.
absolute 0, which is in Kelvin.
Exactly. So here what, right? If I were to plot a graph of volume versus temperature in Kelvin, do you think it would look like this?
No, sir.
No, sir.
No, sir.
It
Nah,
will be orange.
Correct. Well, you guys know stuff, man. I know stuff. That's good. Now I expect you need to know a little bit of stuff, because I mean, I'll study physics for some while, so I expecting you guys to know some stuff. I don't want to treat this session as like I doing everything in like extreme detail. It's more like I run through and we're gonna answer questions, but I'm still gonna try to explain stuff. So guys, pressure law. Could anybody remind me what pressure law says?
For
For
a
a
fixed
fixed
mass
mass
of
of
gas
gas
at a constant temperature is directly proportional to the absolute temperature.
Okay, good. And where's the formula for that? Somebody tell me.
P1 over
P1
P1.
equals
That's
V2
200
plus
seconds.
P2. T2.
Okay, good. Just backtracking. What is Boyle's law? What does Boyle's law state?
Wasn't that the fixed mass at constant volume and the
Nah,
and the
nah.
For
So here,
um
wait,
no,
wait,
the
for a
pressure
wait,
fixed
no,
for a
guys.
fixed mass
Wait,
of
give
gas or
Shania, give Nikolai a chance. Give Nikolai a chance. Nikolai, when we talking about Boyle's law, what two things has changed? See if you can remember, Nikolai. When we talking about Boyle's law, what two things change?
the pressure and the volume,
So, Nikolai, if the pressure and the volume change, then what would have to remain constant?
temperature.
Right. So you would
Oh, I
say,
thought I was talking about. I think I was trying to answer what was pressure law.
yeah. So this is an easy way to understand it. So you would say for Boyle's law, for a fixed mass at for a fixed mass of gas at constant temperature, the pressure is inversely proportional to the volume. You understand?
Yes, sir.
And just remind me quickly, Nikolai, what's the formula for Boyle's law?
Uh, P1 V1 is equals P2 V2.
Cool. Cool. Right. So everybody okay with Boyle's and pressure, Boyle's law and pressure's law? I'm gonna follow you okay with that.
Yes, sir.
Okay.
yes, sir.
Sir,
Yeah. Talk
excuse
to me.
sir, you could go back to the graph for Boyle's law and then get the picture.
Okay, Ollie, I had it moving faster. Fast.
Yeah,
Fast. And I gotta be
okay,
sending
okay.
these notes. I gotta be sending these notes too. So,
I get it, sir.
nice. So remind me, guys, when you're dealing with the pressure law, temperature has to be in what? Someone fast. Temperature has to be in what?
Kelvin.
Kelvin.
And let's just say I had 53 degrees Celsius. How I convert in 53 degrees Celsius to Kelvin?
Add
Add
270.
273 to it.
73.
So what would this be in Kelvin?
That will be
That would be 326.
326.
326 Kelvin.
yeah.
Right. Cool. So we're okay with Boyle's law and pressure law. Good. All right. Charles' law. Big up Charles. Charles chocolate low-key kind of buns, but you know what I mean? But anyways,
Yeah.
Charles' law. It says, okay, so it says for a fixed mass of gas at constant pressure, so Nikolai, if the pressure is remaining constant, what two things are going to change?
The temperature and the volume.
All you understand that, right? And
Yeah.
let me ask Ollie a question. What kind of relationship do you think they would have? Think of an example, like a hot air balloon, for instance.
It's directly proportional or it going to the same thing?
Directly proportional. Imagine you're heating a gas. What would happen to the volume of the gas?
It'll expand and bigger.
It will expand, it will expand. Question, if you leave a Coke bottle in the sun, what happens to the Coke bottle?
It's get harder.
Get harder, so like the volume does increase. So Charles' law says that for a fixed mass of gas at constant pressure, the volume is directly proportional to the absolute temperature. I say it again, absolute temperature. When you're working with these gas laws, you must work in degrees Celsius or Kelvin.
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 And again, to convert to Kelvin, you have to do what?
Add 273.
273.
Add 273. Good. Cool. And Charles' law is V1 over T1 is equal to V2 over T2. So let's do a quick recap. Somebody tell me, what is Boyle's law? Somebody formula.
For a fixed mass of gas at a constant temperature, the
P1,
pressure
P1.
is inversely proportional to the volume.
All right. That's correct. Somebody formula.
P1 V1 equals P2 V2.
Okay, let's move on to Charles' law now. What does Charles' law says? The formula for Charles' law.
V1 over T1
V1.
to V2 over T2.
And pressure law. Well, if it says pressure law, what it must have in it?
Pressure.
Pressure and temperature.
Pressure and temperature, right? So that'll be what?
P1 over T1 is
T1
equal
equal to P2 over
T2.
T2.
All right, good. In Boyle's law, what remains constant?
Temperature.
Okay. Nikolai, for Charles' law, what remains constant? Nikolai, talk to me, Nikolai. For Charles' law, what remains constant? So what two things you see in here, Nikolai?
Pressure.
Pressure remains constant for pressure law. What do you guys think remain constant?
Volume.
Volume.
Volume, right? Because you're dealing with pressure and temperature. Nice. Okay, good. So let me
Volume.
tackle some questions. So this is a question you might get in the exam. They might be like, describe how the graph of volume versus temperature in Celsius of a gas can be used to derive the Kelvin scale. So you would have to draw this graph here, where you have volume in meter cube versus temperature in degrees Celsius. Like I said, is 0 degrees Celsius the coldest temperature?
No.
No.
No, it is not. So will the volume be 0 at 0 degrees Celsius?
No.
No, sir.
No, it's actually quote unquote 0 at
Negative
Minus 273.
Minus 273.
good. And that's how we came up with the conversion, right? That's how we came up with the conversion. So I have like a perfect answer over here. You would say for a fixed mass of gas at constant pressure, the volume of a gas varies directly with its temperature in accordance with Charles' law. If the volume of a gas is plotted against temperature measured in degrees Celsius, the graph is a straight line, right, showing that volume increases uniformly as temperature increases. But when this straight line is extrapolated backwards, it does not pass through the origin. We know that. Instead, it intersects the temperature axis at approximately minus 273 degrees Celsius, where the volume of the gas becomes 0. This temperature represents the lowest possible temperature, known as absolute zero. At absolute zero, molecular motion ceases and the gas would theoretically have 0 volume. The Kelvin temperature scale is derived by redefining temperature so that this point corresponds to 0 Kelvin. Hence, the Kelvin scale is obtained by shifting the Celsius scale upward by 273 units. So, on the Kelvin scale, a graph of volume versus temperature passes through the origin. So did I say anything here that you did not know?
No.
No, sir.
No? Okay.
Nah, so
Good.
I don't think we'll have much lines to write all that though.
Yeah, so are you okay with this, right?
Yes, sir.
All right. And if they were to say the mathematical relationship between Kelvin and Celsius, well, temperature in Kelvin would just be equal to what?
Degrees Celsius plus 273.
Okay, good. Nice. Um, let's do a question quickly. So any volunteers?
I don't mind.
All right, Nikolai, give it a read.
A piston traps a mass of gas in a cylinder at 25 degrees Celsius. The pressure of the gas is 5 atmospheres.
Wait, come on a second. I'll
Yeah.
share up the live and thing on YouTube so people that need help could see it. Right? Give me a second, I'm gonna just share it up. So yeah, you guys could share up the live.
Yes, sir. Continue.
Yeah, continue. So a piston traps a mass of gas in a cylinder.
At 25 degrees Celsius, the pressure of the gas is 5 atmospheres when its volume is 50 milliliters. Calculate the volume of the gas if the pressure drops to 1 atmosphere at constant temperature.
Okay, let me just say this, right? When you're dealing with these gas laws, the only thing you have to be mindful of is the temperature. When you're dealing with the temperature everywhere needs to be in what?
Kelvin.
Kelvin.
sir.
So we have milliliters, that's fine, that's fine. The main issue is that we need to convert degrees Celsius to Kelvin, so it'll be the linear relationship where it cuts the origin. Right, so Nikolai, they're telling us at 25 degrees Celsius, the pressure of the gas is 5 atmospheres. We want to call that T1 or T2?
T1. No, T2.
T2, you sure?
Nah, my bad, T1.
Call that T1. And they're saying the pressure of the gas is 5 atmospheres, so that would be initially. So we want to call that
T1.
all right, P1, yeah. And that would be equal to 5 atm. And they say when its volume is 50 milliliters. So V1 is equal to 50 milliliters. And Nikolai, what do they want us to calculate?
The volume.
Right, they want to calculate the volume. So this will be V1 or V2?
V2.
So volume is changing, and they're saying if its pressure drops to 1 atmosphere. So this will be the what pressure?
P2.
Yeah. And what are they saying, Nikolai? At what?
At constant temperature.
Nikolai, which one is this?
Is
Charles.
it pressure? Is it the pressure law?
Nah, what mean the pressure law?
Boyle's law.
Yeah, this is Boyle's law. Because Nikolai, when you look at what's changing, the volume is changing, and we're dealing with pressure. So we're looking at P and V. And the temperature remains constant. So that's Boyle's law. Do you remember Boyle's law?
Yes, sir.
Talk to me. What's Boyle's law?
Was Boyle's law the fixed
So
mass of gas?
wait, we dealing with the formula. So yeah, this is the formula. We know the formula involves P and V. We know the formula involves P and V. So formula with that.
Would that be P1 V1 is equal to P2 V2?
Correct. P1 V1 is equal to P2 V2. Guys, do we care about temperature in this instance?
No,
No, sir.
No,
because the
because the temperature
temperature
is
is
constant.
constant.
Right. So what is the pressure? What is P1?
5,
5. What is V1?
50.
Do I know what the final pressure is?
Yeah, it was 1.
Do I know what V2 is?
No, sir.
No. Right. So this is real simple. What's 5 by 50?
Wouldn't that be
250.
550?
That'll be 250. And 1 by V2 is just V2. So you have your answer right there. V2 is what? Look at the units we're dealing with in this question. We're dealing with milliliters. So V2 would be equal to what, Nikolai?
Milliliters.
Yeah, 250 milliliters. Guys, that was hard. That was easy, Max.
That was easy, sir.
Easy.
Just remember
Easy max.
So I have a question.
Talk to me.
So I've seen a lot of teachers rearrange the formula, right? That's only when you're dividing.
It depends on what they are asking for. Let me explain something. So in this question, the final pressure was 1 atmosphere, right? If the final pressure is 1 atmosphere, then P2 is going to be 1. What is 1 by V2?
V2.
Just V2, right? If, however, it was something like 7 V2, what would I have to do next? If it was 7 V2.
Subject of formula.
Exactly. If you had 250 is equal to 7 V2, in this instance, you'd have to divide both sides by
7. Oh, 7, I mean, sorry.
7.
By 7.
Hope you understand. Like they make it real simple for us on this particular question. Real simple. It really depends on what the question is asking of you and what the information is. Yeah. Right. So I hope you understand. For this question, it was just 1 by V2, which is V2. So you didn't really have much to do. You understand?
Okay, so
Yeah, sure.
yeah.
Tomorrow I can do a question on my next. I don't trust that.
No, sir. No, I understand.
Right. Nicola, read part 2 for me. Nicola, read part 2 for me fast. Fast. We're on speed tonight.
Yes, sir. After resetting the piston, the gas returns to its initial pressure and volume. If the volume is now fixed while the gas is heated at 60 degrees Celsius, calculate the final pressure of the gas.
So Nikolai, what is now fixed? What is now fixed?
The volume,
If the volume is fixed, then what 2 things will be changing?
the pressure, and the temperature.
Could you think of any law that has pressure and temperature in it? Any law that has pressure and temperature in it.
Pressure law?
Yes, pressure law. And what is pressure law? What does pressure law look like?
T1 equals P2 T2.
Nah. Guys, NS P1 over T1 is equal to P2 over T2.
Yes, sir.
So that was just
Yes, sir.
Nah. I hear you say P1 T1 is equal to P2 T2.
Oh,
I didn't hear you say they divide. You gotta be very careful.
divide. Oh, yeah. My bad.
That's okay. So it was returned to its initial pressure and volume. So what would P1 and well, we don't really care about volume there. We mainly care about pressure. So if it was returned to its initial pressure, what is P1 going to be?
It'll be 5.
Do you guys understand that? They said it was returned to its initial pressure. What was it? What was its original pressure?
Be 5.
It was 5. And that was stated in the question above. Now the gas is heated to 60 degrees Celsius. And they want to find the final pressure. So they want us to actually find P2. Do you all
Yeah.
understand that or not? They want us to find for P2.
Yes, sir.
Yes,
Um,
sir.
Could anybody tell me the original temperature at T1?
Was
Uh,
25.
25.
And could anybody tell me what T2 was?
60.
60.
Yeah,
60.
no, a lot of students would just go ahead and work with this, right? But that's wrong. Why do Nikolai?
You
Yeah, I
have to
converted to
that.
Kelvin
Alright, so how are converting this to Kelvin?
by adding 273 degrees.
Right, adding 273. What would I get?
I got 298 for the first one.
Right? And the other one in Kelvin will be what?
333.
Right, so let's plug everything in now. So what's our initial pressure?
Our initial pressure was 5.
Our initial pressure was 5, right? What is our initial temperature?
298 degrees Kelvin.
Degrees Kelvin.
Just Kelvin.
Take your time, Nikolai. Right? Son, be careful. Alright, so P2. Do we know what P2 is, guys?
No, sir.
Nah, we don't know what P2 is. Do we know what T2 is?
Yes, sir. 333 Kelvin.
Right. Let me call upon Kimura for this one. Kimura, you there?
Yes, sir.
Alright, so Kimura. When you look at this, is P2 the subject of the formula right now?
No.
Yeah or nah?
No.
Nah. Right now, P2 is being divided by what?
100.
Right now you're seeing P2 is over. Wait a
200.
okay. Come on a second. Wait a come on a second, right, guys? Yeah. So, Kimura, right now P2 is being divided by 333. I'm never seeing that. You're literally seeing it over 333. You see, not on that.
Yes, you know.
So, I have a question. What do you guys typically do? Do you all typically cross multiply or do you all just multiply by 333?
I multiplied 333.
Yeah.
Okay, I would multiply by 333, but I know a lot of students like the cross multiplication. This is just maths. Kimura, if P2 is being divided by 333 and they want to get rid of this, what will be the opposite of dividing by 333?
Multiply.
Alright, so I can multiply both sides by 333. If I were to do that, I would end up with 5 over 298 multiplied by 333. The 333 is going to cancel off here to just leave us with what? We're going to leave us with
P2.
P2.
just P2 because the 333 would cancel out, guys. Because the opposites are divided by 333 is multiplied by 333. So it'll cancel off and that'll leave me with just P2. So, guys, put this into a calculator and let me know what you guys are getting.
I got 5.5.
I got
5.8.
5.56 or 5.6.
Give me an answer to 2 decimal places.
Okay, well, 5.59.
Is anybody else getting 5.59?
Yes, sir.
Yes,
Yes.
yes, sir.
Sir.
Yes, sir.
And what units would I use for that? What units would I use?
ATM.
Yes,
Kelvin.
I would use ATM because atmospheres. All right, so I feel like some people are are still confused with the question, so I'll go through it again. The first part, I feel like it was sort of straightforward. If you want to convert Kelvin, if you want to convert degrees Celsius to Kelvin, you just add 273. That's all. For the other question, they told us that we had a piston and it traps a mass of gas in a cylinder. They told us the temperature is 25 degrees Celsius, and they said the pressure of the gas is 5 atmospheres when its volume is 50 milliliters. And they wanted us to calculate the volume of the gas if its pressure drops to 1 atmosphere at constant temperature. When you read that, does it sound like noise in your head? Be honest with me.
Yeah.
Don't be ashamed, guys. It's fine, it's fine.
Nah.
If it does sound like noise in your head, here how I want you to compartmentalize it. So the way to calculate volume, they want you to calculate volume. Do you think that'll be the initial volume or the final volume? If they want you to calculate for volume.
The final volume.
The final volume.
Correct. Because in the question, they gave me the initial pressure. The initial pressure was 5 atmospheres. So they gave me that already. They gave me P1. And if you look, they gave me the volume as well. They told me the volume was 50 milliliters. So we have pressure and we have volume. So obviously, when I say calculate the volume, we're talking about V2. I'm going to understand that part. So we want to find V2.
Yes, sir.
Yes.
Now they're telling us that there's a change in what? There's a change in what?
The atmosphere. Pressure.
There's a
Atmosphere.
change in pressure. So immediately, you guys should see that we're dealing with volume and pressure. What comes to mind anytime you see volume and pressure?
That will be
Boyle.
So, Nikolai, Boyle's law, right? I don't know if you're okay with that, Nikolai. Boyle's law. Pressure and volume. Anytime you see pressure and volume, that's Boyle's law. And to further prove that point, they said constant temperature. If it's a constant temperature, the only things that are changing is the pressure and the volume. So, P1 V1 is equal to P2 V2. When you look at it, my initial pressure was 5 atmospheres, so plug in 5. My initial volume was 50 milliliters, so plug in that. My second pressure, they said it dropped to 1 atmosphere, so I replaced P2 with 1, and they actually want us to find the volume of the gas after you drop the pressure. So we don't know what V2 is. We have 1 by V2. 1 by V2 is just V2. So V2 is 250 watt. When you look at the question, they gave us volume in milliliters. So you'll say V2 is 250 milliliters. Are they sure they understand the question?
Yes.
Yes.
Yes,
Yeah.
sir.
All right. So again, are they seeing that, the
Yes.
change in the pressure and volume is responding? So you're dealing with pressure and volume. Boyle's law for sure. All right. In the next question, they're saying that you reset the piston. If you reset the piston, the gas returns to its initial pressure and volume. So immediately, you know that the pressure is going to return to what? What was the original pressure?
25. Atmosphere.
It was 5 atmospheres. That was the original pressure. So P1 is 5 atmospheres. And they're saying the volume is now fixed. If the volume is now fixed, what are the things that are changing if the volume is fixed?
Pressure and temperature.
Pressure and temperature.
Right. So immediately, we are working with pressure and temperature. Immediately, because the volume is fixed. They're telling us the temperature changes. It's changed to 60 degrees Celsius. What was the initial temperature?
25.
25.
Cool. So here what? Just by reading volume is now fixed, you should be thinking pressure and temperature. They gave you the initial pressure, 5 atmospheres. We have that. I replaced P1 with 5. the initial temperature, they gave us that it was stated to be 25 degrees Celsius. But no. I cannot work with degrees Celsius. I have to convert that to Kelvin. So to do that, I added 273 and I got 298. So I replaced T1 with 298. They actually want us to figure out the final pressure, which is P2, so I'll leave that blank. And T2, they said it was 60 degrees Celsius, so you add 273, that's how we get it 333. You notice that P2 is being divided by what? What's P2 being divided by?
By 333.
Right. If P2 is being divided by 333 and you want to make it a subject, you got to do the opposite of dividing. So you got to multiply both sides by the 333, and that's how I got my answer. P2 is 5.59 atmospheres. Let me know if you guys understand.
Yes,
Yes.
sir.
Yes,
Yeah.
sir.
Okay, bet.
Sir, you
Yeah.
can leave it to 1 decimal place, or you have to put to 2.
Well, they typically want 2 decimal places.
Okay, same thing.
2 decimal places or 3 SF.
Excuse me, sir.
Yeah, talk to me.
So if they ask you to find, like if they give you a Kelvin temperature and ask you to find it in Celsius, you have to take away 273 from it.
Correct. So just to answer what he said, let me explain that, right? Consider you had 70 degrees Celsius. What would this be in Kelvin?
70 plus 273.
Right? What is 70 plus 273?
343.
So question, if I wanted to go from Kelvin back to degrees Celsius, what do you think I'll do?
Minus.
Minus
273.
And that would give me back the 70 degrees Celsius. So that's an excellent question you asked there. So to convert from Celsius to Kelvin, you add 273. To go backwards, you minus 273. Cool. Any volunteers for this question? Any volunteers?
Me and
You know what?
Celine.
All right, no problem, Sarah. Sarah and Celine.
As soon as I start to eat, I get
Right,
called.
so Celine, give the question a read.
Occur, no problem. A car tire is pumped to a pressure of 2 times 10 to the 5th Newton meters per second or something. No, wait. Okay, I'm being stupid. Newton meters in the morning when the
Newton meter
temperature.
squared. Newton per
Newton
meter
meter
squared.
squared.
Newton per meter squared. Newton per
Newton per
meter
meter
squared.
squared
Right.
in the morning when the temperature is 23 degrees Celsius. Later in the day, the temperature rises to 34 degrees Celsius. English A done. Calculate the new pressure in the tire. The volume of air is kept constant.
Okay, guys. If the volume is kept constant, what are the things that are changing here?
Pressure and temperature.
Pressure and temperature.
Temperature.
Right. So Celine, before you see that last part, this last part is clutch. I don't have to read anything, and I could just read this last part and figure out what law to use. So what we call the law with pressure and temperature?
Pressure law.
Pressure law.
What is pressure law, Celine?
P1 over T1 equals P2 over T2.
Easy, right?
Bad man.
So here what? We need to determine what P1 was. So what was the initial pressure they mentioned?
2 times 10 to the power 5.
Right? Newton per meter squared, right?
Right.
Cool. If you're wondering where that comes from, pressure is equal to force over area. You know what I mean? And so like force is newtons and area is meters squared. So Newton per meter squared, which could be represented as Nm minus 2. That's where it comes from. If you was wondering.
That's
Right.
so cool.
And the original temperature was what?
23 degrees Celsius.
Oh, then we could work with that. We could work with that 223. I mean, that
Sure.
23.
No, sir, you have to convert it.
How to convert that? So, Celine, how I convert that to Kelvin, Gil? How do that?
You are adding 273 degrees Celsius.
All right, and what would I get?
296.
Kelvin.
Cool. So we have P1 and we have T1. Yippee! Let's say in a later any day, the temperature rises. So that would now be T what?
T2, sir.
Dos.
T2. So we're gonna obviously we can work with 34 degrees Celsius, right? Add our 273 to that. We know we know the lingo by now. So what would we get there? What is 34 plus
307.
27?
307.
Alright, cool. And they want us to calculate the
New pressure P2.
all good. I hope you see how easy if a question like this come. That's the easiest 5 marks you get in there, you know.
3
Like
marks.
I hope so.
all,
I hope so.
all I had to read is this part over here, you know. Just read this part here, you know, and it will tell you which one to use. If the volume is constant, then pressure and temperature are changing. P1 over T1 is equal to P2 over T2. You just have to skim through the question for the information and you're fine. So, yeah, Celine, where's P1?
2 times 10 to the 5th power Newton
All right,
meters.
where's T1?
296 Kelvin.
Right. What is P2?
We don't know yet.
We don't know what that is, so I'll leave it
We have
blank.
to unlock that part.
We didn't unlock the character yet. What is T2?
Yeah. 307 Kelvin.
Right? So let me ask you a question. With Celine, Sarah, is P2 the subject of the formula there?
Yeah.
Yeah?
Nor.
No.
Nor.
Sarah, take your time. Sarah, right now, P2 is being what? What happened to P2 right now?
Divided by 307.
If it was the subject of the formula, then it would have just be P2. So tell me, Sarah,
Oh, so we had to make it the subject of the formula by cross multiplying.
you could cross multiply, that's fine,
But you
but
could
you could
multiply by
just
307.
exactly, we could just do that. If you're confused, earlier, hear what? Right now, P2 being divided by 307. What is the opposite of dividing by 307? What's the opposite?
Multiplying.
Multiplication.
Right, and obviously if I multiply, it's gonna cancel off, chap. It's gonna cancel off. Right, so and whatever I do on one side, I must do on the
Other side.
Ultra side.
right. So that'll be 2 by 10 to the power 5 all over 296 multiplied by 307. And that'll be equal to P2. If you're wondering where the 307 went, earlier we multiply both sides by 307. If you multiply this by 307, it's gonna cancel off to leave you with just P2. Nikolai, I see you have a question. Talk to me.
Was it -5 or +5? Oh,
Positive 5.
Positive.
yeah.
If it was -5, that'll be an incredibly small pressure. Very, very low pressure.
I was just making sure.
Folded under negative pressure.
And we're dealing with our car tire here. Car tire, nah. But it's a good thing you're making sure. Yeah, physics is math 2.0. Like, earlier, this is where you're gonna apply the math you learn in physics. If you do unit 1 or unit 2 physics, you can see differentiation. I try to say a little bit fancy, right? But you can see differentiation. You can see integration. You can see a bunch of calculus, guys. Bunch of calculus. Just putting out there. So yeah, what again for P2? Give me answer the two decimal, please.
2.07 times 10 to the power 5.
2.07 by 10 to the power 5.
Yeah.
And what are the units?
Newton meters
Newton
squared.
meters squared.
Newton meters per yeah.
All you losing our 5 marks, all again our 5 marks. So now.
So you was right. Physics was
Again,
better than math.
Full marks.
That easy. All you sure all with me, right? Let me know. All with more like all you gonna get a mark, so.
Yeah, we only was.
Of course, we're gonna get a
Yes.
Right.
So
Yeah, talk to me.
I have a question, right? If you leave your answer like normal, like when I say normal, like not penny multiply by 10 to the power 5, you get it wrong? Or
Now, here what's it? I want to know what calculator I have that will give you that as normal. Most calculators would never give you that as normal.
I have
Like
a sharp.
the sharp giving you it as normal.
Yeah, like 207. What's that? Long.
No, my can still give it like that too. I had to convert it to standard form.
Okay, well let me explain how to convert it to standard form then. Yeah, let me do that. because the answer that they gave you was by 10 to the power 5. So let me explain. And this will help you guys in your math paper ones as well. By the way, I'm gonna be doing lives as soon as Friday is done. We're gonna be focusing on paper 1 for maths. All right, just putting it out there. So let me show you guys how to write this in standard form. So we have 207,432.4324. Are you with me?
Yes.
Yeah.
Here how it's working, right? I'm going to shift the decimal place right before the first significant number. The very first significant number. What's the very first significant number here?
2.
2.
Those.
Right, so 1, 2, 3, 4, 5. So 2.074324324. Obviously not gonna write that. So then you're gonna round it off to 2 decimal places. So what is the second decimal place here?
7.
7.
Right, what's the number after 7?
4.
4.
4. So like, since 4 is 5 or less. Okay, since 4 is less than 5, 4 is less than 5, right? 4 is less than 5. So we're gonna round down. So our final answer is just gonna be 2.07. And notice that we shift the decimal place 5 spaces to the what?
Left.
Since it's 5 spaces to the left, it's gonna be 2.07 by 10 to what power?
The positive 5.
Oh, by 5. Smart.
Let me know if you're okay with that now.
Yes.
Yes, sir.
Yeah.
Yes,
Okay, somebody asked me, somebody's asking me about Pascals and what have you. Hear what, right? With these types of questions, generally speaking, you don't want to do that. The only thing you do want to convert is, somebody tell me, the only thing you want to convert is
Kelvin.
Temperature.
The temperature.
Kelvin, because all of these laws rely on absolute temperature, not degrees Celsius, absolute temperature. Yeah. Right? Cool. Everybody got this?
Yes, sir.
Yes.
If you get a different answer, more than likely you just work to the temperatures in degrees Celsius, and that's a big no-no. Right? So Kiki on TikTok, that's probably where you did. You probably used the 23 degrees Celsius and the 34 degrees Celsius. All right? Cool. You see these theory questions. I have all the answers here, and I'll just explain it to save time. Using the kinetic theory of matter, explain why the increase in pressure occurred. Now, tell me something, guys. If you leave something in the sun, we talked about this yesterday. The sun is going to emit short wavelength IR radiation, and that's going to cause temperature of the tire to decrease or increase.
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 All right.
Increase.
If you're hitting something with thermal energy, the particle is gonna receive that as what energy?
Kinetic energy.
Kinetic energy.
Kinetic.
Right. And if particles gain kinetic energy, they'll want to what?
Vibrate.
Expand.
They'll start to move about. They'll start to move about. Some bonds will be broken and they will start to hit the outer surface of the tire. And if they're hitting the outer surface of the tire, what's gonna happen to the pressure of the tire?
They'll
More
expand.
close painted area. So it's more
Shall
pressure.
increase.
Will increase. So here's the ideal answer. So when the temperature is increased, the air molecules gain kinetic energy, causing them to vibrate and move about more frequently. As such, they would hit the walls of the tire, exerting a force, thus increasing pressure. Everybody okay with that?
Yes, sir.
You could explain it one more time, please.
All right, no problem. Shakina, that's you?
Yes, sir.
All right, Shakina, let me look at this in a bit more detail, right? So, do you know that all matter is made up of particles in constant random motion or not?
Yes, sir.
Right, so here what's happened. So guys, quickly, what state of matter does this look like? A solid or liquid?
Solid.
Because it's very closely knit together, right? And it's like really tightly bonded. Shakina, if I apply heat energy to this, Shakina, you there?
Yes, sir.
if I apply heat energy, the molecules inside of the particles are going to gain kinetic energy. Do you know what kinetic energy is? If not, that's fine. I'll explain it to you. All right. So, Shakina, once something is moving, once it's in motion, it will have kinetic energy. So, kinetic energy is the energy something has by virtue of its motion. If you understand what I mean. So, like Shakina,
Yeah.
imagine a fat man. Imagine like a fat man falling down, right? Compare that to like a skinny man falling down. Who would have more kinetic energy?
The fat man.
Yeah, the fat man, right? To stop the fat man, you would need a lot more force. Yeah, so kinetic energy is the energy something has by virtue of its motion. So what I'm saying, Shakina, when you apply heat energy to these particles here, they're gonna gain kinetic energy, meaning that they're gonna start to move about more. So Shakina, if they start to gain kinetic energy and they start to move about more, do you think the bonds will get stronger or do you think they'll break away from the bonds? Tell me, Shakina.
So it will get stronger.
Nah, it's not gonna get stronger. Not gonna get stronger. Okay, so like these molecules here, they're like tightly bound together, right? But when you give them heat, now they start to move about. Start to move about. If they start to move about, do you think it strengthens the bond between the particles, or do you think
No,
they would
sir.
like and you like and
It's
you
a
can see
weak.
it breaking away? You can see it like breaking away,
Yes, sir.
right?
Yeah.
And if it's at a breakaway, it's gonna hit the walls. I'm not sure if you've seen that, but it's hitting the walls. And if it's hitting the walls, what would happen to the area here? Do you think the area would remain the same, or do you think it expand?
It will expand.
Because you see, the particles want to like move away. They start to vibrate, so they want to move away. So I hope you understand what I'm saying. So that's why
Yes, sir. I understand.
I'm saying when I increase the temperature, the air molecule is gonna gain kinetic energy. Right? If they gain kinetic energy, they're gonna start to vibrate and move about more. And if they're vibrating and moving about more, they will hit the walls of the tire, exerting a force. And this would increase pressure. So I hope you guys understand.
Yes, sir.
Yes, sir.
Yes, sir. Thanks.
No problem. What you know, I'm doing here, buddy. Anyways, let me tackle this question. It's a nice question. Any volunteers?
Me, sir.
All right. This question is a little tricky, but it's fun. It's fun. Oh, actually, I wouldn't even say it's tricky. I wouldn't even say it's tricky.
Oh,
Give it a
nah.
read. Give it a read.
Calculate the ratio of the new volume to old volume, V2 over V1 for the tire.
Tire.
Whoa! Hey, never mind. Yes, I know it's tired.
I think
Anyway,
you're tired. I think you're tired. I think you're tired.
yeah,
I think you're
you're all
tired.
tired.
Yeah. But
Shh, I say tired, right? If the pressure if the pressure is held constant while the temperature rise from 23 Celsius to 34 Celsius. Yep.
okay. I'm asking that question, right? We talking about okay, when you read the question, you see they're talking about what two things here. So like wait. Before we even do anything, what I'm asking that question, what is constant? What is constant?
Pressure. Pressure, sir.
Oh, don't rush again. Oh, don't rush. Hey, when somebody answering, don't rush them. No, we know any markets. Right? So if the pressure is held constant, Shashti, hope you're saying your name correct.
Yes.
What will change? The pressure constant, you know. So what will change? What will be two things changing?
That'll be the volume and temperature.
Okay. So guys, well, Shashti,
Yeah.
do you know anything that deals with volume and temperature?
Charles' law. So that will be V1 over T1 equals to V2 over T2.
Okay. I hope all you appreciate the hack, right? Anytime you see them talk about something held constant, that's telling you which law to use. Right? It's telling you directly.
Yeah.
So are you guys okay with how I pick V1 over T1 is equal to V2 over T2?
Yes.
Yes, sir.
Good. And they will actually want us to find V2 over V1. That's what they want me to figure out.
Okay.
Now, Shashti, it looks complicated, but it is not complicated. I promise you.
Okay.
It's more maths than anything else. Because if we want to find for V2 over V1, we'll have to make that the subject of the formula. So here what? Do I know what T1 and T2 is?
Yes.
Tell me, where's T1?
T1 is 23 Celsius, but you have to plus 273 towards it to make it Kelvin. So that will be 23 plus 273. That will be 296.
And we
And the
calculate
next
this up of, but yeah, T2 is
307.
nobody confuses us as yet, right? Nobody confused, right?
No.
Where's T1?
T1 is 296.
Yes, guys, this is the correct way to spell tire. It is.
Yes. Yeah.
Right?
Yeah.
People in Trinidad, they spell all kind of madness. Like professional, talking about professional tire places, you know. Like on the billboard, they will literally spell TIRE and all kind of madness.
Mm-hmm.
Anyways, where's T2?
307.
Here what? We want to make V2 over V1 the subject, right? They want we to find V2 over V1. You see in that, yeah?
Mm-hmm.
So maybe it might help if you cross multiply here.
Yeah, I was
Maybe it
thinking
might.
about that too. So
If you cross multiply, what are you gonna end up with?
that'd be V1 by 307.
I would advise you to write it like this. So say 307 V1, and that will be equal to what?
296 V2 by V2.
So again, we want to make V2 over V1 the subject of the formula. That is what we want to do.
Wait, do you have to like divide? No.
Tell me what you think I should divide by.
You have to divide 307 V1. No, well, 296 V2 over 307 V1.
Wait, so you want to divide both sides by what?
By
I promise you the answer is right here. We want to find for V2 over V1. First of all, are you seeing anything by V2?
well, yeah, that'd be 296.
Wait, no, like in what we want. Are you seeing anything in front of V2?
No, sorry.
Nah. So what do you think we should do then? Right now we have 296 multiplied by V2. Well, in our final answer, we don't want anything by V2. So we think
So
I
you
should
have to just multiply 296 divide 296 to V1. Well,
yeah, I should divide by 296. Yeah.
Yeah.
And so now
You
I
just
would
get
have cool. V1 is equal to V2. We're real close, you know, we're real close, but we want V2 over V1. So we think I should do on both sides now.
Do you have to bring V1 over to V2 now?
Yeah.
So
we think I should.
you just had to like divide it. So that'd be V2 over V1.
I tell you, this is a maths question. So long story short, V2 over V1 is gonna be what?
V2 that'd be 307 over 296.
Are you understand this or not?
Yes.
Yes.
Yeah,
Yes, sir. Yes.
let me run it back again. They're saying what is held constant? What they're saying is held constant.
The pressure.
Right, the pressure. If the pressure is held constant, then volume and temperature are changing, right? So immediately you should be thinking about Charles chocolate law. You know what I mean? V1 over T1 is equal to V2 over T2. Yeah.
Yeah.
And then they are giving you the initial temperature and the final temperature, so T1 and T2. Obviously, you can't work with that in degrees Celsius, so we convert it to Kelvin one time. and I plug it in. Now they want us to find V2 over V1. V2 over V1. So from here, it's just a matter of making known what the subject of the formula.
V2 and
V2
V1.
and V1.
V1. Yeah.
Correct. So I decided to cross multiply. Maybe it might have been a bit easier. So I cross multiplied. Notice in my final answer, are we multiplying V2 by anything?
No.
No, sir.
No. So I divided throughout by 296 to get rid of anything that was in front of V2. You know, because in my final answer, I don't have anything by V2. So now I have V2 is equal to this. Now in my final answer, it's over V1. So then I decided to divide both sides by V1. And in doing that, what happened over here, Shashti? Tell me, what happened over there? Since I divide by V1 on that side, what happened? Okay, and here, Shashti, anybody want to tell me?
Oh, sorry, I was talking and my mic was muted. My bad. So that would be just 307 over 296 equals to well, you take it away. So that'd
Right.
be yeah. So that would be just yeah. That's the
So why did we divide by V1? We actually wanted V2 over V1, so I divided both sides by V1. And I hope you all could see, by dividing this side by V1, the V1 cancelled off to leave us with just 307 over 296. So that is the ratio. That is the ratio over there.
Yes, sir.
Do you guys genuinely understand?
Yes, sir.
Yes, sir.
Yes, sir.
They could ask you a question like this, but
Yeah,
instead
sure.
of okay, they could ask you a question like this, but instead of V2 over V1, it could be P2 over P1, same mojo, just how to make the ratio the subject of the formula. Yeah.
So, and
Alright,
if they wanted V1 over V2, you would have just divide by the 307 on this side, on the other side first to make V1 the numerator.
yeah, you could do that, or you could just invert it.
Okay, right.
Just invert it because watch. I'm not sure if you guys know this, right? But for any equation, if you have one term represented on either side, you are allowed to reciprocate both sides, and it would still be equal. You see, it's still equal, so it's legal. It's a legal move to making maths. So if you wanted V1 over V2 and you find V2 over V1, you just reciprocate both sides and you get through. Yeah.
Okay, thanks, sir.
So do we feel like the dog? Right, Celine, sing the song. Celine, sing the song. Sing the song.
Let me know. Let me know.
Right. Yeah, so I hope you're okay. Big up these sound effects one time.
Gracias.
So this is a little summary. Take a screenshot. This is a summary. Take a screenshot one time. Quick. Move on with pace.
Excuse me, sir.
Yeah.
So they just actually bring graphs like that in the exam?
Yeah, there's actually bring graphs like that in the exam. They could give you different values for pressure and volume and tell it to plot a graph of P versus 1 over V or something like that. Yeah, this is fair game. So I put it here so you could expect what the graphs would look like. They would never do something like this. They would never do something this evil. In CSEC physics, you guys will always 90% of the time deal with a linear graph. In 2025, it was real weird. In 2025, it was real weird. I don't know if all you know what I mean.
Sir, I don't want to get that. Sir,
Yes,
I don't want to get that. Or
I hope
that's
so.
like
I hope you guys don't get that. And well, here's one you should know as well. This is the combined gas law, combining everything. So P1 V1 over T1 is equal to P2 V2 over T2. And this is what would happen if only the mass is constant. If only the mass is constant, you use this one. P1 V1 over T1 is equal to P2 V2 over T2. Right. So let me know if I have the screenshots. Again, moving on speed. Right.
Good
Right.
night.
Good night, son. Good night, son number 2. All right. So we done with that. Are you ready to move on to waves and optics now?
Yep.
Yes, sir.
Yes, sir.
Sure.
Okay, cool. I just gonna give a quick summary, right? So if you didn't know, waves is carry energy. Waves is carry energy without carrying matter. Now, some waves must propagate through a medium. And let me give you an example. And so you know about sound waves.
Yep.
Yes,
Yeah.
sir.
I don't know if any of you was bored, but like when I was in primary school, I used to like put my head on top of the wooden desk and like hit the wooden desk. And you know how I hear the vibration. I don't know if you know what I'm talking about, like
Yes, I do.
Yeah. So
you know you have the wooden desk,
you
right?
like
And,
it's
and
like
you
you on the
Yes.
yes.
and like
I'm
you
So
you,
you
you
was
come
okay?
over here and you hear the sound. So
yeah.
like
Yes.
Good, but
So you was okay?
yes, I was fine.
not
Probably a bit bored though. Probably a bit bored, but um you see this part over here where we're saying some waves must propagate through a medium. That is what I mean. So the sound waves would have relied on, the wood, when you hit the wood, to be transferred, propagated to your ears. Propagated just means transferred. Right? So like it must propagate through a medium, like spread through a medium. And if you hit the wooden desk, what's the medium in that case? What's the medium there through which sound is traveling through?
The desk?
You wouldn't have to?
Yeah. And when you speak, you're not seeing it, but there's a bunch of particles in the air, and when you speak, it causes the particles to vibrate back and forth, and that reaches your ears. So on Earth, air is the medium through which sound is traveled. I mean, sound is propagated. Do you think in space, if you scream, somebody would hear you?
No.
Sure.
No.
Absolutely not.
Space is something called a vacuum. There's no particles. There's like, okay, see how on Earth, if I scream, you will hear me, you wouldn't hear me in space. You wouldn't hear me in space. There's no particles to propagate in a vacuum. Space is a vacuum, in case you didn't know. Right. An example of something that does not require a medium to propagate is everything in the electromagnetic spectrum. Do you guys know what it has in the electromagnetic spectrum or not?
Yeah, sure.
Yes,
You know, like
That's like Roy G. Biv.
no, that's not Roger Biff. I'm
No,
talking about
Oh, shoot.
radio
it's a
waves.
light.
Yeah.
Phases and stuff like that.
Alpha, beta, gamma.
Alpha, beta, gamma. Yeah.
Yeah. So like, let me just sum.
Sir,
Yes, Shakina.
what Peter's used to remember the order in which the
Oh,
electromagnetic waves does.
I just use rich men
Yeah.
in Vegas use expensive gadgets.
So I find an area one raging Martians invade Venus using X-ray guns, and X-ray is literally X-ray.
I don't remember that one.
So,
Oh,
what are
So
acronyms
nerdy, you
for?
should remember that.
okay, should I see how nerdy I was when I was in secondary school? I was the nerd. That's the nerd. So I'm asking that question. You think sound waves could propagate in a vacuum, like in space?
Nor.
No. But let me ask that
Where?
question. Does the heat waves from the sun reach Earth?
Yes.
Yeah.
So let me ask you that question. Do you think sound waves and infrared, which is the heat waves, do you think they're of the same class? Do you think
No.
No.
No,
Not sure.
One longitudinal and one
they're
transverse.
exactly sound waves are longitudinal and everything in the EM spectrum are what?
Are Transverse. Transverse.
Transverse, correct. Yes, you see everything over here. These are things that belong in the EM spectrum. This is the EM spectrum. And you have to remember this. So rich men in Vegas use expensive gadgets. So radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma. Yeah. Bet. Cool. They involve oscillations where they can be just one oscillation called a pulse or a series of succession oscillations called a progressing wave. You guys will be dealing with progressive waves. Waves that require a medium like sound to travel, they are called mechanical waves because they rely on mechanical movements of particles. While those that can travel through a vacuum are called a class as electromagnetic, which we just discussed. So guys, sound is an example of a mechanical wave. Does it rely on a medium to be propagated?
Yes.
Yeah.
Sir.
Does anything over here rely on a medium to be propagated?
No, sir.
No, sir.
No. No. Right? So a wave is a means of transferring energy through a medium or space, vacuum, without the net transfer of matter. That's why I don't know.
Or horror.
And you're probably wondering why. Okay, earlier, anybody here into car audio?
So what
Anybody here
would?
into car audio? Car audio. Not nobody here into car audio, boy.
Or like you drop low hard ponka.
With like a T-line transmission, like a ported box. I literally have a 12-inch subwoofer right beneath my feet. Literally have one. But like, okay, I don't think you guys will get the reference, but if you ever go next to a ported enclosure, and if you put a piece of paper here, you won't see the paper being pushed forward. You'll see it being pushed back, push forward, push back, push forward, push back, push forward. It's not being moved in a sense. It's being like it's oscillating. I don't know if you know what I mean. Like if you have a ported enclosure and you put a piece of paper by the port, you'll see that the paper moves in out, in out, in out, in out. It doesn't. There's no net transfer of okay, there's nothing being moved in a sense. Like you're not moving to a different location. It's oscillating about like a start and an end position. There's no net transfer of matter because it's staying within like a fixed region. Car audio people, you know what I'm talking about? Like if you go next to a speaker, you just feel like a thumping feeling.
Yeah.
Yes, sir. Yes, sir.
Oh, yes.
Yeah. Yeah, like to and fro, right? Compressions and refractions is the proper way to call it. But this way you had to know. A wave is a means of transferring energy through a medium or space without the net transfer of matter. So cool. Let me go on to my notes now. So oscillation. An oscillation is a repetitive back and forth motion about a central equilibrium point. So we just talked about speakers, guys. We just talked about that. So like what I was saying, if you have a slotted enclosure for a subwoofer and you play like a bass note and you put a paper in front of the enclosure, you go see the paper going in, out, like to and fro, back and forth. That is oscillation, right? So oscillation is a repetitive back and forth motion about a central equilibrium point. Right, where's wavelength? Wavelength is the length between two successive crests or troughs. Are you probably wondering where's that crest and where's that trough? Odd math people, what wave is this?
Sine.
Sine wave.
Sine graph.
A sine graph, right? It's a sine graph. Sine graph. Math people should know this too. Right? So let me ask you a question. Ain't you seeing like the peak over here? Well, odd math people until you know that's the stationary point or the turning point.
Yes, sir.
But anyways, people are not doing odd maths. And you can see that this is like the peak of the wave.
Yes, sir.
Peak.
Right, what do you think we call this? The crest or the trough?
Crest.
Yes.
Right, let me just draw. Okay, and what do you think we call this?
Trough.
All right, what do you think we call this?
Also a crest.
Yeah, what do you think we call this?
Trough.
So a trough.
Trough.
So here what I saying, right? Here what I saying. I am telling you that the wavelength is just going to be the distance between two successive crests. So like, what do I mean by successive? Right, so you have a crest over here. The wave will go down. It will come back up. Another exact point in time, you'll have a next crest. So that's the successive crest. So the distance between two successive crests is your wavelength given by the symbol over here, lambda, right? Or you can think about it like this, between two successive troughs. This is also the wavelength. You guys understand?
Yes,
sir.
Yes, sir.
Yes, sir.
All right, so if I need to, I can take a little screenshot. Where's amplitude now? Amplitude is just the maximum displacement from the equilibrium position. Again, cardio people. And so you know about like the spider and like the X max and thing.
Yeah.
Yes, sir.
I really into cardio and thing, you know, like home audio and thing. And I should see my speaker set up. It's real nice. But
So yeah, that's true.
like the X max, that's like how far the subwoofer could extend outwards and then come back in. So like amplitude is kind of similar. It refers to the maximum displacement from the equilibrium position. In other words, like how far could something move from the resting position and then come back? That's amplitude. Period. Period is given by capital T, and it's just the time taken for one complete oscillation. Frequency, this is the amount of oscillations per second, and that's given by F is equal to 1 over period. So I'll probably take in screenshots.
Sure,
If I, yeah,
sure, you could scroll up. I think I can screenshot of the other definitions.
all right, take a screenshot fast, guys. Fully barbecue. Claude is goated. Claude is amazing. Claude is amazing. Yeah, boy. A lot of people don't know how goated Claude AI is. Claude is insane. Claude is much better than ChatGPT. All right. Okay.
Is the how better?
Say that again.
How Claude better?
Have you ever used Claude?
No, but I ChatGPT plus.
Okay, I have Claude Sonnets. I use the Opus model, that's the paid model, and I use any paid model for ChatGPT. Claude could make websites for you. It could make whole solutions for you. It could like analyze a whole data set, and it could make a fully published class paper for you. It's insane what Claude could do. Claude could make interactive models. If I tell Claude to generate like an interactive circuit within Claude, it could do that. It's crazy.
Do you think I should switch?
You should switch.
Alright.
Gemini is not the best way. Nah, bro.
Gemini is
Gemini
the
is
worst.
Claude is amazing. Right.
Gemini is good.
I love Claude. Claude is amazing. Right? But everybody had their preferences. Right? Now frequency is just the amount of oscillations per second. And that's given by F is equal to 1 over T. So here what? Let me just give a little I'll run through, right? Let me do a little I'll pick a little up. See what I know. Again, if I were to sit down and write these definitions and things, it'll take up a real time. Real time. Okay. So here what? Anybody can tell me what this symbol F represents?
Frequency.
Frequency.
Frequency in chat. Cardio people. I'll shame my boy.
That's a question though. That's a question.
What do we measure frequency in?
Hertz.
Oh, T.
Hertz.
Hz.
Oh,
Hertz. All right. And I remember this one Machine Gun Kelly song with what's your name again? One from Camila Cabello. Yeah. When it hurts.
Oh
I
my
don't know if
God.
you know what I'm talking about.
Yeah.
Your love is like
So keep singing.
no. I know what I'm gonna do. I'm gonna post them up. I'm gonna
At
post
the
them up.
concert.
I was sing for Leadia, right? But frequency is hertz. And is the amount of oscillations in what?
Per unit second.
In 1 second.
1 second.
What's the formula for frequency?
1 over T.
1 over
1 over
T.
T.
Oh.
That's the next question.
1 over
T.
And what's the formula? Okay, what
1
does
over
T
F.
represent? What does T represent?
Time.
Period.
Periodic time.
Periodic time.
Period. Which is measured in seconds.
Well, yeah,
Right,
yeah.
periodic time. And we measure periodic time. That's just in seconds, guys. SI unit for time is seconds. Nikolai, this is the time taken. The time taken for how much oscillation?
1.
Yeah, for one
Oh,
oscillation.
1.
Right. Okay, this weird symbol over here, what does it represent?
Lambda.
Wavelength.
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 And it tells us it's just simply the distance between what?
two
Two
successive.
Crest or
Two
drop.
crests or two
Consecutive
troughs.
particles.
Whoa. I feel like I need market here, boy. I think all of we understand it is between two successive crests or troughs. Tell me something fast. What kind of waveform is this? Wait,
Or
A cosine.
Cosine.
Parabola.
A cosine.
yeah, this is cosine, right?
Here.
Cool, this is cosine.
Yes, sir.
If I wanted to find wavelength, would I measure it from here to here, chat? Would I do that?
No.
No, sir.
No,
No.
sir.
Nah.
No, because this is our what? What is this? What's that?
A trough.
Trough.
And these are what?
Crest.
A crest.
I would not do that. That would give me half a wavelength. That would give me half the wavelength. I would really go from here to here. Are you understand?
Yes.
Yes.
Yes, sir.
Yes, sir.
Okay, cool.
So I have a question. We need to know what type of graph it is in physics. Like if it's cosine or sine, we are done that.
Nah, we don't know that just yet. If you're doing unit
Okay,
one, in unit one physics, it's real hard to know that. When you're looking at angular velocity and you're looking at, it's like a lot of it is described in terms of sine, pi, omega, naught, t. Yeah, you had to know the sine graph and English
You
little bit.
mean
so do you need to know that for drift velocity
basically-
too?
Say that again?
Do you need to know that for drift velocity as well?
Yeah.
So
Christopher is goated. If you like physics and you like maths, you will love unit one physics. Unit one physics is vibes. If you don't like maths, do it. Do it.
So what you're saying is unit 1 physics is basically add maths.
It's an application of, well, you'll see things like pure maths as well there. And well, unit two physics is a lot, but unit 2 physics is more electrical part of physics. Which is what I like. Right? What else do you guys have to know? Okay. What is amplitude?
The maximum
The
point.
maximum displacement from the equilibrium position, the equilibrium position.
Right. Somebody tell me fast. In 1 second, where's the maximum displacement there?
5.
5. Would I say 10?
No.
No, sir.
I'm talking about this, guys. Talking about this. Like how far it going now from the equilibrium. This is the equilibrium. That's like the resting position.
Mm-hmm.
Alright, so I think are they okay with the basics? Are they ready to do a question?
Yes, sir.
Alright. And the main formula you need to know here when dealing with these things is V is equal to what? V is equal to what?
Frequency times lambda.
Right. V is equal to F lambda. Ollie, don't forget this. Don't forget this. V is equal to F lambda. Tell me it again. V is equal to what?
F is equal to F.
Lambda.
If you forget this, I will cry. I'll go bald. I really don't want to go bald. I do not. Alia,
Look at
don't
our
forget
pictures.
this. V is equal to F lambda. Don't forget it. Oh, and I should mention this one time since while we at it. Everything in the EM spectrum travels at what speed?
Light speed.
By 10 rays.
Light speed.
3 times 10 to the 8 meters per
Right.
second.
Ooh, I loving the energy again tonight, boy. Everybody know their work. And so instead of seeing V, you might see C is equal to F lambda for things on the EM spectrum. You know why? Because I'm replacing the velocity with
Speed.
Light speed constant.
Light. Yeah, speed.
good. Nice, man. I think I'm mash up physics, boy. Oh, good. I love it. I love the energy I get in. So these are the main types of graph you need to be familiar with. A displacement distance time graph. What's in? A displacement distance graph and a displacement time graph. I'm merging there for a second. So you need to be familiar with a displacement distance graph and a displacement time graph. Did you guys know that these are the two types?
Yes, sir.
Yes, sir.
All right, let me do this fast. What type of graph is given above? What's that?
Displacement.
Displacement, distance.
Displacement.
Distance graph.
Oh,
Displacement. That was easy. Part B. And if you're confused, guys, just look at the axes, right? Displacement, distance graph. State its amplitude. What is the amplitude?
One.
One what? One what?
Meter.
1 meter.
Put the units, you can lose a mark. What is the wavelength?
2 meters.
Yeah, it's 2 meters, right? It's 2 meters. It's 2 meters. Right? With this graph, you don't have any successive crest or trough. So here's what I would tell. Here's what I would tell you, right? Another way you could think about wavelength is the length for one full oscillation. So you see, it starts at the resting position here. It goes up, it goes down, and it returns at its resting position. So what was the distance for one full oscillation?
2.
2 meters.
2 meters.
Now, if this graph did go on, this would be 2.5, and I would say 2.5 minus 0.5, which is
Still 2.
right. But I hope you understand, if you get a graph like this that doesn't have any successive crests or troughs, just look at the distance for one full oscillation. Question: would I consider this to be one full oscillation?
No, sir.
No.
No, sir.
sir.
Nah. All right, good. So the wavelength here is going to be what?
2 meters.
2 meters.
All right, cool. C. They want me to find if they're telling us the frequency. They're telling us the frequency is 50 hertz, right? And they want us to calculate the periodic time t. So here what formula do you guys know that has frequency and periodic time in it?
T is equal to 1 over F.
Well, you're
F
not
is
wrong,
equal
but
to 1 upon T.
the main one that we familiarize ourselves with is F is equal to 1 over T. You could rearrange this accordingly. So if I tell you that F is equal to 1 over T, and I know that the frequency is 50, I could plug that in. And here we're going to do, right? 50 is the same thing as 50 over what?
Over 1.
1.
I could then reciprocate both sides, and I would get 1 over 50 is equal to T.
Or
Yeah. So T is just 1 over 50. So
I got 0.02.
0.02, and we measure that in what?
Seconds.
Let me run it back again, right, chat? So here they give you frequency and the way to find periodic time. Now we know that frequency is 1 over periodic time. We know that. So we're going to plug in the frequency as 50. So I say 50 is equal to 1 over T. Now 50 is the exact same thing as 50 over 1. I want to find for T. So and if I reciprocate both sides, wouldn't that T 1 over T turn to T over 1, which is T?
Yes, sir.
Yes,
Yeah. And 1 over 50 is 0.02.
Yes.
Let me find the velocity now. Guys, is there any formula that you know that has velocity,
V is equal to F
frequency, and
lambda.
V is equal to F.
Equal to F lambda.
good. What is the frequency?
50 hertz.
50.
50.
What was the wavelength I found?
It was 2.
2
Should
So
be
the
meters.
velocity.
100.
V is equal to 100
And what are the units for velocity?
Meters per
meters per
second.
second.
Meters per second, or ms what?
10
To the minus
-1.
1.
Good. We already know this stuff. That's good.
Physics
That's
is bad,
good.
man.
Physics is the best. Physics is the best. You know what I mean? So, is there anybody confused? If you are, that's fine. Don't study everybody else. I will take one time and I'll explain it back to you. Yeah, that's something now. Things only gonna get harder.
So I feel we should do our next question, but not with the distance.
Right on, next question. Such a nice solution. Anyways, I just erase it anyways. It's fine. Who help more this question? Any volunteers?
So I don't mind.
Alright, so Nikolai, what kind of graph we got here?
Displacement distance graph.
I hate writing. I genuinely don't like writing. I don't understand how, like, 13-year-old me used to write 8-page essay and thing. I have no idea. I was like an English mafia boss back in the day. I can't imagine that now. B, the first one, says the amplitude. What's the amplitude, Nikolai?
1.5 meters.
Okay, if anybody confused by that, again, this 0 over here is the equilibrium. And it goes up to 1.5. Goes up to 1.5. So that's the maximum displacement. Similarly, from the rest, it goes down to 1.5. So that's the amplitude. Nikolai, wavelength now.
Wouldn't it be 5?
Wavelength will be 5. That's correct. That's correct. Guys, the scale here is a bit weird, but if this is 0 to 2, what do you suppose the middle would be?
1.
This is real funny, boy. It's a funny graph. 1, 2.
But where the line intersect between 2 and 4, that's not looking like 3.
Yeah, I think the graph looking a bit funny, but the graph looking a bit funny.
No.
Wait, let me just correct the graph quickly. So that 1, that's 3, it's 5, 7. Okay.
So
If you ask me, the wavelength looking like 3. I would say the wavelength looking like 3. That's the best approximation we could do. This is a picture of something and it's kind of wrinkled up. So I suppose that's why it's looking like this.
So how?
All right, let me explain. So we know that, the wavelength is the distance between two successive crests or troughs, right?
Yeah.
Yes, sir.
Okay, never mind. You're looking like 5. You're looking like 5. Like the scale here, it kind of
Yeah.
a bit weird, a bit weird. Because if I go to say that, then that would be a bit weird. Actually, you're looking like 5. Where's 6 minus 1?
5, sir.
5. 5.
And if you look at it here, what's that?
5.
5.
Yes.
Where
Yeah.
I get 3 from, boy? Where I get 3
I
from?
was confused.
I get 3 from. Yeah. So let me run through that again just to make sure everybody's on the same page.
So these
So
questions just come so easy.
yeah, these questions typically when CXC brings it, they put it like on a better scale. They're a lot better scale. So let me run it back again for anybody that might be confused. So the wavelength is the distance for one full oscillation. Can everybody see that this is one full oscillation here?
Yes, sir.
Yes, sir.
And well, this is another oscillation. So what is the distance for one full oscillation?
5.
5 meters.
Yeah, so 5 meters. And another way you could answer the question would have been from here to here. This looks like 1 here, and this looks like what here?
6.
6.
What's the distance between 1 and 6?
5.
5 meters.
5.
5.
I could also do it here. That looks like 4, I suppose. And this looks like 9. What's the difference between 4 and 9?
5.
5.
I need to get my glasses checked, chat. I need to get my glasses checked. So everybody okay with the 5?
Yes, sir.
Yes, sir.
Yes, sir.
Cool. Part C. We want to find the frequency, right? So Nikolai over here, they're telling us that the velocity is 100 meters per second. You seeing that?
Yes, sir.
And they want me to find frequency. Nikolai, what formula do you know have frequency and velocity in it?
V is equals to F lambda.
So what do you suppose you have to make the subject of the formula here?
F. Because
So
F is frequency.
we could probably plug in everything one time. What is the velocity?
Velocity is 100.
All right, what's the frequency?
F.
You don't know what that is. What's the wavelength?
5.
Why are they doing both sides?
Divide by 5 to cancel out the 5 to get F, and you'll have to do the same for the other side.
So F is equal to what? 100 over 5 is
That's 20, sir.
20 hertz. All right. Periodic time. So Nikolai, we want to find periodic time. Are there any formulas you know that you will just find the frequency, Nikolai? So frequency and periodic time. What formula that is?
That is F is equal to 1 over T.
And we want to find for T. So what do you think you ought to do?
Make T the subject by reciprocal of the F and the 1 over T. So it'll just be 1 over F is equal to T.
So T is going to be 1 over 20, and 1 over 20 is what?
That is 0.05.
Okay, is there anybody that's confused in class? Or like, I understand?
You understand?
One question.
Understand.
Okay, bet, nice.
Actually, sir,
Yeah, Nikolai?
do you have any questions that it have with time? Because I know it might have a shift in the.
Yep,
Oh,
I have a question right here for you. Nikolai, look away.
Avert your eyes, Nikolai.
I trust that you guys are very honest. All right, there we go. All right, so Nikolai, what kind of graph is this?
displacement time graph.
Everybody agree?
Yes, sir.
Yes,
So-
sir.
Because like displacement time. I don't know how else to say it.
Yes, sir.
Right. State the following. A. What's A, guys?
A is the amplitude, which is 0.06.
What? 0.06 what?
Meters.
Right, cool. What, Rami, what does capital T represent?
Time.
Period.
No, period.
Period.
Right? So, Nikolai, from this graph, we could actually read off the period immediately. Remember, the period is, what's period?
Is the amount of oscillations in 1 second.
Nah, you're talking about frequency.
Oh.
The
Is it
period is the
one
time it
oscillation?
takes. Nah,
For one
Nikolai.
oscillation.
Right, so Nikolai, the period is the time it takes for one full oscillation. So, Nikolai, what, if you notice, we have time here on this axis now. So, what's the time for one full oscillation?
0.02.
Good, 0.02. So, my answer here is just what?
0.02 seconds.
And what would the frequency be?
That would be 1 over T.
Which would be 1 over
1 over 0.02.
1 over 0.02 is
50.
50 what?
Hertz?
Yeah. Everybody getting these marks for sure, right?
Yes, sir. I
Yeah.
just need to
Se
clarify.
puede.
Yeah.
Yeah, Nikolai, talk to me.
I just need to clarify the relationship if the formulas would have been the same or if you would have had to change it up due to the graphs being different.
It's nothing that much different. The only difference, right? Let me ask you that question. Do you think we'd be able to find wavelength from this directly?
No,
No.
sir.
No,
No.
because this axis does not measure distance, right? So that's the only difference. So Nikolai, in question 4, they're telling us what V is. V is 343 meters per second, and they want us to find the wavelength. So you're seeing V and you're seeing F, a formula to use.
V is equals to F lambda.
Right. We're trying to find the wavelength. So I can plug in V one time. V is 343. Do I know what my frequency is?
Frequency. It was the 50.
Okay, is anybody confused as to what I did? If you are, just tell me. Just tell me.
Yes.
They were way to find wavelength, right? Here what? We just find for frequency. They give us velocity. And they were way to find for wavelength. Think about it. V, F, lambda. V is equal to F lambda. And so we know the velocity is 343. We know the frequency is 50. And we don't know what the wavelength is. So I plug in everything. And from here, I just have to make lambda the subject of the formula. So what should I do, Nikolai?
Divide by 50 to get your lambda by itself. And you'll have to divide the 50 by the 343.
So
And
what would you get when you plug it into your calculator?
I got 6.86.
6.86?
Yes, sir. Should we leave it as that?
Yeah, that's fine. And it'll be 6.86 what? Wait, you round it off to 2 decimal places, right?
No, that is the exact answer. I don't have any other numbers after that.
Well, this is good then. This is good. And here what? Wavelength, as the name suggests, length. What is the SI unit for length?
Meters.
Right. Guys, it's in the name. Wavelength. Length. SI unit for length is meters. And if you wanted further clarification, let me show you something, right? We know that lambda is equal to V all over F. Is that not true?
Yes, sir.
Stay with me, right? We measure velocity in meters per second, and frequency, we know frequency is just 1 over T. So that's really 1 over S. So stay with me, right?
Yes, sir.
This would turn to meter over S multiplied by S over 1. We're going to happen with the S's.
You'll cancel.
Cancel.
To leave it with what?
Meters.
Does.
Bam. Badness. Right? Badness, badness. If I ever forget the units, you can derive it like that quickly using a formula. Right? So I like about physics. So I feel like if this come again, correct?
Yes, sir. I just need to make sure because I know we have two different graphs now.
That's a problem. That's a good thing you made sure. So let's show you okay with this.
Yes, sir.
Yeah, sure.
Oh, and just something you should know, right? Wavelength and frequency are inversely proportional. You'll see what I mean when we look at the EM spectrum, and we have to like generally memorize wavelength and frequency. Yeah.
Okay.
And you're probably wondering why. And we know that V is equal to F lambda.
Yes, sir.
Okay,
Yeah.
if I were to make F the subject of the formula, I would have to divide both sides by what?
F.
Lambda.
Lambda.
Oh, lambda, my bad.
So F is equal to V over lambda. So let me ask you a question, right? If I want the frequency to be big, wavelength would have to be what?
Smaller.
Small, because it's in the denominator. It's in the denominator. So
Yeah.
I hope all you understand the inverse relationship there.
Yes,
If
sir.
you're confused, right, watch. It's literally F is equal to V over lambda. Hear what? If you're confused, right, let me give you an example. Let me just say the velocity remaining same at 10 ms minus 1. I'll tell you the wavelength is 50, and then I'll tell you the wavelength is 0.05. Let me check something out quickly. In this instance, what would you get for the frequency?
0.2.
Let's try it with the other wavelength. So that'll be 10 over 0.05.
That would be 200.
So question, guys. In which instance was my frequency bigger? Was it when I used the larger value for wavelength, or was it when I used a smaller value for wavelength?
Smaller.
Wavelength.
So as the wavelength decreases, what happens to the frequency?
It increases.
Increase the smallest value. Yeah.
Thank God, I'll remember this. Again, I should always try to understand something as opposed to just trying to memorize it and regurgitate it. So, remind me, if something has a really big frequency, the wavelength will be
smaller or very small.
No.
Are you understand this?
Yes.
And you can think about it visually as well. If a graph has a very large frequency and it will be like really compressed.
Yes, sir.
Yeah, be really, really compressed. So its wavelength will be small. That's how you can think about it intuitively. So guys, if something has a low wavelength or a short wavelength, it have a what frequency?
High frequency.
High frequency.
Good. Cool. All you understand that, right?
Yes, sir.
Yeah.
So I would say wavelength and frequency are what proportional? Are what?
Inversely proportional.
Inversely proportional.
And inversely proportional just means that if one goes up, the other one what?
One goes down.
Goes
That-
down.
Goes.
So you could
Okay.
use it as maths as well.
Yep.
The K over lambda.
Yep. And in this, watch. Like my Form 4 students, I would have showed them the mathematical relationship and whatnot. This is my Form 4 notes. Wavelength is directly proportional to 1 over f because it's an inversely proportional relationship. So I wouldn't say it's proportional to f, I'd say it's proportional to 1 over f. And wavelength would be equal to k over f. And in this instance, k is actually velocity.
Yes, sir.
Yeah. Physics is just a real life application of maths. Everything you learn in maths could be applied in physics. So let me look at types of waves. We would have touched on this briefly. So the two types of waves are transverse waves and what? Transverse waves and
Longitudinal.
good. Give me a quick example of longitudinal waves.
Sound.
Song.
Sound. Give me an example of a transverse wave.
Light.
Lights are. It don't just say light, right? Say like visible lights.
Visible light.
Because like what kind of light you talking about? Infrared light, visible light. I mean, all lights would
So all of
be
them transverse anyways.
all of them transverse anyways. I don't see that. But you should be specific. If you want to flex your knowledge, you could just say anything on the EM spectrum, right? Because everything on the EM spectrum is transverse. Remind me, everything on the EM spectrum travels at what speed?
Speed of light.
3 by 10 to the 8.
3 by 10 to the 8.
Gas. Big up for yourself. So let me explain something, right? In transverse waves, we are moving the slinky up and down, right? Because you're gonna be moving it up and down a little bit, no?
Yes, sir.
But
Yeah.
the direction of movement is going to be in this direction. So you are moving it up or down, and it's going in this direction. So what's the angle there? What's the angle?
Perpendicular. 90 degrees.
Perpendicular.
So that is why we say in transverse waves, the displacement of particles is perpendicular to the propagation of the wave. And if propagation of the wave confuses you, guys, it's just the direction in which the wave travels. That's what it is. So watch. You're displacing it up and down, and the direction in which it travels is left to right. So you can see perpendicular. That makes sense or not?
Yes, sir.
Yes, sir.
Yeah.
So that means you get a cross and a trout.
Yeah, it would give you
Transverse waves.
give you a crest and a trough. But we typically don't really use that for transverse waves. I mean, you've seen it here, but we typically use compressions and refractions when we're dealing with Oh wait, no, what I'm talking about? What I'm talking about? Yeah. I was talking about longitudinal waves there for a second. So for transverse waves, yes, there are crests and troughs. For longitudinal waves, there are compressions and refractions. Oh, you know about compressions and refractions, perchance?
Yes, sir.
Yes.
Okay.
No,
If you
No,
don't,
like
if
we're
No, sir.
you don't, that's fine. I'll show you some real life examples. But good. Somebody
Compression
said
is high pressure and rarefaction is low pressure.
correct.
yeah.
Wait, what a bad boy. What a bad boy. I have like a perfect example to explain that. Like I'm so prepared. So in a transverse wave, the displacement of particles is what to the propagation of the wave.
Perpendicular.
Perpendicular, right? And for transverse waves, you have crest and
Troughs.
good.
Trust.
And
Trust
all
and believe.
right, and all EM waves are transverse. Some examples of transverse waves as well, other than EM, is seismic S waves for earthquakes, geo people, and if you know what I'm talking about, right?
Yes, sir.
But EM just means electromagnetic. In case you didn't know,
So what about the P waves that is transverse too?
I'm not sure. Like I literally just look up an
Because I know
example
one
and I
of
see
them
yes
could pass
waves.
through like water and one of them can't.
I'm not sure. I can't tell you. I can't tell you specifically. I know.
Yeah, so the seismic S wave, that is what has caused the earthquake. But that is like underneath the oceanic crust, underwater.
We have some real bad people here, boy. There's some
Yeah,
smart
that
people
can
here,
do
boy.
on a spirit.
Yeah. I don't know about P waves though. I don't know about P waves. I don't know about S waves though. I don't know about P waves. Right? And if you want to see like a real life example, watch. You see how it moved up and down? And you see how it traveled in this direction? You see it?
Yes, sir.
Watch. Watch it. I'm gonna move it up and down, and the propagation is in this direction. So you can see the 90 degrees. Hope you're seeing it. And this is our S wave. Yeah, so long story short, somebody summarize transverse waves. What we know about transverse waves?
Transverse waves are waves that are moving in a perpendicular direction.
So you gotta say the displacement of particles is what? To the propagation.
Perpendicular to the propagation.
Perpendicular.
Right. And these would have, and give my example of transverse waves.
Visible light.
Visible light, infrared, and the
So
seismic.
everything in the what? Everything in the what spectrum?
EM spectrum.
EM spectrum.
EM spectrum.
What does EM stand for?
Electromagnetic.
Electromagnetic.
Good. All right. Alibad, big up for yourself. Cool. So this way you had to know, right? So remind me, wavelength and frequency are what to each other? What?
Inversely
Inversely
proportional.
proportional.
Inversely proportional to each
So
other.
let me explain something. And so when I hear me say this before, rich men in Vegas use expensive gadgets.
Yes,
Did I
sir.
hear me?
I heard you mention that yesterday.
Yeah.
Right. Now, we just remember this intuitively. I'm not sure if this is correct, right? But I just remember it like this. Radio waves. Don't they have to be broadcasted like via like a long distance?
Yes, sir.
Yes, sir.
So the way I just remember it is like if it has to be broadcasted a very long distance and still have strong signal, it would need to have a large wavelength.
Wavelength.
Yeah. It needs to have a large wavelength. So, and obviously, if radio waves have the largest wavelength, it would also have the
Lowest
what frequency?
frequency.
Shortest frequency.
Yeah.
Lowest
Largest
frequency.
frequency.
Nah. Remember what we discussed? Right? Wavelength and frequency are what?
Smallest
Inversely.
Inversely proportional.
Inversely proportional.
So if the wavelength goes up, the frequency what?
Goes down.
Goes
Exactly.
down.
Frequency goes down. So guys, all you had to do just remember our radio waves. I feel like it's really easy to remember. It has the largest wavelength, and if it has the largest wavelength, it would have the lowest frequency. Because they're inversely proportional.
Okay, thanks, sir.
No problem. Everybody understand now?
Yeah.
Yes, sir.
Yes, sir.
And conversely, gamma waves would have the what wavelength?
The
Smallest one.
Smallest wavelength.
Right? We typically
Smallest?
say shortest wavelength. But yeah,
Shortest or smallest?
It have the shortest wavelength and the what frequency?
Highest.
Highest.
Right. So take a screenshot if you need to. So rich, radio waves, men, microwaves, in infrared, Vegas, visible light, use ultraviolet, expensive X-rays, gadgets, gamma.
Excuse
And
me. I
you
only
have
know
the wavelengths here as well. Yeah, Nikolai, talk to me.
I only know it as the aliens with the X-ray guns.
Tell me the acronym you learned.
Raging Martians invading Venus using X-ray guns.
It's always using something.
Yes, sir.
So this was actually my first time hearing these acronyms. I didn't hear it like that.
I didn't hear it like that.
I don't know
Well,
if my school that I went to did
Me
differently,
too,
but
sir.
that's the first
Maybe
time
my
I
teachers just do not teach us this, I guess.
Well, I hope I remember it after today, right? Rich men in Vegas use expensive gadgets. Right?
Okay.
Yeah. I see Sammy raise a hand. Yes.
So the P waves are longitudinal and they can move through both solids and liquids, but the transverse S wave can't move through liquids.
Okay. So P waves could move through liquids and solids, you see?
Yeah, because they're longitudinal.
Okay, makes sense. Right. Generally speaking, longitudinal waves are mechanical waves. Like sound waves. So I suppose that makes sense.
Yeah.
It can move through like a physical medium.
Yes, sir. Baiju have a diagram on how the S wave does move and how the P wave does look.
I'm curious, what P wave does look like, boy? I'm curious. I forget these things, you know. I am long
It
past
would
my
just look
prime
like
in
the land, or
geography.
like, and then it would have like areas of compression and rarefaction. So like, they're just longitudinal. I'll send a
Okay,
picture in
okay.
the chat.
I have a picture right here.
Wouldn't it
Okay.
look the same way how the S wave does look? It's just it not moving as much as the S wave.
No, it's not the same way. One of them transverse and one longitudinal.
So like
Oh,
with
okay.
one of them, so like let me show you what happened in here, right? So the S waves, it moving it up and down, and the propagation is forward, right? So like S waves, propagation is up and down. Well, not saying propagation. You're like displacing the particles up and down, and the propagation is forward, right? But P waves is like it's like that. You understand what I mean? It's like back and forth and moving forward. So it's like, you know what I mean or not? So transverse is perpendicular and longitudinal is what?
Parallel.
I see my hands, right?
Okay,
Parallel.
so one is perpendicular and the other is parallel.
Correct. Yeah. You seeing it or not? Like okay. Like watch. Like it's parallel. It's
Yeah.
parallel. Alright. So I have a screenshot of this.
Yes. Sir.
Okay, cool. Awesome source. And all EM waves travel at the speed of light. We know this. Instead of writing V for speed of light, what do we typically write?
C.
Typically write C. Cool. Alright, longitudinal waves now. In longitudinal waves, the displacement of particles is parallel to the propagation of the wave. Imagine a speaker, right? And that speaker does move in and out. So it is like vibrating particles, like back and forth.
Yeah. Oh, yes.
And the propagation of the wave is in that direction as well. So it's parallel. And I think, watch, when you look at the general symbol for a speaker, these waves look what? These lines look what? Well, I can't really call them lines. These curves look what to each other?
Parallel.
Parallel. It real hard to forget this one. Longitudinal waves, the displacement of particles is parallel to the propagation of the wave. Good. So please remember
So
that.
you went over infrared already.
No, I didn't go through infrared as yet. But like I did go through everything here. Like briefly.
Alright.
Infrared is just heat energy, guys. Like heat is carried via infrared waves. So like the sun, yesterday when we did thermal physics, I would have explained that the sun does emit short wavelength IR waves. And that's actually reach Earth. And that's actually passed through glass very easily. And it's caused a greenhouse effect. Watch it live after this. The previous live is real good. Right, so sound waves are mechanical waves. We talked about this. So for sound waves to propagate, you need a what? Remind me fast. You need a what?
A
A
medium.
medium.
Yeah, medium, right? Cool. What does amplitude correspond to? Loudness.
Loudness.
And frequency is?
Pitch.
Right, they will ask you about this, right? So high pitch implies high frequency.
Low
If
pitch is low frequency.
Right. Yeah. Right? I like the energy I get in, so like we might go a little longer than typical. Yeah, maybe like 1 o'clock or something. So can you guys?
So mind you, I come in your class late and I'm still picking up.
Yeah, that's the thing about
It
math
wasn't
vibes. No
my fault
matter.
though. I was in the other class.
That's okay. No matter where you come, you got benefit somehow. So you can see that the speaker is moving in and out. So I have a perfect representation of it here. Big up ChatGPT. So when the speaker moves out, what exactly is happening there? Well, it pushes the air molecules together. Let me explain. So guys, imagine you have some air particles over here, right? When the speaker moves out, wouldn't it exert a force on these particles here?
Yes.
And that would push against the other particles in the air, therefore causing a what? If it presses against, cause a what? A compression or a rarefaction?
Pressure.
Pressure.
a compression, right? So when the speaker moves out, the force from the speaker, it actually pushes the particles against other particles, and it causes compression. And when the speaker moves in, is the opposite, right? It pulls air from, like, okay, here, I'm gonna explain this. So you would have some particles closer to the speaker, and when the speaker moves in, it's going to pull the particles. And there's going to be like, it's like essentially the opposite of compression. In compression, you're bringing particles closer together, but in rarefaction, you're kind of pulling them apart. That makes sense?
Yes,
Yes.
Yes, sir.
Kinda.
Kinda. Okay, let me see if I could get a better example, right? So I have some air particles here. When the speaker moves outwards, it's going to push these air particles together. If it pushes the air particles together, because I hope you understand why, like the speaker literally push outwards, like, you're going to push the air particles against the other air particles there in the air, and that would cause a what? Since I like pushing it together, that'll cause a what?
Compression. Oh, I understand.
Cause a compression, right? And the particles closer to the speaker, like when the speaker moves in, it's gonna be pushed outwards like that. And since it's pulling them apart, that's the opposite of a compression, which is called a rarefaction. So all you understand that on that?
Yes, sir.
Yes, sir.
Yeah, sure.
Okay, nice. Physics in school is be taught so black and white, eh? A lot of students don't realize a lot of these things is seen day-to-day life. It's very cool. Physics is very, very cool. Physics is peak. So watch this, guys. Quickly tell me, what was this? This is a transverse or a longitudinal wave?
Transverse.
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 If you guys recall, transverse waves have crests and
Troughs.
Troughs.
what is this?
Crest.
What is this?
Trough.
Good. And as you guys can see, the displacement of particles is up and down, and the propagation is left to right. So that'll be 90 degrees. This is clearly transverse in nature. And over here, this is longitudinal waves, because again, we just talked about this. When the speaker pushes out, it's going to cause compressions. When it pulls in, it's going to cause rarefactions. So you have areas of high density here. These are the compressions. Are you with me?
Yes,
Yeah. Yes, sir.
Yes, sir.
And these areas here, where the speaker moves in, it pulls the air molecules away from each other, and that does the opposite of compressing, which is a rarefaction. And this would be the equivalent to the wavelength for a longitudinal wave. So I hope you guys understand that. Right. Are you okay or not?
One question,
Yes,
sir.
sir.
Yes, sir.
Would they
Talk
ask
to
any
me.
questions on the definition of the compression and refraction?
They could.
So I'll just say how the molecules and everything, how the particles are aligned.
Yeah, you could say this. So, when the speaker, you could like give an example with a speaker, and it could be like it pushes air molecules together, pressure increases, molecules get closer, compression. Speaker moves in, it pulls away from the air, pressure decreases, molecules spread apart, rarefaction forms. You could tell them that. So a
Okay.
compression is just simply where, imagine a speaker, it pushes the molecules together, compression. Speaker moves in, rarefaction. Not hard to explain. So transverse is here and longitudinal is here. So transverse, we know it has crests and troughs. They will ask you about the differences, eh? They could do that. So you need to know the differences here. So transverse has crests and troughs. Displacement of particles is perpendicular to propagation of wave. An example, anything from the EM spectrum. Longitudinal, compression and refractions. The displacement of particles is parallel to the propagation of the wave. And examples is sound waves and some seismic waves. Like you guys would have told me, the what waves? S or the P?
S.
No, not yes. If it's longitudinal, it's a P.
Oh. Okay.
And if it's the transverse, it's the S. And we talked about this? Sammy, did you talk about this? Look at did I
Yeah.
remove it? I think I removed it, but it was here on the screen at some point.
Okay.
Yeah.
Oh.
So a seismic S wave is a transverse wave in nature. And a seismic P wave is a longitudinal wave in nature. So when I send this document, you will have everything right there, but you need to remember this for tomorrow. Like they could ask you differences. So quick run through. Transverse. Transverse has what? What does that transverse have?
Press and trust.
Chris
Press and trust.
Press on.
Right. Longitudinal has what?
Compression.
Compression and reflectance.
Refraction.
Okay, good. Transverse. The propagation is okay. The displacement of particles and the propagation is what each other.
Perpendicular.
Perpendicular.
Perpendicular to the purpose.
And longitudinal is what?
Parallel.
Parallel.
Parallel. Bam. Badness. Good.
Could you also talk about the speed and the how it travels in a vacuum and how it doesn't?
You could talk about that. You could say transverse waves. They travel in a vacuum. Longitudinal waves, specifically sound wave, is a mechanical wave and cannot transfer. I mean, it cannot be propagated in a vacuum. You could talk about that as well.
Okay.
So that means they need a medium.
Yeah. Like, okay, longitudinal. Okay, sound specifically, sound needs a medium. The seismic waves as well. These require a medium to be propagated. And okay, if I have like a loud DJ truck passing by, right? Wouldn't you feel like the wall's vibrating? Like if you put your ears against the wall, wouldn't you like hear the sound wave?
Yeah.
Yes, sir.
Yeah, so like
Those things be shaking, sir.
exactly, and
Sometimes you
clear.
feel the thing beating like your heart. You feel the
Exactly.
thing like it.
It's clearly a mechanical wave and
So
requires
talk
displacement.
about them cars and them that is passed. Talk about them cars and them that is passed with this long bass in the music. And it's
Boy,
be like, what?
Ale should see my subwoofer, boy. Ale should see my subwoofer. I have like
Nice
a
work,
fix,
Ainaka.
like I fix it up my car. When I fix up my car, I got put speaker and thing in it.
So I have a question, right?
Yeah.
Like let's say I'm passing the going up the road, something like that. The sound or the pitch will change most of the time.
Yeah.
Like
That's
if
like
they're
the
playing a
red.
song loud.
Yeah. That's the red shift effect. It's red shift effects. Like
So
you
when
would
you fix up your car and you put your speakers, you have to pick up me and Nikolai to watch Avengers Doomsday.
Of course. Yeah, I will do that. I can't really don't worry.
The kind of truck that's be passing. Well, for carnival, that's be behind the masqueraders and that truck does play music loud as well too.
That would be how my car will sound. That's how my car will sound. Yeah, boy. So my car will sound. I'll play some Suicide Boys, some Puya, some like
Suicide Boys,
some Scarlord,
Don't forget Sabrina Carpenter and Olivia.
Don't forget
nah,
about Drake new album.
Pink or Iceman.
Nah, not
That's
Drake.
Iceman, yes.
I will play some. I'll play some.
Right?
You know what from?
Weekend, The Hills.
Yeah. I'll play Weekend. Prisoner is a good song from the Weekend. What else I'll play, boy?
Don't forget Blinding Lights.
Yeah.
That's a nice song too.
Oh yeah, I
Lana.
overlove Lana Del Rey. A real blast from Lana Del Rey. I see CS.
Yeah.
Is it CCS? I love CS.
Respect you so much.
Snowball.
So you know he blasted Sophia the first.
And I will play Pink Panthers like yeah boy, Pink Panthers making some bangers these days, boy.
Boys a liar.
With Zara and
Boys a
yeah,
Please
and
don't
with
hate on me, y'all. I
Spice.
could listen to some Billie Eilish as well.
Yeah, that's
Yes!
all for them. Yeah, boy, big up Billie Eilish. But I like kind of music that people don't know about really. Like I love Suicide Boys, boy. I love
I
Suicide.
love Suicide Boys.
Yeah, like
What is Suicide Boys?
like Napoleon, like it have this one. They just always have like these long names to
So
their
this
songs.
isn't the Green Day?
Long
This isn't the Green
names that
Day?
you can't pronounce, so you
I
just
used
have
to
to
listen to Green Day.
Green Day
I
is
thought you
tough.
yeah, boy. You know what? After the end of the session, I'll sing a Green Day song for you. I'll open my key and sing. I'll open my key and sing. I'll go back
Which
to
one
me
you
emo
guys
phase.
think, Sid?
Eh?
Sing Basket Case.
21.
21 Pilots real good too. Yeah. The new album's really good. The Breach and whatnot. My girlfriend loves Mrs. Matt Vibes love 21 Pilots. Yeah.
Very
She loves
Hey,
21
them
Pilots.
sound good too, you know. Them sound good. Oh,
Yeah, boy.
all right.
But we're taking a long detour. Let me get back into it. Right? So now we're gonna look at wave phenomena. Quickly before we look at the answers, what are some wave phenomena you guys know about?
Diffraction,
Refraction. What's refraction, boy?
the
Refraction.
bending of.
Okay.
Okay,
Let me give a little quick example, right? So refraction, what is that? You
The
just
bending
run
of
this.
light.
So isn't that the spread of a
bending
wave?
of.
No, you're talking about diffraction.
It's
So
like bending of wave.
here what tell you. Do we run the same speed in air versus the sea?
Nah.
Nah.
No.
Different.
Do you think light will travel at the same velocity in air versus
Oh,
water?
nah.
No, it wouldn't.
No. So anytime light goes into a different medium, the
So got the
velocity,
bend.
and so it would bend accordingly.
Yeah.
Yeah. So
So what
that's
happened to the velocity?
the velocity would change because okay, think about it logically. Where would you run faster? In air or in the ocean?
Eh,
Yeah.
Okay, so where do you think light would travel faster? In air or in a denser medium?
Yeah.
Yeah.
Yeah, exactly. So the denser the medium, the slower light travels in it.
Okay.
And that would cause the light rays to bend. Right, so reflection, we know about this. All waves can bounce off a surface. So these are the wave phenomena of waves, right? Waves. So reflection, all waves can bounce off a surface. Refraction, all waves bend or change direction when entering another medium. We know why, because the velocity changes. Diffraction, all waves can curve or bend through narrow openings and edges, but the opening on the edges, the wavelength must be smaller. Like okay, the opening or the slit must be smaller than the wavelength of the wave for diffraction to happen. And the teacher told you that for diffraction to happen, the size of the slit, the wavelength, it must be like smaller than the wavelength of the wave.
Yes, sir.
We did a lab with a refraction and reflection.
Yeah, we did a lab with that, with like a kind of glass bar, and we had to put a pin on top.
Perspex block. I know what you're talking about. Actually, I can have it right here. Give me a second. I know what you're talking about. We're gonna do all of this today, you know. All real work today, you know. I don't think I'll realize how much work we're gonna do
For
today.
sure, I remember
Yeah,
that
keep
lab.
talking about this. Talking about this.
Yeah, he put a little small nail on top of the block, and then we have to go at eye level and look to see if we see it reflected.
Yep, that is it. So reflection, refraction, diffraction, interference. It's okay. Interference, all waves can fuse, increasing or decreasing their amplitude. Again, car audio men. You ever hear somebody hook up a speaker out of phase and like when you're walking past it, it's sounding real bad? Like some parts is loud, some parts is low, like the bass sounding kind of bad.
Yeah.
Yeah. When you wire speakers out of phase, when one speaker moves out, the other one moves in, and it kind of cancels off the sound waves. So you have some regions of constructive interference and destructive. As the name suggests, constructive is when the amplitudes combine. Destructive is when what?
Opposite combined.
Cancel.
Cancel.
When they cancel out each other.
When they cancel off each other. Good, when they cancel off each other. And dispersion, we don't really see dispersion much, but you guys should know about dispersion. You ever see that Pink Floyd album cover where it's like a triangle and like rainbow? I'm talking about.
Yeah.
Yes.
Yeah. So that is dispersion. So
So,
light can split into different.
hypothetically,
Wait, sir?
dispersion could come.
Yeah, it could come, but that wouldn't be bad. It can come in the form of a question like this. Like you see it in the paper one, right? You see it in the paper one.
Oh yes, it had a question for my year that they asked which one is the correct thing.
Yeah. Typically look like this. And you have to select. That's dispersion there. Right? And light would disperse in the order Roy G. Biv. Okay, cool. So let me explain the phenomena quickly. Right. So wide gap, small diffraction effect. So can you see that the wave kind of bends?
Yep.
Okay, that's a small diffraction effect. If we had a narrower gap, well, it doesn't look that narrow, right? It's a very poor diagram. But like if the gap is narrower, the waves are going to spread out a lot more. So this is called diffraction. Right? What do you guys think this is?
Reflection.
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 Right. Because the angle of incidence is equal to the angle of
Reflection.
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 When we're dealing with reflection, we typically don't say angular refraction, we say angular reflection. Even though technically it is. Okay, what do you guys suppose this would be? So you're seeing the straw bending.
Refraction.
Refraction.
This
So
refraction.
I know how to explain this scientifically. In water, right? If you look at water, the reflection will fool you to think that the straw, then when it literally standing up in the water, is the reflection of the straw you're actually seeing.
That reminds me of this one question we had looked at with the shark. Until you're not talking about Bruce the shark. Until you're not talking about
Yes,
the
sir.
Nemo thing. Yeah.
Shark.
Okay, let
The
me continue.
water is to fool you and think the straw bend, but it not bend. It
All
literally
right.
stands straight.
I want to talk, but we have real work to do. We have real work to do. So, guys, the first one was an example of diffraction. This is reflection. This is refraction. This is dispersion, and this is interference. Are you understand it?
Yes, sir.
Yes.
Yes, sir.
Okay, cool. So I have constructive interference here. As you can see, both of the waves are in phase with each other. And what do I mean? It means that their crests line up and their troughs line up. Are you seeing that or no?
Yes,
sir.
Yes, sir.
And so when they overlap,
Yes, sir.
watch, the amplitude here was 2 and 2, but since the crests and troughs were in phase, it went up to what?
4.
4.
And this went down to what?
4.
Negative 4.
Negative 4.
Mm.
So that's constructive interference. It occurs when 2 or more waves overlap and their amplitudes add together because they're in phase. Let's look at destructive interference now. So guys, does the crest line up with the crest for the other one?
No, sir.
No, sir.
No, sir.
No. These are trough over here and these are crests. Opposites, right?
Yes, sir.
Opposites would cancel off, would it not? So with destructive interference, you would see a straight line. Because it would cancel off what? What is 2 plus minus 2?
0.
What is minus 2 plus 2?
0.
Right, 0. So destructive interference happens when you have 2 or more waves that are out of phase. The crests or the troughs do not align. They could ask you, when does maximum destructive interference occur? And you would have to say it occurs when a wave has a phase difference of 180 degrees, meaning that it's out of phase by half. Let me explain. So over here, this is a full oscillation, right?
Yes, sir.
Yes, sir.
People are doing odd maths, right? Sorry, regular maths people. Experts are doing odd maths. The sine wave goes from 0 to how much degrees?
Pi over 2.
Pi.
I say degrees, so 360 degrees.
Yeah,
Right?
360.
Oh, no, it's 2 pi then.
Okay, so 0, 180, 360. Okay, and this over here, it was shifted by how much degrees? Okay, so let me show you what I mean, right? Let me show you what I mean. Let me show you what I mean. Quickly. Watch. If I shift it 180 degrees, watch. That is what's gonna look like now. If I shift it 180 degrees.
Yes,
If I
sir.
shift it 180 degrees. So that's what happened in there. And so the maximum destructive interference would occur when the waves have a phase difference of 180 degrees, meaning that they would completely cancel off. Because watch, if you had an example like this, it doesn't completely cancel off, like over here is 0 and over here is a little less than minus 2. It wouldn't completely cancel off. But when it's like this, can you see that it would completely cancel off with the 2 and the minus 2, for instance?
Yes, sir.
Yes.
Yeah, so you need to know that you need to know that maximum destructive interference happens when the waves have a phase difference of 180. and the crest of one would align with the trough of the other, which is what we saw there. See, I don't know this. So remind me, maximum destructive interference happen when's what? The waves have a
Out of it.
Of 180 degrees.
right, the outer phase by 180 degrees. So they have a phase difference of 180 degrees. Good. So this was the question in 2025. They asked us to say the wavelength. Anybody can tell me what's the wavelength fast?
The distance between two successive crests or troughs.
And how do
Or
we
what?
measure wavelength in?
Wavelength?
Lambda.
Meter.
Meter. Meter. If you wanted to get us say meters as well, like you could have say the units of it. So wavelength is the length of one full oscillation, but like Virginia said, they prefer to see the length between two successive crests or troughs. Easy to marks. Amplitude is just the maximum displacement from its equilibrium position. I like to believe they're given 2 marks for this. I like to believe that.
I don't like it too much, sir.
Well, yeah, that's real
So
easy
it's
marks.
CSEC we're talking about, you know, the
And this
wicked
is
like that.
2025 May June. No, but like you should be smiling. Isn't this like a easy 2 marks?
Yep.
Yeah. Definitions?
Yeah, diffraction. Right, so diffraction. This is the curving or bending of waves through narrow opening or edges. The smaller the opening or edge, the greater the effect of diffraction. So somebody tell me, where would I have more diffraction? In scenario 1 or scenario 2?
Scenario 1.
Scenario 1.
Scenario 1.
Scenario 1.
Because the slit is much more narrower.
Yes,
Yeah.
sir.
Yeah,
Is that the flashlight, sir? Or no?
the flashlight.
Like where the light passing through the like a small spacing.
Okay, I think I know what you mean. Like you're talking about, I need the bulb would be over here.
Yes, sir.
I wouldn't necessarily say that is it, but diffraction will have a slight effect there. The
So
main
you
thing
know,
is that the main thing over here is the fact that you have a reflective surface over here, and it's in a conical shape. So it would cause it to spread out. But diffraction does have a small effect here. Yeah, somebody was gonna say something.
well, so I was not gonna say what he said with the flashlight. If you think about it, like for like those plays when they put the lens over, the opening on the lens is really, really small, but when you actually watch the light, it is actually be pretty big.
Yeah,
Yes, sir. What you're
that's
saying is true.
that could be an example of diffraction, yeah, but I wouldn't necessarily say that. You know why I want you know why I'm saying that? Okay, for diffraction to happen, like truly happen, the slit needs to be smaller than the wavelength of the wave. And a lot of these waves are okay, a lot of these waves have a really, really small wavelength. So you need like an extremely narrow slit for it to happen. And let me show you what I'm talking about. Let me show you an instance where you would see diffraction. Okay, let's see how the wavelength here is 6.86 meters for this wave.
Let's go.
Yes, sir.
Yeah. And there are a lot of things smaller than 6.86 meters.
Yep.
Yes, sir.
Yeah, so like if I had if this wave had to pass through a narrow slit, it would rail diffract. It rail diffract. Seeing that this is the wavelength. You know what I mean?
So
So
something like a pinhole, like I don't know what it is, but like with the pinhole, like how that's so small, basically.
yeah, but like you have to make sure that the size of the opening
It's smaller than.
smaller than the wavelength of the wave.
Okay.
The diffractions
Okay,
are.
so
You can learn about that in Unit 1 physics. Unit 1 physics is vibes. So somebody said diffraction is not the spreading out of waves. It is. That's what diffraction is. It is spreading out of waves after passing through a very narrow slit. As you could have seen here. It is spreading out of waves. Cool. So we're okay with the phenomena. Cool. Let's look at this quickly. Two loudspeakers placed about 1 meter apart are simultaneously playing the same song. Sophia walks along the line from A to B as shown in figure 3. Now they're saying 2 loudspeakers and the part taken by Sophia walking by. Describe what Sophia hears while walking along the line from A to B. So does everybody understand that speaker 1 would produce its sound waves like so?
Yes, sir.
Yes.
And then speaker 2 would produce its sound waves as well.
Yes.
Aren't you seeing they are aligning at some points?
Yeah.
Yes, sir.
Yes, sir.
If both of them align, then that would be what kind of interference? Constructive or destructive?
Constructive.
Constructive.
And everywhere else would be what?
Destructive.
Destructive.
Good.
Because the reason why the first part is constructive is because it's connecting the dots in the middle.
Well, the real reason is because the waves are meeting in phase with each other. That's the real reason.
Okay.
So like one crest hitting another crest. And so it's directly in phase. If you guys recall, and for something to be in phase, the crest of one and the crest with the other one need to line up, or the trough with one and the trough with the other one needs to line up.
Yes, sir.
Yeah. Right. So describe what Sophia hears while walking along the line from A to B. Sophia would hear alternating loudness because in some parts she's going to experience constructive interference, and some parts she's going to experience what?
Destructive.
Cool. Explain your answer in B part 1. I have it here, and I'm going to write all of this. The 2 loudspeakers produce sound waves of the same frequency and amplitude. You had to say that. And the waves overlap and interfere with each other. At some points, the waves arrive in phase, and if they're arriving in phase, they would produce constructive interference, and the amplitudes would add, right? At other points, the waves arrive out of phase, and if it arriving out of phase, they would subtract, and that would be destructive interference, resulting in softer sound, or in some instances, silence. Could anybody tell me in what instance you would have silence?
Complete destruction.
Okay, when does complete destructive interference happen?
When you're away from the waves, like you're not.
When they
You're like
have
you're behind.
No, no, you had to tell me the specific phase difference. When they have a phase difference, or what?
180 degrees.
180 degrees.
180.
Right. Let me show you a quick example, Nikolai. Okay. Wait, it's probably a bad example. Okay, now we're gonna make sense. Nikolai, let me show you what I just do, right? So Nikolai, if I take this wave and I pull it back 180 degrees, I'm not sure if you're seeing what I'm seeing, but Nikolai, when you have a trough over here, you have a crest here. So what happen here, Nikolai?
Cancel.
It will cancel off. This is a trough over here and there's a crest. It go what?
Cancel as well.
Cancel. And that happens when you have what? Again, that happens when you have a phase difference of
180.
180 degrees. Yeah.
So will we say that's a destructive interference as well? Or
That
no?
is complete destructive interference. Complete.
Okay.
And complete destructive interference happens when the waves are 180 degrees out of phase. 180 degrees out of phase. That's when the sound waves will completely cancel off. Okay?
Yes, sir.
Good. Oh, I was so surprised when I saw this in the 2025 paper. I was so surprised. I wasn't expecting this. Explain the concept of wave-particle duality of light, making use of the contributions of Newton and Young. So guys, all the way to really say is Young's double-slit experiment, Let me give all you a run through. I'll run through on it.
Yes, sir. If you don't mind me asking, you could go over that because I don't remember my teacher telling me anything about that.
That's okay. So check it out, right? Let me just say you have a light source. You have a light source, right?
Yes, sir.
The light source will produce a wave, produce some waves, right? Let me check something real quick. Yeah. It will produce waves like this. So you have some waves here. I'm going to have a slit here. After the wave here, actually, let me use sound here. I'll use sound instead. I'm gonna use sound. But it could work with light. It could work with light. But I feel like we just did sound, so that'll be an easy one to explain. So, okay, when the sound waves passing through this narrow slit, what would happen after?
It'll expand.
Will expand, yeah.
It'll spread out.
Well, it's spread out, right?
Yeah.
Okay. And the experiment is classed Young double slit experiment. You have two slits. So after this, you're gonna have right. That's one over there. But you'll have another slit. So aren't there some instances where the waves, where the align? Let me show
Yes.
you what I'm like right here, here, here. Are you seeing what I'm talking about or not?
Yes, sir.
Yes, sir.
And everywhere else will be what?
Destructive.
Yeah, destructive.
Right. Okay, are using sound here. If we're using sound, then the areas of constructive interference would be softer or louder.
Louder.
And the areas of destructive would be what?
Softer.
Softer.
Okay, let's just say I was using light instead, right? I was using light waves. Because light is a type of wave as well. If I'm using visible light here, the areas where they are in phase would produce bright fringes or dark fringes.
Bright fringes.
Right.
And Nikolai, the bright fringes would be areas like where it's really bright, right? And dark fringes would be area of darkness. So Nikolai, you understand that if we did use a light source instead of sound, you would have bright areas where the waves are in phase, and you'd have dark areas where the waves are what? Where the waves are what, Nikolai?
Out of phase.
Yeah. And this is Young's double slit experiment right here. Right. Cool.
So,
Yeah.
could you like describe the diffraction of the waves, kind of like concentration?
So that again?
Like, could you describe the diffraction, whatever, of the waves and the double slit motion as like concentration?
Concentration.
Yeah, to like a certain point. Yeah.
Well, the concentration of constructive would result in bright fringes, and the concentration of, however, I don't think you're using with concentration there, you know. Yeah, I think I would use it with concentration, but like this is Young's double slit experiment here, guys. But I don't think I would use concentration.
I hope you don't mind. I took a screenshot of it.
No problem. Let me know if you guys understand Young's double slit experiments. So like I'll go over it again, right? We just use sound, but instead let's use light, because light is also a wave. Light is a transverse wave. We just learned that. Well, I hope you guys should have learned it before, but that's fine if you didn't. As you can see, we have a wavelength here. And if you notice, my slit is what? Bigger than the wavelength or smaller than the wavelength?
Smaller than.
Smaller. If it's smaller, it's going to result in diffraction. So I have diffraction happening here. And when it encounters the two other slits, it's going to diffract again. Aren't you seeing that there are regions where they intersect?
Yes, sir.
Yes, sir.
Again, if we're dealing with light, that would be areas of bright areas, and we refer to that as bright fringes. So everywhere they intersect is going to be bright fringes, and everywhere they don't intersect, that would imply what type of interference?
Destructive.
Destructive.
So can I get that screenshot? Yes.
Yeah, no problem. Take a screenshot of this. So the
So that
interference.
you explained it with the diagram, it all making sense now.
Okay, good. So anytime the waves intersect, that would produce bright fringes because those were areas of what type of interference? If they intersect, areas of what type of interference?
Constructive interference.
And if they didn't intersect, that's areas of what type of interference?
Destructive.
Destructive interference.
Destructive.
All right, cool. We're gonna move on. All right. I tell you, Israel peace, Israel peace. Here. I do a question here quickly.
So I remember this question. It was in a test, and I only thought we were supposed to do one only, not knowing it's two answers.
And nah, boy. Oh, and this is a nice question here. We do this one too.
So at that time, I wasn't good in physics.
But you get in there, you get in there.
Yes, sir.
Don't feel
All right.
shame, boy. Me neither. But again there, again there.
All right, so I need a volunteer to speed through this one fast. Because we are real working on. I find we doing a lot of work. It's 9:32 already. And we're going till like 1. So we have time.
Yeah.
I need a volunteer.
So if nobody going, I go.
All right, no problem. Nikolai, give it a read.
Humans can see electromagnetic radiation only between the wavelengths of about 4 times 10 to the power negative 7 meters and 7 times 10 to the power negative 7 meters. This is called the visible part of the spectrum. A rattlesnake can detect EM radiation of frequency 3.5 times 10 to the power 14 Hertz, and a honeybee can detect EM radiation of 1 times 10 to the power 15 Hertz. Calculate the wavelengths corresponding to each frequency.
Remind me, guys, wavelength and frequency have a what type of relationship?
Inversely
Indirect.
Inversely
Inverse proportional.
Inversely
Big up
proportional.
for yourself. So, okay, which one has a bigger frequency? The rattlesnake or the honeybee?
The rattlesnake.
Rattlesnake.
You
The
sure?
rattlesnake?
The
No,
honeybee.
I see the honeybee
No,
is
the
10 to
honeybee,
the
the
power
honeybee.
15.
Oh, the honeybee, the honeybee, the honeybee.
10
Sorry,
to the
sorry.
10 to the power 15 is bigger than 10 to the power 14. So
It's the honeybee.
honeybee, right? So which wavelength do you think is going to be shorter?
The
The honeybee.
Honeybee.
Honeybee, because it's an inversely proportional relationship. Good. Let me calculate the rattlesnake first now. So Nikolai, right off the bat, you see them talking about frequency wavelength. What formula I think we should use here?
V is equals to F lambda.
Now let me ask you guys a question, right? They didn't mention it in the question, but what do we know the speed here? What do we know the velocity is? What is the velocity?
3 by 10 to the power of 8. By 8.
Right, because all waves in the EM spectrum travel at what speed?
Light speed.
speed of
Light
light.
speed.
Light speed.
So did they give that form? Did they give that calculation for the speed of light in the question or no?
They did. But a lot of people wouldn't even know where to use that. I know that.
Yeah, that is so
for a
true.
fact. Right, so all waves in EM spectrum travel at the speed of light. And we know that the speed of light is 3 by 10 to the power 8 meters per second. Right, so guys, if you see a question like this, you know that the velocity is going to be what? If you see an EM
Light.
radiation, what?
Speed of light.
Speed of light. Good. Okay, so V is equal to F lambda, not a problem. We know that V is going to be what?
C. You replacing V with C.
Now hear what, right? Hear what, Ollie? In both of the instances, I want to find wavelength. So what I should probably do is, I should probably find a formula for wavelength one time and done, if you know what I mean.
Yes, sir.
Yes, sir.
So if V is equal to F lambda, how would I find for lambda?
V
Divide.
lambda the subject of the formula. So it'll just be V is equals no, lambda is equals to V over F.
V over F. Cool. Let me do the rattlesnake first, huh? Rattle. Don't forget, if all stay to the end, I'm going to sing a Green Day song, boy, with the emo hairstyle and all that.
Really?
Yeah.
Okay, sir.
Basket case. Say singing basket case.
I walked up, no, let me not pull out the bars before, the end.
Nah,
Big
nah, sir.
event.
Let
Yeah.
me cook first.
Right? With the rattlesnake, well, all of them see EM radiation, so that'll be 3 by 10 to the power 8. And the frequency here is
3.5
3.5.
times 10 to the power 14. I got 8.57 times 10 to the power -7.
What you get?
I got 8.57 times 10 to the power -7.
And obviously that'll be in what units? Because we do wavelength. Meters, right? Meters. Cool. Let's look at.
So you sure that's the answer?
Well, I trust in Nikolai.
Well, I divided.
Trust him. Let me verify. Let me verify it. So the way to find wavelengths, which is v over f, right? So the velocity is 3 by 10 to the power 8, 3.5 by 10 to the power 14.
So you're sending this document tonight?
Yeah. This is correct. I'll make you see that. Like how small it is.
Yes, I get that too.
Somebody was like, "Yeah, sure you're right." Did you say that because like it was concerned about how small the length was? Remember, like we dealing with.
No, so my calculator just playing now.
Oh, you have a sharp end.
Yeah.
So with the sharp, you're not going to get the correct answer unless you like put the brackets and things. So that's probably why.
You find so like I could do this. I think actually let me try. Let me try to do it without brackets and see what happens.
So he almost catch me there because I was going to doubt myself. I was like, what? I get this wrong already?
Let me look again. Oh, you're gonna get to the power 21.
Yeah, my bad, boy, Nikolai. My bad.
Because when you put divided, it's gonna do 10 to the power 8 divided by 3.5 first, then multiply that by 3, multiply that by 10 to the power 14. Yeah. If
So
you
I
do
get
it,
the answer and it's just in plenty zeros, so I have to convert it to the.
So until us have to subtract the powers for you to
you have a
get
calculator.
the.
You have a calculator for a reason there, boy, Renisha. Easy
So I
calculator.
know that. I'm just saying you're supposed to subtract the powers for you to get the.
Renisha, like hard what?
Yeah, boy.
Well,
Yeah.
I am a science student for a reason. Hello, to experiment.
Yeah. But
So for the honeybee, I got 3 times 10 to the power -7.
all right, cool. So we have rattle there for the honeybee. Right, for the bee. It's going to be 1 by. I don't know if I realize, but all of these questions easy, All of these questions easy. What's saying, buddy?
Wait, no, wrong. Wait. Yeah.
My bad. But all of these questions, I find these questions straightforward. Most of
Yes,
them.
sir. Yeah, I say not now, but before, no.
You know your formulas and thing in a gear. Mechanics is really easy too. The hardest part of physics to understand, I feel, for students is the electromagnetic part. With
Yeah,
Fleming's right hand rule, Fleming's left hand rule, Faraday's law, kind of thing, Lenz's law.
Sir, you would need to explain that to me, sir.
Well, I'll explain that tomorrow. Because I'm doing my electrical engineering degree, so light work. All right, so I'm gonna follow. Okay with this?
Yes, sir.
Yeah.
All you get that?
Yes, sir.
Good. 5 marks in all. 5 marks. Part C. Thunder is heard 2.3 seconds after a flash of lightning is seen. If the lightning strike is 750 meters away, calculate the speed up for this event. Oh yeah. What's the
Simple.
formula for speed? What's the formula for speed?
Distance over time.
Distance over time.
All you realize I'm giving away marks. The distance is 750 meters away, and the time is 2.3. What is that?
I got
326.1.
326.1.
326.
0.1.
So with 4 marks just for that?
Yeah, yeah. It's crazy, right? I tell you, I don't know if I
Wait,
realize, but CSEC physics is very easy to pass in. CSEC
And I
physics
do.
is very
Isn't
easy
it
to.
meters per second
Yeah,
minus
yeah. I
1 meter?
just verifying something.
So I feel that is just way to overthink things and get wrong.
oh, wait, I think we gotta put our unit, yeah.
Yeah, so like 1 mark for the formula, 1 mark for the substitution, 1 mark for the answer, and 1 mark for the units.
Yeah.
Yeah. Cool. Are you okay with that? Easy, right?
So
Good. All right. Carl and his friend Tommy were doing a school-based assessment on estimating the speed of sound in air using an echo method. All you need to understand what echo means, right? Echo means
yes, sir.
that the sound wave is gonna go hit the wall and then do what?
Bounce back.
Bounce back.
Bounce
Reflects.
back.
Reflects.
Like when a bounce back like a basketball, if I'm correct.
So there's always have that short friend, I said. What's
Yeah,
Tommy?
boy. Yeah, boy. Tommy ball too. Yeah, boy. Tommy boy. Tommy ball. I'm put some here for Tommy.
Let him not be ashamed. Give him a buzz cut or something. Yeah.
Give him a hat.
Nah, boy. Who's Tommy Baba, boy? He had no fade.
So this reminds me of she's bald and she's torturing people who have hair.
She's bald. She's bald and she's torching people up here.
Torturing people who have hair.
What is going
No,
on?
I know what you're talking about. That was on TikTok. That was on
That
TikTok.
was from
What
You
just
looking
happened?
fresh there, boy. You looking
That from
fresh there,
that
boy.
from the old cartoon
Whoa.
Totally Spies.
Nice, it's on TikTok.
Yeah.
That looked up. That
Yeah.
looked up. That looked up.
Totally
So,
spies
so,
on our way.
Tommy, poor
so, hey, go
Tommy.
back. So,
I should be a Baba dog. I should be a
Look.
GTA Baba boy.
Who's his
So
Yeah.
boyfriend?
Tommy looking deformed.
So let me go back to work.
Yeah, yeah.
He
Let
was
me know.
supposed to be without it.
So the sound wave would travel to the wall. So anytime you know an echo, just need to multiply the distance by 2.
Dose.
So the
Because they're
sound wave is
traveling
gonna
twice.
exactly it's gonna travel to the wall and then it's gonna come back. So by the time you hear that, it would have traveled what distance?
200 meters.
200 meters.
Right, so Carl stands 100 meters from a wall. Carl claps 2 wooden blocks to produce a series of echoes, and Tommy, who was standing beside him, starts his stopwatch. After 1 echo, Tommy stops the watch. This process is repeated, and the time for 50 echoes. So 50 echoes is calculated as 30.3 seconds. So what do you think we should do, eh? They try to make it sound complicated, but it's easy. They want me to calculate.
200.
They want me to calculate the speed of the sound generated. Remind me, guys. 1 echo. What is the distance 1 echo travels?
200 meters.
200 meters.
200 meters.
So
100 meters.
they give me 50 echoes. What do you think I should do?
Multiply the 50 by the
Divide
200.
200.
I wasn't gonna do that now. I'd have fine for 1
Multiply
echo
200
first.
by 50.
I'd have fine for 1 echo first. Because here what I'm saying, right? Here what I'm saying. We know the distance 1 echo travels. Shouldn't we find the time it takes for 1 echo?
Oh, yeah.
Yeah, that makes sense.
No, because here what I'm saying, right? We know that speed is equal to distance over time. And so if we could figure out the distance for 1 echo, we'd need the time for what?
1 echo.
Yeah. So probably understand any logic. So 1 echo would be 30.3 all over 50. And that would be what?
0.606 seconds.
Right. And your answer is supposed to be like around 300 and something, right? Because the speed of sound we're dealing with, right?
Yes, sir.
Seconds. So then the speed could be what?
Speed could be distance over time.
What's the distance?
Distance is 200.
What is the time?
0.606.
Let me know what I get. Should get something like around 3.
Yeah, so
330.
330.03.
330.03, yeah.
Wait, so let me just verify it. Yeah. I think the speed of sound is 333 or something. Let me just verify. Like, what's the exact speed of sound?
Someone wants to know how you get the 200 again.
No problem. Speed of sound is 343 meters per second in dry air. Yeah. So 330.0. You can round it off to 3 significant figures or 2 decimal places. Yeah, it's fine. Whichever one you choose. Are you okay with this? Or are you confused?
Now we're good, so.
So I fully understand too.
I understand.
Right, so somebody was confused about the 200. So let me explain. If it's I still admire and the job I do for Tommy Boy, big up Tommy looking fresh now. Right? But if it's an echo, okay, so when he hits the wooden blocks together, the sound wave is going to travel. It's gonna hit the wall and it's gonna bounce back. And it's gonna hit their ears. What distance is the sound wave traveling?
Meters.
To the person I was confused, do you understand that the sound wave would travel 100 meters to hit the wall? Then 100 meters again to hit their ears. Do you understand on that?
They say yes, sir. They're talking in the chat.
Okay, good. So here what we know the distance one echo travels 200 meters, and they told us 50 echoes is 30.3 seconds. So can we find the time it takes for one echo?
Yes, sir.
Yes, sir.
Again, I hope I understand my reasoning, because speed is distance over time. So if we know the distance for one echo, well, you gotta know the time for one echo as well. So that's that. 5 marks.
Like 3
Easy.
marks.
Physics is amazing.
Physics is amazing. What's like that doing here, boy?
Right now,
Define
physics. Right now,
Saitama,
physics
just
allowing
define
me to sit down.
physics.
Right now, physics allowing me to sit down.
Nah. Saitama before he started training and lost all of his hair.
Oh
Looking
gosh,
like
that
Thrag.
my body sticker with a take
Yeah.
Dora and a
Good, I
put
don't
Dora.
have stress,
We
sir.
get Dora, yes,
That like a
guys.
Thrag hairline.
Like that.
So at this point, you might as well change your career path.
Baba dog.
Yeah.
I'm telling you, wait a minute.
Baba.
I changed the race on to one thing. You know what I mean? But as a GTA Baba, you know, as a GTA Baba. Yeah, but it's
He's
hey,
a
he looking
maths
like
whiz,
mob.
a
No,
physics whiz, and he could do hair.
Looking like mob psycho.
Mob Psycho. Yes, I was going to say that. He looking like Mob Psycho. Yes. He does look
I
like
am
Mob Psycho.
Steve.
So let me continue. A popular radio station broadcasts with a frequency of 100 by 10 to the power 6 hertz. So I don't know if I realize this. Remember, rich men in Vegas use expensive gadgets, right? And so we understood that radio waves had the what? Radio waves had the what?
Longest wavelength.
Longest wave.
It's
Longest wavelength.
Lowest frequency.
Lowest frequency.
Now, I don't know if I realize this, right? But the frequency for the radio station was by 10 to the power 6 hertz. And if you look in the last question for Rattlesnake and B, it was a lot more. 10 to the power 14. So let's see how everything connecting. Like we know that the radio waves have a very low frequency because the wavelength is very big. It's a very long wavelength. So everything is connected. Everything is connected. All right, cool. So let me answer the question on Nikolai. So they gave us the frequency as 100 by 10 to the power 6 hertz. And they want us to calculate in centimeters the wavelength of the sound waves generated. And it's telling us the speed of radio waves. We know that. So Nikolai, we're going to use here to find the wavelength.
Well, first of all, you use the formula V is equals to F lambda. But since you don't know Since we don't know the velocity, we'd have to change the velocity to speed. So we would change it to c is equals to f lambda. And then
That's fine. That's fine. You can make a direct substitution if you want.
all right, well, we'll just change the velocity to 3.0 times 10 to the power 8. We know the frequency is 100 times 10 to the power 6. And we don't know what is lambda, so we make lambda the subject by dividing by 100 times 10 to the power 6. And we'll have to find out that, well, we have to divide that on the other side too. I got 3 as my answer.
Likewise.
I got 3 as well. And let me ask you a question, right? We're working in terms of hertz, which is 1 over s, and we're dealing with speed in meters per second. So our wavelengths will be in what units?
It's supposed to be in meters, but they ask it in centimeters, so
Right, so I'll have to multiply this by what?
100,
100.
100.
So it's 3 by 100.
300.
300
Yeah, boy.
centimeters.
That was, hey, 4 marks. Well, yeah. Well, you don't
And
find
that's
this
the end of the
physics thing.
exam.
Well, you don't find this physics thing low-key easy. Like low-key.
Yeah,
So I'm
low-key.
locked in. I'm
Yes,
locked
sir.
in.
Locked in.
Right. Yeah, boy. Okay, now let me move on to a harder question, huh? Right, this was a harder question. A lot harder.
Nobody cheating. Stop looking.
Close
As you
our
can see,
eyes,
as you can
protect
see,
yourself.
as you can see, it was a lot harder. It's a very hard question.
That's a lot of lookings, boy.
Son, what year was that?
I think 2014. I wonder if I should even do this question, but I think I'll like tackle
Yeah,
it.
Let's do it.
you can explain it to me as we go along.
Yes,
Yeah.
sir. You could,
Can't say it,
you could
but
explain while
explain.
we go along.
God forbid they drop one like this on week Friday.
Well, let's see.
Gil, don't say that, nah.
So, state 2 properties of EM waves. Tell me fast, guys. What are 2 properties of EM waves?
All our transverse waves.
And
Transverse.
travel at
Speed of light.
Speed of light.
easy 2 marks.
Or they have the crest and the troughs.
Yeah. Visible light is a type of electromagnetic wave. State 2 other types of electromagnetic waves, indicating whether the wavelength of each is higher or lower than that of visible light. So here,
Radio waves and gamma rays.
Infrared.
a little bad boy.
Infrared.
UV.
So here what, guys? Here what? They're telling us visible light is a type of EM wave, and they want us to state 2 other types of EM waves, indicating whether the wavelength is higher or lower. So here what? Rich men in Vegas use expensive gadgets. So we're looking at visible light here, right? So if you pick radio waves, you would say radio waves have a higher wavelength. So you would say it have a bigger wavelength, right? They want them to, yeah, higher or lower. Okay. So radio waves, okay, with reference to visible light, radio waves have a what?
A higher visible light.
Infrared would have a what?
A higher.
Higher.
Right? If you had picked gamma, you'd say gamma has a what?
Smaller.
Yeah.
Right? A way to use the lingo they say in the question, right? So higher or lower. So you see like higher wavelength or lower wavelength. Use the lingo. But it's fine regardless. So I decided to pick radio waves and microwaves. And I say both are higher than visible light. And I find that was hard or easy?
It was easy.
That was easy.
Yeah, just had to learn your EM spectrum and that's it.
Yeah, just had to learn your acronym.
Yeah, 6 marks. Let's just get 6 marks in the exam. Okay. Any volunteers? Any volunteers with this one?
So if nobody will in you.
Oh, well, we go chatting.
Well, I hear Gil, so they will try a thing.
Yes. Yeah.
What am I yawning for?
So we catch you lacking. Thought you had everything.
So if nobody know what try, I go like to try.
Don't sleep.
You know, we can do it collectively, you know, Renisha.
Okay, no problem. All right. Electromagnetic waves of one wavelength are absorbed by a solar panel, and wave of a longer wavelength are emitted if electromagnetic waves of wavelength equals 2 times 10 to the power of -7 meters are absorbed by a solar panel, as shown in figure 3, and waves of wavelength to the power of 2 equals 6.5 times 10 to the power of -5 are emitted. -5 meters, sorry, are emitted. Calculate A, the frequency in each case, and B, the decrease in frequency F.
Delta.
Right. So delta F means the change in F, right?
Yeah.
Okay.
Change in F. Right. So Renisha, you want to help me with A or B?
The first one.
First one, a big easy one, right? So
Okay.
they want me to find the frequency in each case. So Renisha, in the
Yes, sir.
questions, there it is stated that we are dealing with EM waves. For EM waves, you know that the velocity is what?
Correct me if I'm wrong. Higher and lower.
Nah. When we talk about velocity, we're talking about the speed. What's the speed of all EM waves? All
3
EM waves
times 10
travel.
to the power of 8.
Speed
Yeah,
of light.
Speed
Renisha.
of light.
Inversely proportional.
Nah. So Renisha, you remember this, right? All EM
I'm
waves
so
travel.
sorry.
That's okay. You're learning. So all EM waves travel at the speed of light. So
Okay.
speed of light. So all, Renisha, don't forget it after this, eh? We go have problems if you forget after this.
Speed
So,
of light. Right.
right. And the speed of light, C, is equal to 3 by 10 to what power?
8. 8.
Meters per second. Right? So Renisha,
Yes.
I'm gonna
Yes, sir.
pull it away. Renisha, tell me a property of EM waves.
Property of EM waves.
Mm-hmm.
They are inversely proportional.
Now,
No. Wait. Hold on. Oh, I know it. So we just went over it, right?
mm-hmm. Just went over that.
Speed of light.
Yeah, so all EM waves travel at the speed of light. Yeah, and what's the speed of light?
What is the speed of light?
Mm-hmm.
3 times 10 to the power of 8.
Good. And all EM waves are transverse waves, right?
Yes, sir.
Right. So here what they want me to find the frequency. Renisha, they give it.
Yes, sir.
We know the speed is the speed of light. We know the wavelength. They gave us the wavelength, and they want me to find frequency. What formula should use?
Formula.
What formula have wavelength, frequency, and speed in it? Or velocity?
V over F.
Nah.
No, it's not that one.
Renisha, you gotta grind physics tonight. Alright, so Renisha, I'm gonna help you out, right? Remember this. Everything we do today, remember it, right?
Okay.
So tell me fast, what's the speed of light?
3 times 10 to the power of 8.
And all EM waves travel at the speed, right?
Yes, sir.
And the formula we want to use is V is equal to F lambda.
Oh, never heard of that one before until now. So
What? What,
no
Renisha?
serious thing. The teacher
What?
that I had
We just do that. Renisha.
until
Renisha.
today. I say until today.
Renisha, we use that formula real time today, boy. But that's okay. You're learning. So let me find the frequency now. If I wanted to find the frequency, what would I do? I would have to make what the subject of the formula?
F.
Yes.
F. So I would have to I'd have to divide both sides by what?
F.
No, I'm trying to find
No,
for
no,
F.
no. No, no, no. V?
Nah, I feel like you guess some. All right, so Renisha, we're trying to find for F, right? We're trying to find
Or
for
the
F.
symbol, the symbol. Yeah,
We
the
want to cancel that off. We want to get rid of it. We want to get
right,
rid of it. So I
right.
should divide both sides by that.
Yes. Okay.
So
So
leave
I'm
us a 3.
sorry. I'm sorry. I'm sorry. I try and I try and I really try and I try.
That's good that you tried. So let me find the frequency at the first one, huh? So we
Okay.
could probably call her F1.
Mm-hmm.
So what is the wavelength for the first one?
Wavelength for the first one is 2 times 10 to the power of -7.
Wait, what's going on? On top is supposed to be velocity, right? Was the velocity or EM waves?
The velocity,
Yeah, was the velocity or EM waves?
3 times 10 to the power of 8.
Right. So let me plug onto the calculator first.
Okay. Okay.
Yeah, I'll leave it a minute for again, yeah?
Yes, sir.
So when you shut that's what you're supposed to
Yeah.
get.
Yes, sir.
1.5 by 10 to the power 15. And what's the unit for frequency?
Meters slash seconds.
Right, that's
Minutes slash seconds. Sorry.
that's hertz. Frequency is hertz.
Hertz. Okay.
Yeah, frequency is hertz. Renisha is scared him a little bit. Little bit.
Sir, I am sorry.
Little bit. Right, so let me
So
find for
how would
F2
you put
now.
this in a shop calculator? I haven't
It
traveled.
okay, open bracket 3 by 10 to the power 8. Close bracket divided open bracket 2 by 10 to the power -7. Close bracket. You know how to put powers on the sharp?
Yes, sir.
Alright, nice. So plug it in and now hopefully you should get the answer. Sharps just make people's life so complicated for no reason, huh? Sharp. So let me
Hey,
find for
my sharp lass, innit?
sharp is not the way, not the way. Alright, so find for F2 now. F2 would be Tamaronisha fast. How would I find for F2?
Okay. So I'm sensing I have to divide the speed of velocity by wavelength 2.
Yeah, that's partially correct. So what am I gonna put on top?
The speed of velocity?
Nah, it don't say speed and velocity. Speed means okay.
Oh,
Speed is
sorry.
speed is a scalar quantity. Okay, speed is a scalar quantity and velocity is a vector quantity. They are
Okay.
used interchangeably.
Okay.
So velocity is the vector counterpart to speed. So like
Okay.
they more or less they kind of mean the same thing. It's just that velocity has direction. You wouldn't say speed of velocity. You would say speed of light or velocity
Speed of
of light.
light.
Yeah, speed of
Okay.
light. So that would be 3 by 10 to the power 8.
Yes,
Then
and underneath will be 6.5 times 10 to the power of -5.
I'm checking people on YouTube, see if they get through. People on YouTube, are they getting through? Let's see. People on YouTube, are they getting through or not? Nikolai, it have 160 people on YouTube, boy.
Wow. Physics.
Yeah,
So remember, physics is vibes and
yeah, physics is vibes.
And I catching my backside here.
Nah, you'll get through, get through. So Renisha,
Yes, sir.
this is the answer you're supposed to
Yes.
get. F2 is equal to 4.61
times 10.
Oh, you were saying 4.62, right? 4.62.
Yeah.
4.62 by 10 to the power 12 is.
Yes.
So let me explain that again, right? So, if you have a sharp, you'll have to plug it in like this, right? You'll put open bracket 3 by 10 to the power 8, close bracket, divided open bracket 6.5 by 10 to the power negative 5, close bracket. And you should get this. Now we want to round off the answer to 2 decimal places. So we have 6-1, number after 1 is 5. Since it's 5 or more, you add 1 to 1 to 4.62. 4.62 by 10 to the power 12 is. People in Zoom, want to get through or not?
Yes, sir.
Yes, sir.
Okay, Renisha, I'm worried about you, not Renisha. I'm worried about you.
I know.
I was say I prayers for you tonight. But you had a real grind physics tonight, I tell you. I learned, you real how to do with physics. You have
Wait.
limited time. Yeah?
We can go over it one more time, just once.
Okay, no problem. So in the question, they are saying now we are dealing with what type of waves? Renisha and Sarai.
Electromagnetic waves.
Electromagnetic waves.
EM.
Good. You guys need to know that EM waves travel at what speed? What speed do they travel at?
Speed of light.
The
3
speed
times
of
10 to the
light.
power of 8.
Right. So in other words, that's what V would be equal to. So we would use V as 3 by 10 to the power 8. So Renisha and Sarai, you understand that?
Yes, sir.
Okay.
Yes, sir.
And they're saying electromagnetic waves of one wavelength are absorbed by a solar panel and waves of a longer wavelength are emitted. People that did that were there when we did thermal physics, and this making sense? You have short wavelength radiation coming from the sun and it gets re-emitted as long wavelength radiation.
Yes, sir. I
People
remember
out
that.
any
I
thermal
remember that.
Nikolai, you remember this?
Yes, sir.
And Nikolai, I tell you, if it had a longer wavelength, it had more or less energy.
Less energy.
Yeah. Higher penetrative ability or lesser penetrative abilities.
Less. It'll be
Yeah.
It'll
trapped.
be less.
Thermal physics live was real important, guys. Real important. So anyways, Sarah and Renisha, we're dealing with EM waves, so automatically I'm gonna use V as 3 by 10 to the power 8. They're telling us the wavelength of one and the wavelength of the other one. So you're seeing speed, you're seeing wavelength, and they're asking you for frequency. Sarah, what formula comes to mind when you see these three things mentioned? Frequency, wavelength, and
Velocity by frequency, gamma. Yeah. Yeah.
lambda. So V is equal to F lambda. V is equal to F lambda, right? V is equal to F lambda.
Yeah. V is equal to F lambda. Yeah.
And they want us to find for frequency, so we should probably make frequency the subject of the formula. So what would I do here to make frequency the subject?
Divide both sides
You
by
would,
lambda.
yeah, divide both sides by gamma.
Oh, not lambda, lambda. Lambda.
Lambda. Sorry.
That's okay. So it cancel off over here, and so F would be equal to V over lambda. So Sarah and Renisha, you understand this?
Yes, sir.
All right, and since we're dealing with
Yes,
EM
sir.
waves, EM waves, what is the velocity for EM waves?
3 by 10 to the
To
power
the
of
power of
8
8.
meters per
Right.
second.
And so if you wanted to find F1, you'd just say 3 by 10 to the power 8, and you'd plug in the initial wavelength, which was 2 by 10 to the power minus 7.
And you get 1.5 times
You get
10 to the power.
1.5. And
Okay.
well, Sarah, for the other one is the same process. It's just I replace the wavelength for what now?
For 6.5, yeah, 6.5 by 10 to the power of negative 5.
Good. So somebody said, where did the 3 by 10 to the power 8 come from? Again, anytime you see EM waves travel at the speed of light. So all EM waves travel at a speed of 3 by 10 to the power 8. You need to understand that velocity and speed are used kind of interchangeably. So if we're dealing with EM waves, the velocity or the speed is 3 by 10 to the power 8. But you should know that velocity is a vector quantity of speed, but they use it interchangeably. So the 3 by 10 to the power 8 is just the speed of all the EM waves, and we use that as V. Hope you understand.
So hence, that's why C is equal to 3 times 10 to the power of 8.
Right. Let me find part B now, the decrease in frequency. So the decrease in frequency, that would be, so like, okay, they want me to find delta F, which is a change in frequency. Let me look at this intuitively, right? Over here we have short wavelength radiation. And if we have short wavelength, it would imply that the frequency is higher or
Higher.
Higher.
Yeah.
and over here we have long wavelength.
Lower.
This would
It would be
suggest
lower.
a lower frequency.
Okay.
Does our answers reflect this? So for the first
Yes,
one,
sir.
we get in 10 to the power 15, and for the other one, we get in 10 to the power 12. Which one is higher?
10 to the
10 to the
power of
power
15.
15.
Yeah, so you see how the intuition is important? Just by looking at this, you can figure out if you're going wrong or right. So this is correct. And we want to find a change in frequency. So if I want to find a change in frequency, I'm going to put the bigger frequency first minus the smaller frequency. What was the bigger frequency?
1.5 by 10
by
to the
10 to
15.
the power of 15.
And I minus that by what?
4.62 by 10 to the power of 12.
People on YouTube, all the people in the Zoom, tell them what to do. Tell them what to do. Don't forget to, you know what I mean?
Like and subscribe.
Yeah, don't forget to like
Watching
and
the video and not liking the video and not subscribing.
listen to
Like
Nikolai.
and subscribe, guys. We have to hit 5K before CXC done.
Exactly.
Yeah. And CXC
Plus,
finishing in
plus
the
I'm gonna be
next
missing out a lot
2
of
weeks.
information and new videos that should be posting up.
Exactly. We're gonna be doing people one lives for maths, art, maths, and physics.
So Ole, make sure and subscribe and turn on those notifications.
For
So
sure, for sure.
they go subscribe to other things that are not helping them in their knowledge. Or something like this. They're just watching and not doing anything. Come
It's
on.
crazy. Exactly. It's crazy, right? It's crazy. I don't know what's wrong with these people, but all right. So when you minus that, you should get 1.50.
Yes, sir.
Now, can we both agree that that's like a very negligible difference?
Yep.
So
It's really, really negligible. It's like really, really negligible. Like I can't even see it. I can't even see it really. I mean, if I write one, yeah,
Is there one other question I could do to redeem myself?
the questions just get a lot harder from here onwards. A
Oh
lot harder.
boy.
Yes, sir,
If
that difference.
I
It's
still won't
crazy.
try.
Don't
right, so
worry, Nisha, girl, I believe in you.
Oh,
Renisha,
thank you.
read part 2 for me.
Okay. We assume that the useful energy transferred to the solar panel is a constant K times the decrease in frequency of the EM waves. In brackets, E equals K delta F,
Right?
close brackets. State the corresponding energy transfer E1 in terms of K.
All right. So Renisha, you can get through with this one, man. You can get through. So they're telling you that E is equal to K by delta F. Do we know what delta F is?
Delta F is 1.5 times 10 to the power of 15 hertz.
Right?
And they give you the speed of light in the brackets
Wait, yeah.
underneath.
No. In this, all we had to do is just substitute. That's all. All we had to do is
Okay.
substitute.
Okay.
Let me explain why. In the question, they said, we assume that the useful energy transferred to the solar panel is a constant K times the decrease in frequency of the EM waves. So they are telling us energy is equal to this K by delta F. So
So we
all
have
they
to
have
find
to do
K.
is, they just want you to state the corresponding energy transferred E1 in terms of K. So in terms of K. So all you
Okay.
had to do was just plug in what delta F was. That's all. Delta F was 1.5 by 10 to the power 15. Just plug in that in. All I understand that part or not?
Yes, sir.
Yes, sir.
I
So
just
redeem myself.
Yes.
Mm. You can try with part 3, but this one really tough. It's really tough.
All right. Never give up.
I can't give up.
Never say
With a
never.
chance of conditions, the wavelength of the wave now absorbed by the panel increased to 6 times 10 to the power of -7 meters, but the emitted wavelength remains at
Lambda 2.
lambda 2 is equal to 6.5 times 10 to the power of -5 meters. What fraction of E1, the original energy transferred, is now transferred to the solar panel?
Okay, how much did I read that? And it just come through one is and going through the other one.
Yeah, that was me.
Yeah. Oh, annoying. Hey, what's that? Anyway,
Oh, by the way, if any other gonna do unit 1 physics, you will see this pop up again. And you
so
would see that it looks like this. It looks like proper thing would be E is equal to HF. So K is really Planck's constant, but we're not gonna assume that. But just telling on it, you go see E is equal to HF. Right?
in unit 1 or unit 2?
Unit 1 physics. Unit 1 physics is a lot is like mechanics, light, and unit 2 physics is like heavy on electrical part of physics.
Well, thanks for the spoiler alert, because I had to do that. I needed a cape
Good one.
pass in physics.
It's be tough, So
They became complicated, but I think I have an idea.
all right, so I'm gonna read back the question one more time and write down the key information, right? Just so people could kind of have ideas of what we're on. So the change in the conditions and the wavelength of the wave now absorbed by the panel increased to 6 by 10 to the power -7 meters. But the emitted wavelength remains at lambda 2 is equal to 6.5 by 10 to the power -5 meters. What fraction of E1, the original energy transferred, is now transferred to the solar panel? So like essentially what they want me to do is they want me to compare E2 and E1 together. So Marshall, let me hear a suggestion. Suggest something and I'll tell you if you're correct.
Oh, well, I was thinking, So it was in my head, but it was something along the lines of the wavelength. Like when you calculate the frequency using the new wavelength that they gave you, and you compare it to the last one, the difference kind of would be the energy absorbed by the solar panel.
Okay, I have idea. So what changed? Well, if you notice, the wavelength of the wave now absorbed by the panel increased to 6 by 10 to the power -7 meters. So if that's the case, it would have an impact on the amount of energy the solar panel would produce. So what they really want me to do is they really want me to compare this new energy to the previous energy. So you see what we found in the last part, E is equal to K by 1.5 by 10 to the power 15. That would have been the energy.
That was the last answer we get.
That would have been E1. That's what E1 is. So here what? They really want me to compare E2 and E1 together. That's what they want me to do. Because they said what fraction of E1. So they said what fraction of E1, the original energy transfer, is now transferred to the solar panel. So what they really want E2 over E1. And we already have E1.
Excuse me.
Yes, sir.
Isn't does of, I know of means to multiply, but in this case, would you have to multiply anything?
You would have to multiply things, yeah. Yeah.
Okay.
When you have to find for the second energy.
Okay.
So here what? I want somebody to tell me how would I go about finding for E2? Anybody could give me any suggestions? Or we know energy is equal to how would I find for energy? Tell me that.
For E2, you want to do speed multiplied by the Planck constant divided by the wavelength.
So you would first have to find the okay. You would have to factor in the new delta F. You would have a different delta F this time. You understand that? Right? Or not? In this question, you have a different delta F. Because if you notice, it now absorbing a different wavelength. So here what? I'll guide all that accordingly. So if I want to find for energy, it's gonna be K, which we know is Planck's constant, but we're not gonna assume. And by delta F. So we need to find a new delta F. So they're telling us the wavelength it is absorbing is now increased to 6 by 10 to the power negative 7 meters. So I could probably find for F1 there, the new F1. And if I want to figure that out, what was the formula for F again? What did I find F to be?
V over lambda.
F was V over lambda.
Yeah. V over lambda.
So here what? I could find the new frequency. So that will be 3 by 10 to the power 8 all over the new wavelength. What's the new wavelength it's absorbing now?
This is for 1, right?
2.5.
Yeah, 6 by 10 to the power of negative 7.
And this would be the new F1. I will explain it back when we finish. What are we getting for that? Somebody plug that into your calculator and let me know what you're getting. Anybody gets an answer? I plug that in the calculator.
So my sharp's telling me error thing.
I got 5 times 10 to the power 14.
Right, that makes sense. If you have a sharp, you have to put copious amounts of brackets. So like for one bracket here, 3 by 10 to the power 8, close bracket, divided, open bracket, 6 by 10 to the power negative 7, close bracket. Plug that into your sharp and let me know what you get.
So I do that, but
2.5.
like I had to put the -7 in a bracket by itself too.
Yep, yeah, do that too.
Um,
Anytime you have negative numbers on a sharp, you gotta put that in brackets too. Sharp is very infuriating.
So at this point, sharp is no longer sharp. Just name it brackets on them.
Yeah. It real dull. Real dull. Sharp, real dull. So it's supposed to get 5 by 10 to the power 14.
Calculator dull, then why the name it sharp?
so I gain 180 and thing.
Oh my.
Burn the sharp and jump over to Casio.
Let me see if I can help you out somehow. Give me a second. I don't want to abandon anybody. Give me a second. Suppose I have a virtual calculator lying around. Why is it not working? Give me a second. That's weird. Give me a second, right? So I have a sharp calculator.
So I know get you.
Okay, yeah, because the sharp calculator I have on my laptop now not working.
Well, how you get through though, like what you do because other people have a sharp, so share the knowledge.
Oh, sorry, my bad. But yeah, it's just excessive brackets. So like after the
Yes,
first,
you add up all the
yeah,
numbers in brackets, you see, right?
you literally have to, instead of putting actual brackets around the -7, you know, the minus bottom at the bottom with the slash
Yeah.
between the plus and minus sign. Yeah, to press that, and it will implant its own brackets and then a bracket after that, and then you'll get through.
Oh, okay.
Yeah.
Thank you.
Yeah. All right. Let me continue. So 5 by 10 to the power 14. So here what, right? Since the wavelength I absorbed is now different, wouldn't that affect my delta F?
Yes, sir.
It would affect my delta F. So in the last question, we found the delta F for this. I mean, not the delta F, we found the frequency for this. What was that way?
Yes, sir.
So
Wait,
which one?
What was
Yeah.
what was the answer?
what do you mean, what's the answer? It was 5 by 10 to the power 14.
Okay, well, I get that.
Okay, good. I feel so bad for anybody that have a sharp. So bad.
For real.
All right, so let me explain something. Here, the only thing that changed in the question was the wavelength that the solar panel absorbs. But the wavelength the wavelength it re-emits is the same. That was lambda 2 is equal to 6.5 by 10 to the power minus 5. Didn't we find that frequency already?
Yes, sir.
Yes,
Yeah,
sir.
so it's 4.62 by 10 to the power 12. So we already have that. So ultimately, if I want to find for delta F, how would I find for delta F? The new delta F.
So you just subtract the new one, the old one from the new one that you got.
So, wait, so I would say what? Well, I'll say the bigger one minus the smaller one.
Yeah.
So I would say 5 by 10 to the power 14 minus what?
4.62 by 10 to the power 12.
This is highly unlikely to come. I hope.
So it's not that bad.
It's not that bad. I will explain it back when I finish. Not bad. Yeah. Which is, I'm going to follow again now. 4.95.
Yes, sir.
So 4.95 by 10 to the power 14 hertz. So here we're seeing, right? If this is a new delta F, then the new energy will be given by K by the 4.95 by 10 to the power 15. And if we want to find the ratio, they literally said they want me to find what fraction of E1 is the original energy transferred. So this was the old energy. This is the new energy. And so if I want to find E2 over E1, all I have to do is just say K by 4.95 by 10 to the power 15 over what? Does anybody know?
K, 1.5 by 10 to the power 15.
Yeah, because isn't that literally E2 over E1?
Yep.
Yes,
It
sir.
was literally E2 over E1. So when you
So
plug
I
that
don't
into
know
your
if my
calculator,
calculator going KY, but you say the answer is 4.95 times 10 to the power 14. Well, I get the 4.95, but after the 5, I had 3.8.
wait, guys, give me a second. That 4.95 was beaten to the power 14. No? Where do I get 15 from? Yeah. So let's say that again, Renisha.
I get the correct answer, but I don't know why my calculator gave me 2 extra numbers.
You have a sharp end.
Yeah, unfortunately.
No, it have two extra numbers. It's just that we round it off.
Oh yeah. We round it off.
All right. Just making
Yeah.
sure. Just making sure.
Watch. 0.95. Number after 5 is 3, which is less than 5. So we round down. So 4.95. Right? So here what? The keys are going to cancel off, and we can now plug this into our calculator. So when you plug that into your calculator, what are you getting for E2 over E1?
0.33.
3.3.
That's it? 0.33? That's your answer. That's it. It looked hard, but I wouldn't say it's a hard question. It sounds complicated to understand, but
Yes, I get that. Yeah, correct.
so 33 over 100. That's the ideal thing to write. 33 over 100.
There's a fraction also, right?
Yeah, because it said what fraction of E1, the original energy transferred, is now transferred to the solar panel. So 33 over 100. So let me go through the question again, right? In part 2, they gave us a way to find energy, and energy was equal to K times the change in frequency. So for the last bits of information, we found that the energy would have been K by 1.5 by 10 to the power 15. Now in this question, they change the wavelength that the solar panel is absorbing. Guys, if they change the wavelength that the solar panel is absorbing, will F1 be the same?
No, sir.
No, so we have to calculate F1 from scratch. So F1 is going to be 3 by 10 to the power 8, and we're going to put the new wavelength. The new wavelength is 6 by 10 to the power negative 7. So when you plug that into your calculator, you should get 5 by 10 to the power 14 hertz. Now that was the only thing that changed. The wavelength re-emitted by the solar panel is still the same. And so that would have still been F2. F2 did not change. That was 4.62 by 10 to the power 12 hertz. And so the difference would have just been 5 by 10 to the power 14 minus 4.62 by 10 to the power 12, which gave us a delta F of that. So in other words, my new energy is just going to be K by 4.95 by 10 to the power 14. I wanted to find E2 over E1, so I took E2 and I divided it by
E1.
exactly. And that's how I get to the 3 over 100. Yeah.
What I'm looking, but the understanding is there.
Yeah, I understand.
I'm going to tell you back again. It's a lot of big words. So the solar panel is absorbing radiation of a certain wavelength, and it's going to re-emit radiation of a certain wavelength as well. Now in the first part, they told us that it absorbed electromagnetic waves of this wavelength, 2 by 10 to the power negative 7 meters, and it re-emitted it at a wavelength of 6.5 by 10 to the power minus 5. So in first part A, they wanted us to find the frequency of each case. Now frequency is just velocity all over lambda. That's all it is. So if I have a wavelength of 2 by 10 to the power negative 7 meters, to find my frequency, it's just the speed of light, because we're dealing with EM waves, over the 2 by 10 to the power negative 7. And that's going to give us a frequency of 1.5 by 10 to the power 15 hertz. We do the same thing with the other wavelength, and we get the other frequency. They asked us to find the decrease in frequency delta F. Delta F just means the change in frequency. So I'm going to put the bigger frequency, which is the 1.5 by 10 to the power 15, and I'm going to subtract the 4.62 by 10 to the power 12 from that. That is going to give me delta F. So you should get delta F to be 1.5 by 10 to the power 15 hertz. Now, in the next part, they're telling us that we could find energy as the delta F times a product of some constant or proportionality K. So the energy in the first rounds would be given by E is equal to K by 1.5 by 10 to the power 15. And that was for the first scenario. Now in this round, we have a different scenario. Guys, what was the only thing that changed in the second scenario?
The wavelength. Absorb.
Wavelength.
The wavelength absorb. So if the wavelength
Yeah.
absorb those change, then wouldn't the frequency consequently change?
Yep.
Yes, sir.
Yes, sir.
So all we had to do was just find a new frequency, that's all. The other wavelength didn't change, so that was the same frequency as before. Same frequency. So all I had to do from here is find delta F, because wouldn't delta F change now?
Yes, sir.
Yes, sir.
Yeah, delta F would change because it's now absorbing a different wavelength. And if it's absorbing a different wavelength, then that would correspond to a different frequency. So we calculated a new delta F as 5 by 10 to the power 14 minus 4.62 by 10 to the power 12. And we got 4.95 by 10 to the power 14 hertz. Now again, if we want to find energy, energy is just K times delta F. So if we know delta F is this, then E2 would just be K by 4.95 by 10 to the power 14. They wanted us to find what fraction of E1, the original energy transferred, is now transferred to the solar panel. So they want us to compare the new energy to the previous energy as a fraction. And so E2 is just going to be E2 over E1. And so E2 was K by 4.95 by 10 to the power 14. And we were supposed to divide that by the original energy, which was K by 1.5 by 10 to the power 15. So the K and the K would cancel off, and you could just input this into your calculator, and it should get to the 3 over 100. Definitely on the harder side, but I think we can manage it. Like, okay, I had to be honest, this was the only hard question we come across. This was the only hard question we come across.
True.
Yes, that's true.
Yes, sir.
I would have never even guessed that until Sir explained it.
Yeah, that was one of the harder ones. So here what? I'm going to move on to refraction, right? Gonna move on to refraction.
Sir, I could take a screenshot of this, please.
Sure.
So even though it was hard, that's okay. We still cooking with gas. We still pushing through. Look how much work we do.
Yeah. The pass rate was 35%.
Thanks, sir.
No. I feel a lot of people has passed physics. Yeah, like the numbers drop after that question. Like I see had like 60 people in class, it dropped down to 48 when people see that question. Yeah,
So
boy.
true. That's true.
Yes,
Yep.
that's true.
Yeah, boy. The numbers on YouTube rising though for some reason.
Although
Don't
you was a
understand.
bit disappointed in me, I still give the question a try.
That's the main thing. The main thing is that you try something, right?
Yeah.
So let me talk about refraction now. What exactly is refraction? Refraction is just the bending of waves when they enter another medium. And this makes sense because would light travel at the same speed in different mediums?
No.
Nope.
No, it
No.
will be a different mediums.
And that has to do with the fact that light doesn't travel at the same speed in different in different mediums. The denser the medium, the what light will travel.
The slower.
The slower. Good.
Slower.
So let's look at the laws of refraction. Number one, the normal is always perpendicular to the boundary line. I'll explain this shortly. Part two, light waves bend when they pass through different mediums, as a result of light traveling at different speeds. This relationship is called Snell's law. How much of you guys learned this particular formula in school? Or you learned the N is equal to sin I over sin R?
Me, sir.
I
Yeah, me
learned
too.
I
it,
learned the
but
other
I
one.
still quite didn't understand it well.
So which one did you guys learn? N is equal to sin I over sin R?
Yes,
Or
sir.
Ni sin I is equal to
Yes,
NR
sir.
sin R?
So I
Mentioned both,
Sir.
but he didn't really go into depth with it. He mentioned both, but he didn't go depth into it. That's the teacher I had.
Okay. I'll explain the differences right between the formulas, don't worry. Because there's a subtle difference.
Thanks, sir.
And there's a reason why I prefer this one. TikTok think I'm a robot. Give me a second. Alright, cool. So again, light waves bend when they pass through different mediums as a result of light traveling at different speeds. This relationship is called Snell's law. Ni sin I is equal to Nr sin R. Number three, the angle of incidence and the angle of refraction lie on opposite sides of the normal, but all lie on the same plane. How much of you guys would have learned this third rule but never understand it?
Me.
Me,
Be
sir.
honest. Right, so I'm going to attempt to rectify that. I'm going to attempt. The first thing I should probably explain is what's the boundary line and the normal. So let's just say we have a cup of water here, right? Stay with me. We have a cup of water. I have a cup of water. So everything over here is what? What's inside here? What is inside here?
Water.
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 Don't worry,
Agua.
guys. I'm going for 12 hours tomorrow. We will do everything I didn't do today. Everything. So you have water here. And what you have on the outside?
Yeah.
Straw?
Yeah.
Oh, eh. Sorry.
Yeah.
That
I
was my
thought that was an
mistake.
invisible straw. No, I thought I wasn't
So,
seeing
Yeah, that's
see
what
and
I'm
lie.
saying.
See and lie too. Waste
Same.
straw.
Sorry, I said what everybody was thinking, but it's my fault.
So we
I'm like,
breathe in
eh.
straws now. We breathe in
Yeah.
straws. Okay.
All right. So guys, over here we have air and over here we have water. So this line over here, doesn't it separate the air and the water?
Yes, sir.
Yes, sir.
Yes,
So
sir.
when you hear boundary line, what do you think about boundary? Boundary.
Separation of two mediums.
Separation of 2 million.
Yeah.
Excuse me. Is this the one with the incident ray and the refractive ray?
Yep, that's it.
Okay.
So guys, you see this purple line over here? This is called the boundary line because it separates the two mediums. Are you understand or not? I need some gas, boy. I need some gas.
Yes, sir.
I need
Yes,
some
sir.
gas.
Yes, sir. Yes,
We
sir.
understand.
Understand it.
Right. And now the normal is going to exist at a right angle to this. Like so. Oh, let's see that dash line I just drew? What's the name of that?
Yeah.
Normal.
The normal.
The normal.
And as you can see, the normal is what to the boundary line?
Perpendicular.
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 Right. Now the next thing I should probably explain is incident ray and refracted ray. Something I want you guys to remember from now till like whenever. If you're going from a more dense to a less dense, you actually bend away from the normal. Conversely, if you're going from a less dense to a more dense, what do you think you're gonna do?
Bend towards.
Yep. This is so important, and I cannot stress the importance of this. This is extremely important. So, tell me, if I'm going from water to air, will the refracted ray bend towards the normal or bend away from the normal?
Bend towards.
Wow. What is more dense, water or air? Somebody tell me, what is more dense, water?
Water than air.
Water is more dense.
So if I am going from a more dense to a less dense, I'm going to bend away from the normal.
Oh, so you mean like you're coming from the air side, from the water side?
Yeah. So more dense to less dense. If I'm going from a less dense to a more dense medium, so like, say for instance, you're going from air to water, you'd bend towards the normal. This is very, 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 very important. Very, very, very important. I'll let you guys take a screenshot of this later on. So actually, I'll leave it there. So let me ask you that question, right? When you hear incident, doesn't it sound like incoming?
Yep.
All right. Cool. Now the incident ray is formed between the what? The boundary line or the normal?
The normal.
Yeah. How much of you guys didn't know this? Did you guys notice that the angle is formed between the incident ray and the normal?
Yes, sir.
Yes, sir.
No, sir.
Yes, sir.
No? Okay, well, if you didn't know, now you know. So, I have a question. If the incident ray went straight through, wouldn't its trajectory look like that if it went straight through, undeviated?
Yeah.
Yes, sir.
Yeah.
Yes,
But
sir.
that is not the case. If I am going from air to water, I'm going from a what to a what? Somebody
Less
tell me.
dense to more dense.
Less
Less
than
dense to
more
more dense.
dense.
Less dense to more dense.
Right. I'm going from less dense to more dense. So you see this ray over here that are wiggling? That's called a refracted ray. Would it bend towards the normal or would it bend that way?
Bend towards.
Towards.
Bend towards the normal.
Towards.
Exactly. And this over here would be the angle of what?
Refraction. Or reflection.
Reflection.
No, not reflection.
Reflection.
Not reflection. This is refraction.
Refraction.
Reflection. Reflection.
the right thing.
Reflection is the instance where the angle of incidence and the angle of refraction are equal. It's not equal over here. So I hope all you understand the basics. So let me run through the process again. So the incident ray is the ray that's incoming. And the angle will be formed with respect to the line and the what?
The
normal.
The normal.
I find I'm only hearing Marshall, Nikolai, and Renisha, you know. I really hear nobody else. I level the camera on and thing. I need some energy.
So you want to see how scary I looking right now?
Well, maybe go wake me up. Maybe go wake me up. You're looking scary.
Almost.
Ways.
Hey, so I'm
All right.
getting more energy.
So-
Yes.
So here what? Let me go on a new page and try to explain this thing again, or you need to understand the concept of this. Otherwise, you're not going to get anything else. All right, let me look at some scenarios here, right? Again, the boundary line separates what? What does the boundary line do?
The two different mediums.
Separate
Separates two different mediums.
Different
Right.
mediums.
Let me just say that A here and there's water over here. Somebody remind me. If I'm going from a more dense, so if I'm going from a more dense to a less dense,
Bends away the normal.
Away.
Bends away
It
from
goes
the
away from the normal.
It bends away from the normal. And if it's less dense to more dense, it will be towards the normal.
yep. Okay, cool. And if it is less dense to more dense, what will happen?
It will bend towards the normal.
Towards.
This part of physics I love.
Me too. So here what, right? Can somebody give me an example of where I would go from a more dense or less dense?
water to air.
Water to air.
Yeah.
Was there an instance of less dense to more dense?
Air to water.
Air to water, yes. Now this black line over here, I'm trying to teach you already foundation. Right, this is the boundary line. What's the name of this line over here?
You
Wait,
know.
I even draw it yet,
Normal.
Nikolai.
Normal.
Normal.
Right, this is normal.
So I predicted it, sir.
Okay, good. Let me try to tie it up, right? What ray would I call this?
Incident.
Incident.
Right, because the incident ray is the what ray? Incoming.
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 What
And
I
the one that
measure
would be on the other side of the boundary line would be the
Refraction.
refractive.
Okay, good. And would I measure the angle here
No.
or here? One or two?
By the normal. So
By the normal.
Two.
It has never be on that side, it has always be on the side by the normal.
Good. So let me ask a question, right? If this ray were to go undeviated, wouldn't it go in this direction?
No.
Yes.
Yes, sir.
Yeah.
Yes, sir.
However, I know that However, I know that I'm going from a more dense to a less dense. So what should happen?
It should
It
bend
should
away
bend
from
away
the norm.
It should bend away from the norm.
So it might look a little something like this, right?
Yeah,
Hypothetically
it will look
speaking.
like a crooked line.
And I'll call this theta what?
Theta
R.
R.
Theta R. Cool. That hard or that easy?
Easy.
Easy.
Piece of cake.
Now I am going to explain something without telling all where we're going to. And they're gonna be mesmerized. They're gonna be like, oh, okay. Alright, so I'm gonna let me keep going, right? So I have a question. I explain something very, very important here. If I were to increase the angular incidence, what would happen to the angular refraction?
They will also increase.
It will also
Will be in the
increase.
same place.
Okay, so let's see that, right? I increase the angular incidence, and as a result, what increased?
the angle of
The angle of
refraction.
refraction.
Okay, let me keep going now. Let me keep going. Whoa. Whoa.
Down there.
What do you call that?
Critical angle or something.
A critical angle.
A critical
Yeah,
angle.
some
A critical angle is when the incident ray is. How you would explain that?
Nah, look, somebody look at that and tell me, like, okay, at the
As you-
critical angle,
Oh,
At the
so I
critical
remember.
angle, the angle of refraction will be equal to 90 degrees.
yes.
Yeah.
So at the critical angle, the angle of refraction is
90 degrees.
now I'm gonna say this. You could only have total internal refraction if you're going from a more dense to a less dense, eh? All right. Oh, I'm gonna verify that. I had read that somewhere and it makes sense.
Yes, so that makes sense. Because
Yes,
the
sir, that makes sense.
because like if it was from a less dense to a more dense, and it will end up lining up with the normal instead. If like
Yep,
yeah.
that's correct. So yeah, we correct. I said that's all the correct thing. Yeah. So here what? Let me keep going now. Oh, let me keep going. Let me keep increasing the angular incidence. So let me ask you that question. If I push this even further, the refracted ray is now gonna go where? Where's it gonna go?
Inside the water. So it'll be a total internal reflection.
Yeah. And when it goes from water to water, there's a phenomenon that occurs that's called total internal what?
Reflection.
Yeah. So I would at this point in time I would call this theta R, I would call it the angular what?
Reflection.
Reflection.
And I'm saying this because and by the way, in this instance, theta I is less than C or more than C. So if all they confused, I literally take it and I push it back. So is the angle less than C or more than C?
More.
Is more than C. So if you surpass the critical angle, what phenomena occurs?
Total internal reflection.
Yeah.
So
If the critical angle is surpassed, total internal reflection occurs. So let me run through this whole process again now, just to make sure everybody on the same page. So Alit, remind me, if I'm going from a more dense to a less dense, what happened? What happened to the refracted ray?
Moves
It
away from the
bends
normal.
away from the normal.
Bends away from the normal, right?
Bends away from the norm.
Right. And you can see that over here, yes or no?
Yes, sir.
Yes, sir.
Which
Yes,
angle bigger?
sir.
Which angle is bigger, the angular incidence or the angular refraction?
Angular refraction.
And let's see the angular refraction bigger or tweaking.
No, sir,
No,
we
you're not
seeing it.
tweaking. I see it.
Okay, now here what I'm saying. If you increase the angular incidence, which angle will increase as well?
Yeah, no. What?
The angular
The
Refractive,
angle of
refractive angle.
Once the incident increase, sorry. I know what I'm trying to say, but I
Just take your time.
Take your time. But
when the incident ray increases, correct me if I'm if I'm wrong, the refractive ray also decreases.
yeah, watch. Okay. I made the angular incidence bigger, so therefore it moved further away from the what? It moved further away from the what?
The boundary line.
No, the normal.
Normal.
Oh, the norm, right. Sorry.
And if I keep increasing the angle, and at some point it will line up with the boundary line.
Yeah, it will be 90 degrees. It'll be equal
And
to 90 degrees.
and
That's
at
the
that point,
critical angle.
yeah. And at the critical angle, the angular refraction is 90 degrees. And guys, if you keep going past the critical angle, what happen?
It will be the
Total internal
internal
reflection.
angle of reflection.
You would have total internal reflection. So like we'll do a question on this shortly. But like, do you guys understand the process of critical angle and total internal reflection?
Yes, sir.
Yes, sir.
Now let me explain this third rule to you guys now. So they're saying the angle of incidence and the angle of refraction lie on opposite sides of the normal, but all lie on the same plane. So let me explain. So over here, we have the boundary plane. Now a plane is just a 2D surface. And you can imagine, like, okay, if you had like a square, okay, imagine you had a swimming pool, right? And everywhere over here will be water.
Yes, sir.
Yep.
And then all here over will be
Yep.
air, right? All here will be air, yeah?
Mm-hmm.
Yes, sir.
So the boundary plane is just a 2D version of the boundary line. Make sense?
Yes, sir.
So like
Yes,
you
sir.
see this over here? This is a 2D representation of the boundary line. This green line over here, what do you think that was called?
The normal.
Yeah, the normal.
Normal. And you see this over here?
That is
This
the normal.
this would be called the planar incidence, and this would be called the plane of refraction. Now let me ask you guys a question. The normal is here, right? The normal is here. Let's see now.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
The incident ray on this side. Where's the refracted ray?
On the
On
other side.
the plane of refraction.
On the opposite side.
On the opposite side. So I say the angle of incidence and the angular refraction lie on opposite sides of the normal, but both of them lie on the same.
The same plane? Yeah, I understand it.
Makes sense.
Both of them lying on the same plane. You see, this is the normal, but incident on this side and refracted on this side. So they line on opposite sides of the normal, but both of them are on the same what?
Plane. They're both on the same plane, yeah.
Yeah, both of them on the exact same plane. So I hope they understand it a bit better now. Because teachers rarely show students what this mean. So laws of refraction. Number 1, the normal is always perpendicular to the boundary line. Number 2, Snell's law. Light waves bend when they pass through different mediums as a result of light traveling at different speeds. 3, The angle of incidence and the angle of refraction lie on opposite sides of the normal, but they're on the same plane. Cool. Let's look at the formulas you need to learn, right? Now, guys, do you think, okay, we live on what? We live in the water or we live on air? We live on land. We live on land, right? We live on land. So what will be the medium we're seeing things through?
Less than two.
So here we're saying, right? Here we're saying we live on land. So
Air.
what will be the medium we are seeing things through?
Air.
Air. It's air. Like I mean, bro. Am I SpongeBob SquarePants? Like, am I underwater? Am I like it's air? It's air, right? I'm breathing air. So we just see through the medium air. So we would reference everything which was and air would be our like reference then. Because we just see things through air, right?
Yes.
Yeah.
So the refractive index for air is actually 1. Because we see like we just see things through air now. So that's the standard. Nothing changes. It's just 1. If you multiply something by 1, would it change?
No.
No, it wouldn't change, right?
No.
So here what? You see this? This is a generalized formula. It's one I prefer. And this works for any two mediums. Right? You would just need to know the refractive index for the incident ray, where the incident ray is. You need to know the angular incidence. NR just means the refractive index for where the refracted ray is, and R is the angle of refraction. Now this formula works for absolutely any two mediums. Now this formula that you learn in the school, it only works when you go in from, say it with me, it only works if you go in from
Air.
A to something else.
Air to something.
It only works if you're going from A to something else. The moment something changes, chaos. But I don't think CXC would do that, right? I don't think CXC would do that.
Air to water.
Air to water, once it's from air to another medium. But like I say, I prefer this formula because it works regardless. It works regardless for any condition. Ni sin I is equal to Nr sin R. But if you recognize you're going from air to another medium, this is the easiest one to use. If you want to find the refractive index, right, of the other medium. Right. Cool. So I'll take a screenshot of this. You guys can take a screenshot of this.
In this moment, I'd like to say to the people on TikTok and YouTube, subscribe, turn on our notifications.
That's what I'm talking about. Oh no, I refresh my feed and all yeah.
That's what we like to
Subscribe to
see.
Bad
Turn up those
Vibes.
numbers, guys.
Subscribe.
No, but look at the number.
Fire!
Look at the number.
Don't
Six,
worry about
seven.
the number.
Sir, we don't condone
Sir,
that
let me
action, sir.
promote
We don't
that.
condone that.
Why I keep
7
seeing that
number.
number everywhere I turn I see that number.
So your thing don't charge and you leave it plug, it's still plug on, you will damage your battery like that.
No. As a physics student, I can tell you. Well, I'm not as a physics teacher and somebody that is doing my bachelor's in electrical engineering. No, not
It
really.
wouldn't really damage it.
No, actually, no, serious
But
thing.
it
It
will
does.
overheat it.
The lithium batteries on them after a while when you leave it plug on charging. If you're not using it, that's fine. But because you're using it and it heats the batteries, is actually swell really bad.
Yeah, batteries
Yeah.
that's
Alright,
well.
you're not teacher in
I
physics, right?
hear what you're saying, and you're not wrong, but the BMS and the management systems of these modern machines can withstand that. And they have like power pass through and whatnot. So like instead of using the battery, the power could just go straight to the device. So it might be
Okay.
yeah.
I would trust the physics teacher.
I understand what you're
I
saying.
have trust, but like I lost a phone like that, so you know.
No, I understand what you're saying. I understand what
We're
you're
just
saying.
looking out for Sue. Such a nice tool.
I appreciate it. And the Apple Pencil is what needs
And
charging.
now go to ask if the Apple Pencil surviving.
Sue, You know your
Now,
Apple Pencil like to cut off on you just so.
yep. So here what? Let me give a little example, right? On how we could derive that formula you learn in school. Give a quick example. Let me just say we go in from. So let me just say we're going from air to water, right? If I go in from air to water, I would bend away or bend towards.
Towards.
And towards.
Toward.
All right, I bend towards.
Towards the knob.
Now,
Angle
question:
R.
if the angle, okay, so the incident ray is in which medium? Which medium is the incident ray in?
Yeah.
Air. Air.
Air. It's in air. So what's the refractive
Air.
index at air?
1.
Right. Okay. And we'll leave this blank for now. We'll leave this blank for now, right? Let me show you guys something. So in the general formula, it's Ni sin I is equal to Nr sin R. Okay. And so we know that, okay, as you can see, I'm going from air to some other medium, right? So if this is the case, what will be the refractive index for the what will be the refractive index for the incident ray? Since it's an air.
1.
1. So that'll just be sin I. Because where's 1 by sin I? Where's 1 by sin I?
Sin I.
One. Well, sin I. Ooh,
And if you
Jesus,
make
tired.
nr the subject of the formula, you divide both sides by sin r. Ta-da! Isn't this the formula I learned in school?
Yes, sir.
Yeah. Yes, sir.
Yeah, so that formula only works if you're going from air to another medium, which is bonds, if you ask me. I don't know why they give away that formula. What if you're going from water to glass or something like that? They're gonna do cry.
Well, I guess so, sir.
Telling you.
All right, so we just looked at all the formulas you need to know. We looked at the concept of critical angle and total incident reflection. Yeah, you guys could take a screenshot of this. I have it nicely written over here. If you go into a denser medium, the refracted ray is going to bend towards the normal. If you go into a less dense medium, the refracted ray is going to bend away from the normal. Right.
Oh, that's true.
Okay, cool. So are you ready to do a question?
Yeah.
Yeah.
Oh, and these are some more formulas you need to know, right? So, well, yeah.
You watch the boys final?
Well, yeah, see how home I did, but I was kind of underwhelming actually.
Yeah,
And
Antika.
then,
Sir, I didn't
Oh,
watch it
God.
yet.
well, I mean, it was bound to happen, right? He was bound to do that at some point.
Yeah, but it was
That's
kind of.
true, you know, but I wanted to find out. Jeez.
Why? There's some spoilers, right?
Okay,
That's why.
that's fine. That's fine. I'm sorry. I didn't never hear that. I didn't never hear that.
My bad, guys. My bad for asking.
So, here what I'm saying, guys. This is the general formula. Ni sin I is equal to Nr sin R. These are some other formulas you need to remember. N would be equal to the speed of light in air over the speed of light in the medium. We also have the wavelength in air over the wavelength in the medium. We need to know these formulas as well. These are all the formulas you need to know. Generally speaking, it's always in air over the medium. So if we're dealing with speed, it's the speed of light in air over the speed of light in the medium. If we're dealing with wavelength in air over wavelength in medium. Same thing over here. It's sine the incident ray in the air over sine refractive index. I mean sine R in some other medium. Same procedure. Right? So I can take a screenshot of this.
Excuse me. I feel if you do like a question with actual numbers, I feel I go understand better.
Don't worry, I'll do a question with actual numbers. But some of you guys were asking me about the graphs. If you're given a graph of sine I versus sine R, the gradient gives you refractive index. So it's just something to know. So you guys can take a screenshot of this. But when you have a screenshot,
potentially, it don't have to be the actual question. If it asks us to plot a graph.
yeah, there were questions where you had to draw a graph.
Okay.
All right, so are there the screenshots? Yeah or no?
Yes, sir.
Yes, sir.
Okay, cool. You got a question, huh? So, given the question below, find theta r, angle of refraction. So, I'm telling you that the refractive index of what is 1? The refractive index of what is 1?
A.
Air.
Yeah. And I'm telling you that the refractive index of what is 1.3?
Water.
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 Water. That reminds me of this coconut water song, buddy. I don't think
Water.
coconut water. I
Coconut
don't even know what.
water.
Yeah. So, we had to find for theta r. So, here what? Let's use the formula you would learn in school, right? And that formula you learn in school is really when you're going from air to another medium, yeah?
Yes,
Another
sir. Yes,
medium.
sir.
Water.
So you would learn that nr is equal to sine I all over sine r. Right, so let me explain. Over here we have the incident ray. Where's the incident ray?
In the air.
Air. And where's the refracted ray?
In the water.
In water.
Water.
Alright,
In the
cool.
water.
Now, since the refracted ray is in water, then the refractive index for the refracted ray, you see nr? That is telling you the refractive index for the refracted ray is what? What are we going to plug in? What are we going to substitute for that?
1.3.
We're going to put
1.30.
1.3. We're going to put 1.3.
1.3.
I hope you understand that, right? nr just means the refractive index for the refracted ray. Where's the refracted ray? Guys, where's the refracted ray? In what medium?
In water.
Oh,
The
water.
water. The one in
Water.
water.
So that is why I replace nr with 1.3. Hope you understand.
Okay.
What is the angle of incidence?
45.
45
45
degrees.
5.
degrees.
45 degrees.
Do I know what the angle of refraction is?
No.
No,
No.
sir.
Here, a
No,
lot
we
of
don't.
students like to cross multiply in this instance. So you cross multiply, I just doing what you're accustomed doing to not confuse anybody. If you cross multiply, what would you end up with?
1.3 sine r is equals to sine 45 degrees.
What do I have to do next, guys? It's just a maths problem at this point.
Just
Divide by
Sir,
carry
I
over
biggest
wanna
sine
find
r.
the
the
answer. I wanna find the
sine
answer.
r. The 1.3 sine carry it over.
Wait, so you're thinking to divide both sides by 1.3 sine?
Yeah.
That's highly illegal, eh? That's highly illegal. That's very, very
It's
illegal.
legal. It's legal to
Because
me. And
So
that's
you
what's
could just
important.
Boomers.
so instead of just
because wait, because sine is a function, and right now r is inside the sine function. So you can't do this madness. Nah. You can't divide by 1.3 sine and thing. Because I know you was going to do this next. Nah, that's highly illegal.
I was not going to do that next. Don't worry.
Okay, I hope not. So here what? You'd first have to divide both sides by what?
1.3.
1.3.
1.3.
1.3.
1.3.
Anytime you have to find for angle, you have to use the what trig function?
The inverse.
The
The
inverse,
inverse.
yeah.
The Now I know some of you have a sharp, so I'll just show you the easiest way to use that sharp. If you
Sine
have a sharp,
45 divided by 1.3.
add maths people, make sure you calculate that in degrees, eh? Because I know the add maths exam was the other day.
Hey, sir, I leave it in radians.
So you wanna know something? Well,
Yes, sir. I
if
appreciate
you forget
that.
your calculator in radians, it wouldn't affect normal calculations unless you're doing some with degrees.
That's correct. It wouldn't affect normal calculations, but it will affect any result involving a trig function.
Yeah, anything with sine, cos, and tan.
That's correct. So
So
let me.
I get 0.54.
So here what I would recommend writing a good bit of numbers, right? Probably write like the first 6 numbers again. So you can say 0.5439.
39.
So 1, 2, 3, 4, 5, 6. You can probably do that. That's fine. That's enough degree of accuracy. And then what you gotta do if you want to find for R?
The end
Sine
find the sine
inverse.
inverse.
Yeah, then you'll go and do the inverse of sine.
Yeah. In a sharp, you have to press second function, then press sine, and you'll get sine inverse. And then you put your numbers in brackets, and you'll get your answer.
Right? So let me
Yes.
if you guys get in,
Yes, sir. 33.0.
right? Yeah, that'd be 33.0 degrees, right?
Yes, sir.
Yes, sir.
Yes, sir.
Right, so that was that. Was it that hard?
No,
No,
it
sir.
wasn't.
No, sir.
Normal.
Sure, that is the same answer. You have cover there. Well, I
No.
would like to believe so.
No.
Yes, sir.
Let me show you the other way you could the question using the other formula, which is the formula that works for anything. So this is one way you could do it. And you could use this formula anytime you're going from air to another medium. Right? I see you have 32.95. Yeah, you can write 32.95. Let me write it to 2 decimal places now. Yeah. I prefer to write it to 2 decimal places. So that'd be 32.95 degrees.
So the actual number they give us in the calculator instead of putting it to 33.0.
Yeah, you want to write your answer to 2 decimal places.
Okay. Okay.
Monster 33250. You are expected to know the refractive index for air, which is 1. They're expected to know the refractive index of water, which is 1.30. Well, sometimes they would specify. When we do the questions, they go see. Generally speaking, they do specify. Right? Now, the other formula is Ni sin I is equal to what?
NR
Sine R.
Right, so somebody tell me, where is the incident ray? Where's the incident ray?
In air.
In the air.
In air. So what I'm going to replace Ni with?
One.
One.
Okay,
One side.
I. Where's the angular incidence? Angular incidence.
45 degrees.
45
5
degrees.
degrees.
Cool. Do I know what the refractive index of the refracted ray is?
Yep.
Oh, yes, sir.
1.3.
1.3.
Do I know what sin R is?
No.
No, so
No.
what should I do now? What should I do now?
So you could carry over the
You can point
1.3
out the left-hand side.
by the
Yeah.
both sides.
Yeah.
And yeah, then find it inverse and it good.
So you're gonna get sin R is equal to, okay, 1 by sine 45 is sine 45. All over 1.30. And yeah, you just find the inverse and they get true.
Yes, sir. That's arc sine it.
30 is there for placeholder, right?
Yeah.
Once there's no number after, the
Yep,
output
that's
has
correct.
0. Okay. I remember that
Yeah.
from maths.
Big up. Don't worry, I will make sure they get full marks on my paper once. Trust.
So I will need that.
Yeah. So
Output for a grade 2.
honestly, I like this formula a lot more. I kind of biased towards it because it does work every single day.
Okay.
And it's much faster, in my opinion.
Yeah.
Yeah, that's true. Let me take a screenshot of this.
So Ni sin I is equal to Nr sin R. I believe that's the typical way they learn it in GCSE physics.
GCSE and CSEC is the same thing, right?
More or less the same thing. Yeah.
Fine, just from England.
Yeah, it's more or less the
Oh.
same thing. It's more or less the same thing.
I thought it was from Guyana.
Guyana? What?
What?
Nikolai.
Caribbean
That's right,
country.
CXC boy.
No,
Me
no, no.
rotted.
Like I heard Chris
Remember,
Brown went on some kind of
CSEC
trip
stands for CSEC stands for Caribbean Secondary Examination
Oh my
Council.
days, Nikolai boy.
No, 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 no. Like I think I mix up. Well, I know I mix up the country, right? But I know
It's
conspiracy.
because Guyana in
Yeah.
the Caribbean.
Exactly.
Nah,
Not
it's just
geographically.
Guyana is
Guyana
part of
mix
the
up.
Caribbean.
Right,
So
right,
they will
right,
fall
right.
underneath CSEC.
Yeah. I mix it up. I know conspiracy. I went on some trip to support the students who was just not talking about that test, the NGSE or something. So what I was just not talking about.
NGSC.
CSEC.
That is not for form trees.
Yeah,
I don't know.
that's happened in Trinidad too, I think.
Yeah.
Yeah. But I
We
thought
just
that the
at least
kids out.
we just
Oh,
at least get a exam in form tree to do to see how good or what we remember
yeah.
before we go into form 4.
Big up the Guyanese one time. Which of the following scientists discovered radium? Is it Marie Curie? Marie.
Marie
Marie
Curie.
Curie.
Marie Curie, not Curry Marie.
Curry Marie.
The Guyanese people come from me,
I'll be
I'm asleep. The
laughing
Guyanese people
so
come from
hard.
me.
Yes. All right, let's go, guys. Let's go.
Yeah, so like going forward, which formula I prefer to use?
The second one you do.
The second one.
Your one.
It's less time consuming, but you'll get the answer faster.
I would. All right. Well, let me.
How's your good information, sir?
So I
Right.
know Kajiju, you know.
Damn, that's crazy.
Mary Curry, like, how did I say chicken curry?
Yeah. That's itself. So here, what? Let me tackle this question. Okay, so in this instance, guys, where is your incident ray?
In the water.
In the water.
Water.
In the water.
So I can say Ni sin I is equal to Nr sin R.
Yeah.
So here, what? Again, Ni is just the refractive index of wherever the incident ray is. My incident ray is in water. So what am I going to use for Ni?
1.30.
1.3.
1.3.
Do I know what the angle of incidence is?
No.
No,
sir.
No. Do I know? Okay, where is the refracted ray? It's in where? Where is it?
In the air.
It's in air.
Yeah.
It is in
Bends
air.
away.
So it's in air, right? What's the refractive index of air?
1.
One.
I hope they're not confused, right? NR just means the
Sine
refractive
50.
is the refractive index for the refracted ray. The refracted ray is in air. So for NR, I'm going to use 1 because it's in air. And that's gonna be sine 50. So what to do next?
Then you have to divide both
Substitute.
sides by 1.3.
Clock it, Renisha. Clock it.
So she locked in right now.
Then
Yeah,
you
boy.
have to bring it over. So it'll be sine I equals sine
Nah.
1.3.
Wait, nah.
Oh, sorry.
Wait, here what? For the sharp users, plug this into your calculator and let me know what they getting.
Okay, so no problem. Now you're mine.
Sine 50 divided by 1.3.
So
Sine
0.59.
Yes, so 0.59.
Here
Well,
what? Since you do not calculation, let me write like 6 decimal places now.
okay then.
So like 0.58.
0.5.
0.58926.
Yeah.
The reason you're writing it out the 6 places because we still had to find the inverse. So because if
we
we
still had
round
to
off,
find
it'll
the
be
inverse.
yeah.
If I use like a really rounded off value, I'll get like an inaccurate answer for the angle.
And
So
that's a no-no.
that's a no-no.
That's
So
no. You'll lose your marks.
ideally, what you would do is you would like find your answer immediately. So you'd say sine inverse of sine 50
Okay, so
Yes, so that's what
all
I was
over 1.3.
Alright. Sine
But
inverse.
I need to cater for the sharp users, right? So
Hey, say you
Okay.
could do that on sharp, eh?
you could do it on sharp, but I feel like it's a
Yeah.
lot. It's plenty work. It's plenty work. Plenty brackets.
Again, I'm gonna call a petition to rename sharp to brackets. Brackets and hard work.
Exactly.
don't
Brackets and
even need
hurdle.
the brackets, Olive.
No, you don't need the brackets. You
No.
still get the same answer.
You just
36.104.
you just press your
No,
little
what
second
what's
function and sign.
what I'm saying is, if you had to put this into your calculator, you gotta say sine inverse, open bracket, sine 50. It's actually not that much brackets, to be honest.
So
But so
no, you
generally,
don't have
those
to do
speaking
that.
other calculations is a lot of brackets.
Yeah, for sure, for sure.
Yeah, it has some calculations where you have to use plenty brackets, but it has some where it's just one you have to use.
Ollie, I never use no brackets for this equation. I always sleeping on my sharp right now.
Thank you. Tell them, Marshall. Tell them. Tell them.
Guys, when we do this calculation, subscribe, right?
Don't forget to subscribe. Hey.
One thing if we continue, right? Renisha did sound like an old person. Is just nice.
Excuse you.
Is he laughing? Is he laughing?
Hey, that wasn't no laugh. That was just a big up thing, okay? I don't laugh like that.
Let me know if you guys got the 36.120.
Yes, sir.
Yes, sir.
Yes, sir.
Clock it one time. I redeem myself. I know.
Big up yourself. I think if all the questions you about yourself, I can manage it.
Yep.
Yes, sir.
Yes,
Yeah.
sir.
Yes,
I
sir.
wouldn't knock until you try.
I can't see the screen, right?
Yes.
Well, I can't.
See any screen.
If you
Okay.
mean you're still showing you that you explained just now there, that's what I see.
Okay, good, because I formulated a question for you guys.
I'll close my eyes.
So you're using Claude?
Excuse me, there
No,
was
I'm not using Claude, I'm using my brain.
Excuse me. There's
Yeah,
a
Nikolai?
question. There's a question, I believe, before when I used to, okay, like before when I was bad at physics, there's a question that was some kind of tube, and there were angles were going in and out of the tube, and I feel that was like a trick question. If you want to go through that, I think it's either in 2025 or somewhere around there.
Okay, no problem, I'll look for it.
It has like a mirror in the tube or something.
I think so.
Alright,
I know what you're talking about.
Okay, we're all there. 5 minutes, go. Tomorrow we're gonna tackle. I finally Zoom looking real scarce, boy. Everybody leaving. Hey, boy.
So wait until tomorrow, sir.
Hey, boy. It have 133 people on YouTube though, and 22 people on TikTok. People on YouTube, all they want to be in the Zoom.
People on the YouTube, speak now or forever hold your peace.
Some
Yeah.
ways good. Some
So
ways
you
good.
gotta be careful how you saying them things, sir.
Yeah, boy. Next thing, troll coming. Coming back. I hope I'll get through the question. After we do this, I will look for the question that you said giving you trouble. So, guys, we nearly finished, you know. After this, we need to look at his lenses, but lenses will take a little while.
You, sir, if you don't mind, we could go over concave and convex lenses.
That's part of it.
till I finish.
All right, nice. Hold the answer.
Okay, so
Question,
N1,
question 2 and 3, yeah?
okay, N1 is equal to N1 sine angle 1 is
Wait,
equal
Rachel,
to
don't
N.
say, wait, yeah? Don't say any working here. Time still, we still have time. I have a question. Any of you guys doing POB too? I mean, POA tomorrow? People on YouTube,
Yes,
anybody doing
sir.
POA tomorrow?
I'm doing POA tomorrow.
What kind of mix up subjects is that?
So that again?
No, like I know, like if you're doing like in my school, if you're doing sciences, you have to choose other sciences. So wait, how
It's
you
the
have
same at my school, but I'm doing POA and POB along with the sciences.
I mean, I'm not doing all the sciences.
Yeah, I did the same thing.
I have a question to ask.
Sure.
If the place in a all science class, right? Would geography really count as a science?
Say that again?
Would geography really count as a science?
New geography is a science.
Okay, just making sure. As the school I went, we were only allowed to pick 6, and 3 out of them it was split with other subjects. So even if you wanted to do all the subjects, you could have only choose like about whichever one that it slash with.
And which school is this?
Success Lavendale.
Okay.
So mine's is just give you all the science subjects, but not really all. They'll give you geography as an option, but I didn't choose that because I was curious at technical drawing.
I
I was
didn't
curious
choose.
about geography, that's why I choose it.
Well, my school does full sciences, but like we have a split with like Spanish PIT, and then my school it gave if the teacher was willing to do the work, you could have done an extra subject. So my school didn't have TD, so I ended up doing visual arts.
Okay.
I wanted Spanish, but I didn't choose Spanish. I ended up doing social studies. And I was curious about the geography, so I didn't choose chemistry. But anyway, I take it. I
I don't
still
know.
had was to come back and do chemistry
Did
anyway.
I take chemistry because this past paper
Chemistry
for
yesterday was
2026?
chemistry
Yeah.
yesterday
Chemistry
was
still
cake.
come back anyway, because I still
Chemistry was
have to
cake.
take.
I don't want to be rude or
This
anything,
year?
guys, but we have to
Continue, yeah. There you go, sir.
Of course.
Yeah, sir,
So
Studying
just
at
say the word, you know.
physics.
Yeah, sir,
Alright,
just say the
you
word and
ready
we
to
know
hear
right.
the
keep
answer
going.
now?
Of
Right.
course.
So wait, we gotta label everything first. This blue line over here
Yes.
is what? What's your money blue line?
The
Incident.
incident rate at 30 degrees to the
No.
normal is
Wait,
inside the
no, sir, at the
water.
The
boundary
boundary
line.
line.
That's the
That's
boundary
the boundary
line.
line.
That the border.
It's the boundary line.
Yeah.
Yeah, that is the boundary line, of course.
Why is that the boundary line? Well, over here is water, and over here is air.
Yeah, but there's
Boundary line.
yeah.
And this over here is the normal. This was the hint, because you know the 90 degrees
Mm-hmm.
each other all the time. Right? Cool. Hope I understand that. What would I
Yes,
call this? This is the what ray?
Incident ray.
Incident ray.
Incident ray.
It's an incident ray.
Yeah, because it can come in. What would I call this?
Angle of incidence.
Angle of incidence.
Angle of incidence.
What would I call this?
Angle of
Angle of
refraction.
Refraction.
What would I call this?
The
Reflected.
refracted ray.
Refractive ray.
Cool. Can I it?
Yeah.
Nice. All right. I will let Eden help me with question 2 and Renisha will read myself question 3.
Okay.
So Eden, which formula I want to use?
So, I know prepared. My word. No comment.
All right. Well, here what?
So,
I go keep up, right?
alright.
Easiest formula to use is Ni sin I is equal to Nr sin R.
We don't have the sin I over something
Yeah.
or something's equal to.
Ni is equal. This is the one you typically learn in
Oh yeah,
school.
that yes, yeah, sin I over sin R.
Yeah. Now that formula comes from this. This is like the mother of all formulas. This is the general formula.
Okay.
So I'm gonna show you how we're gonna use it, right? So Eden, where's the incident ray?
Incident ray, on the water.
It's in water, right? It's
In
in
water,
water.
yeah.
So if the incident ray is in water, then the refractive index for the incident ray is gonna be what? So let me run that back again. So Eden, the
Yeah.
incident ray is in what medium?
Water.
So will I be using Na refractive index at A, or will I be using NW refractive index at
1.3.
Right. So I'm gonna plug in what for Ni.
1.3.
Right, because we're talking about the incident ray there. So I'll say
Yeah.
1.3. Do we know what the angle of incidence is?
30 degrees.
Right.
Is equal to.
Now be careful, right? So NR, we're talking about the refractive index of where the refracted ray is. The refracted ray is in what medium?
In air, so it'll be 1.
So I will replace that with 1. Yeah. We don't know what R is. They want me to find R. They want me to find
for R. Yeah.
So 1 by sin R is just what? Where's 1 by sin R?
One sin R. Oh, it's just sin R.
Just sin R. So Eden, what to do next?
You gotta multiply 1.3 by sin 30.
Say that again?
You gotta multiply 1.3 by sin 30.
Yeah. Again, 0.65.
The sin R is equal to 0.65. And to find R, you gotta do sine inverse.
People on YouTube, people in the Zoom, how much of you guys got through the question?
Yes. Oh, yes, sir.
Yes, sir. We got that.
So the answer was 40.54 degrees. Yeah, that was easy or hard?
Yeah, that was real simple.
Yeah, it is real simple. You just have to, like, the hardest part is recognizing what NI and NR is. But I mean,
I just had to know my formulas. Has a
but like, NI,
Yeah.
you're talking about the refractive index of where the incident ray is. The incident ray in what medium?
I knew water.
So I will replace that with
The 1.3.
easy peasy lemon squeezy.
That's
NR.
the answer I was gonna say. Because that's what I
Right.
get.
All right, Wood. Well, let me give you a chance to help me with question 3. All right, so Renisha, in question 3, they want me to find for NR. So Renisha, tell me, what's the formula to use?
Okay. So the formula to use is N.
Wait, yeah. Kisses 5092. The first question was to find for angle R, which is this 40.54 degrees.
Yes.
I'm talking to somebody on YouTube. Kisses 5092. Kisses 5092. Weird name. Yeah. So Renisha, what formula to use?
and I sine I and R sine R.
Right, cool. Let me plug in the information we know now. So Renisha, tell me,
Okay.
where's the incident ray? Where is the incident ray?
Water by the
Right,
water.
water. So we're gonna replace Ni with what?
And W
Which is?
water. Well, 1.3. Sorry. I was
Right,
supposed to
1.3.
say the number. I
Yeah,
was
you're
supposed to
locked in,
say
you're
the
locked
number.
in, you're locked in. And where's I? What is I?
I is 30 degrees.
Do we know what NR is in this question?
Mm,
So in part,
what
in question 3, what do you want me to do? What do you want me to do?
they wanted us to find for an R?
So do we know what NR is?
No, not
Nah,
quite.
nah. Nah, we don't know what that is. I had to write it back. Then sine R. What is R?
R 40.54 degrees.
W in the chat for Renisha, boy. W in the chat for Renisha. All right, so Renisha,
Yes,
what
sir.
is 1.3 sine 30?
1.3 sine 30,
Mm-hmm.
0.65.
Right, 0.65. So we have 0.65 is equal to NR. And what is sine
NR
40.54?
sine 40.54 is 0.64997.
Which is essentially what?
That would be 0.65.
Yeah. And now, if I want to find for NR, what I had to do on both sides?
Divide by 1.3.
Nah. So here what? If I want to find for
Okay, that
NR,
part cut me off.
all right. If I want to find for NR, right?
Yes.
I want NR to be the only thing here. The only thing. The only thing.
Substitute.
Not substituted, finding for NR. So
Okay.
we have
Fine.
NR. We have NR multiplied by 0.65.
Okay.
So what would I have to do to get rid of the multiplied by 0.65?
You'll have to divide
I'd have to divide both sides by
0.65.
yeah, because you wanted to cancel off to leave you with what? Leave you with what alone?
And R.
Which is what we want to find for.
Yeah.
So where's
Basically.
0.65 over 0.65?
1.
1. And earlier, this makes so much sense. Because
And
I
R is
just
equal to 1.
yeah, watch. Because okay, where's your refracted rate? Your refracted rate is in what medium?
Air.
What's your refractive
Air.
index at air?
1.
Yeah.
Ah.
So I just reversed engineered the question. I'm not sure if you guys realize, but I utilized the answer from the last question here.
So not
Yes,
only
you're
that,
right.
the
You're
in
smart.
the
You're
No.
third
smart.
part, how you give us angle R is literally the answer for part 2.
Yeah, yeah. Yep.
So,
Yep.
so how
But
was how should I
I
do?
thought because the angle R was the same thing that I didn't need to do the work in because it's
No,
the
no,
same
you needed to really work
equation.
it. It was just like a reverse engineer. Like I just reverse engineer the question. So you guys
So
will
how
see
do
that
I do?
no matter like where how you look at the question, it'll work out either way. So like over here, you find for R, and over here, I use that to find for NR, which we know is 1. So everything just loops back upon itself and completes that full circle.
Yeah,
Yeah.
so I feel the biggest problem in physics is overthinking because I get the one and I was like, I don't see how give me back this now.
Yes, sir. For real. The biggest problem in physics is overthinking.
Well, that's why we're trying to address that tonight. All right. Try not to think. So here what?
Could you just plug in the stuff, like the sign and everything, and you still got a new one?
Yeah, like okay. If you want and you want to work this out directly, watch. You could like plug the whole thing into your sun wave Casio cross whoever. So watch. 1.3 sine on 30 all over sine 40.54. If you round that off the two decimal places, what would you get?
1. And
Yeah,
that's
so
what we
that's
get in physics.
Yeah, the
Yes,
scientific
sir. That's how
calculator
I
gave
was
you the
taught to
answer
do it.
already. The
yeah.
sharp you had to do it. You had to do more work than that.
And so,
Nobody.
excuse sir.
Yeah.
That's what we gain in physics, sir.
What was that?
Don't know the code.
Let me get
One,
it
the
to
one,
him
sir.
again.
Oh,
But
One.
thank you very much.
boy, I really
Yeah,
see.
one. Is that sign? Is that sign?
That's sign. That's
Give me a
I see
sign.
Kyle has his hand raised. Kyle Bramble. Talk to me.
So it's Kylie. But I was asking, right, how come the incident ray in the water?
All right. Where does the ray look like it's coming from? So like, okay, what goes towards this point? What goes towards this point? Which arrow goes towards that point?
The incident ray.
This one. And so that's why I call it the incident ray, because it's incoming. It's coming in. You know what I mean? Like
Yeah.
going towards the point. Let me show you some more examples, right? Watch. Look at this example. What's coming in there? This one. So that's the incident ray. Watch. Look at this one. What is going into that point? This one, incident ray. You understand? So like watch. This ray is going in. This ray is what? Look at the direction of the arrow. That ray is what?
The refracted ray. Oh, it
Right,
coming
but
out.
I hope you understand what I'm trying to say. Like the one that comes in is the incident ray. Incident ray. Yeah,
Yes, sir.
no problem. Nikolai, let me see if I can find that question you're talking about.
So you're doing any more questions like this, or this is the last?
Yeah, I do know. I got no more questions like this. Don't worry.
The last one is with the 90 degrees. So I guess and that is probably a question we could go into one time.
Wait, yeah. This was a question from 2026. Really easy.
January?
Yeah. Are you ready to tackle this?
Yes, sir.
Alright, really easy, and I'll
Yes,
just
sir.
already. So we can do this. Here, what? In the meantime, could somebody find the question that Nikolai was talking about to save some time? Please.
Yeah, I'll look for it.
Alright, cool. So, who wanna help me with this question?
Me, sir. If nobody
Alright.
else will.
Alright, so Renisha, give it a read fast. Yes, so
Okay.
Nikolai to some
Figure
face,
5
like
shows
Nikolai
circular
was like
wavefront.
Nikolai was like, bro, what do you mean by that? Yeah, Brandon?
Figure 5 shows
Oh, wait,
circular
wait, Brandon
wavefront.
was saying something. Brandon was saying something. Yeah, Brandon?
The question is on the 2023 question.
That's in 2023, what, January or May?
May June.
May, June? Okay, no problem. We will do that question next. Fun stuff.
Figure 5 shows circular wavefronts produced at the center of a wave pool. 2 paddle boats, P and Q, float on the water in the pool. Boat P is on the crest of a wave at the instant shown in figure 5. The
Right,
2
so
dots.
Risha, you know how like waves would have like a crest,
Yeah.
then they would have a trough. So the crest is in max, is like the top of the wave.
The top of the wave, like the point.
Yeah. So in figure 6, a snapshot of the displacement distance graph of a wave at a particular instance is shown. The wave takes 0.95 seconds to move from boat P to boat Q. They want us to define the following terms associated with waves. What's the wavelength on them? Renisha, tell me fast. What's the wavelength?
The wavelength on
What's
the
the
on
definition?
the graph, right?
No. Like, okay, like the definition of the wavelength. What's the definition of the wavelength?
Do this one, I know this one. This one entirely from my head.
Like gas up Renisha in the chat. They gas
Just
up
take
Renisha in the chat.
oh my God, just take your time. Think about it. I believe
So
in you,
we could
girl. I
give
believe
share
in you.
hints.
Yeah, let's take a share hint.
Trough.
So go
Renisha,
back
the
to the graph, you might
crest
get
and the
it.
trough.
Crest and trough.
The crest and the trough.
So go back to the graph, you might get it.
Right. So, Renisha, I have a graph here, right? How would
Yes,
I
sir.
find the wavelength? How would I find the wavelength?
I was going to say that, wouldn't you have to read the graph?
Okay, but like, what do you mean by that?
How I would read it? Between the I know what I'm trying to say, it's just that I can't place my words properly. I'm trying.
Take your time, Renisha. Think about it.
Okay.
You say, okay, you say you go and read the graph, and we give you a hint with the crest and the trough. Just think about that for a second.
Wait, so like, Renisha, what do you call this? What do you call this?
The crest?
And what do you call this?
Crest. Oh, so you have to read where it stops,
Okay, what do you mean by that?
where the crest ends at.
So, finding distance, someone tell me where you think it is.
Okay. So both P's at the bottom.
Now, we just studying both P. We just studying, we just focused about, okay, so we're running low on time. I want to,
No, sorry, sir. I'm sorry.
that's okay.
So
That's okay.
better, just tell her it.
That's okay. That's okay. Right?
So I think she probably getting mixed up with the formula, you know.
I'm not sure, but Renisha, let me run through it, right? So,
Okay.
what exactly, that could be the case. She could be getting tired with the formula, right? Renisha, let me give you something to take a screenshot of.
Okay.
Renisha would have come a bit late, so she would not see when we went.
Yes, I was late. I was in biology, so
All right. Take a screenshot of this.
okay.
Renisha, everybody supporting you on the YouTube chat, you.
Well, thank you.
Yeah,
Love
buddy.
y'all.
You know what to say about that?
What's that?
The same time when she was talking, she was quarreling with them, you know.
I was no thinking that.
Y'all,
No,
y'all. All you
it's
ever
all
hear
love
anything
and
all the Caribbean parents say that is both here because they love you. Okay? Right.
yeah,
Renisha just cracked me up, buddy. All right.
I didn't think of
Okay.
So,
So
Renisha, what's the wavelength?
yes,
Now that you have the definitions there.
the wavelength. Hey, with that screenshot going, boy. All right. So the wavelength is the length between two successive crests or
Trough.
troughs. Right.
I don't really sure. I don't know why I have a laughing, you know. I don't know why. But people will think that I'm a bad teacher and as like laugh at students and But I doesn't. I feel like I
Oh,
very
sir laughing at
understand.
my joke only. Sir trying to help me here. Don't make the
Yeah.
man feel bad. He trying to help me. If he didn't have patience, he would have told me it's best you mute your mic and don't say anything again.
So did I just saw Renisha's me and Renisha in the same bio chem everything, and that's just how she is. She make everybody laugh right through.
So the length
Thank
between
you.
two successive what?
Trouts or crest, whichever one is suitable for this.
Crests or troughs? I feel like I spelled that wrong.
No,
Let's
sir,
see.
you spell it correct.
You sure?
Yes, I had a screenshot of evidence.
Okay.
No, take out the 8.
You sure? Like I feel like that age
Yeah.
was a bit there, you know.
No, but literally, I had the age in it.
I'm gonna look up the spelling.
But what if you spell it wrong twice? That's the thing. I can't help.
Oh
I
yeah, that's the
dyslexic, so
thing.
don't ask
Somebody
me.
check it now. I do a
Oh, I spelled it
self-feedback.
correct. I spelled it correct. I spelled it
You
correct.
see what I
Thank
tell
you.
you,
Thank
sir?
you. Yeah. Ah, nice. Okay.
And the other one that asks for is period. Time
Period.
taken for one complete oscillation with S in brackets. I think the S is for seconds.
Yeah. But like for those of you guys that are new to math vibes, like I understand most of the Caribbean is real struggle with science subjects, you know, like I understand. So like I trying to be as patient and as like guiding as possible. Because a lot of students still get the opportunity to like kind of like they really get the opportunity to have a safe space to like take the time. Everything is like real fast paced. So that's what I'm
Not
trying to
only
do.
that, some schools, the science class, like the intensity and the pressure. Some people, if they don't understand, they wouldn't say anything.
Yeah,
Yeah,
I don't
they would be frightened.
yeah, and I don't want that.
And you see how you does like give real life examples. Like it wasn't like that in school. Like, you know, if you understand what I'm trying to say.
I know school
Yeah,
sucks. School sucks. Yeah. I know guys, don't worry.
6 cruel hours of our life.
So we have a crest and a crest here, right, Renisha?
Yes, sir.
So what's the definition of wavelength again?
The definition states the length between two successive crests. I would say crest. I would say
Okay.
crest.
Or troughs. So like here
Or
was here, right,
troughs.
Renisha? So
Yes,
like
sir.
this is a crest over here, it going down, then it coming back up again. So this is another crest. So this is what I mean by successive crest. So if I wanted to find the
Ooh.
wavelength, I would just find the distance between these two. That's why they was hinting here at crest and trough and thing.
Oh, thanks, guys.
So Renisha, if this is 4
Yes,
and
sir.
6 here, what do you think will be in between
5,
and over here?
11.
So what's the distance between 5 and 11? Get to
The
it.
distance.
Between 5 and 11.
Just now, sir, I have flying here. I have flying. I pay no more extra 2 4s. Ooh, sorry.
Wait, give me a second.
6.
Wait, yeah, wait.
Just do it. Okay.
I know. I thought for a second I thought it was like you can do it, but then I was like, no, it's like it's just do it. Yeah. So
Okay.
it's 6. It's 6. Now that's not the only thing you could have done. You could have also looked at it. You could have also looked at two successive what? We looked at two successive crests over there. We could also look at two successive what?
Troughs.
Troughs. Would I call this a trough? Okay,
I
so you see
think
how
so.
you see how crest is the highest point?
Oh, the troughs would be the lowest point.
Yeah. So like, would I call this a trough?
Yes, sir.
Yeah. Right, these
So
are
you
tough.
know what between 6 and 8?
7.
Yes, 6,
6.5.
7.
6.5. That is what's passing through. That would line
Right, so
passing.
Renisha, over here
Yeah,
we have 2.
6.5.
Over here we have 2, and over here we have what?
8.
What's the difference between 2 and 8?
The difference between 2 and 8 will be 6.
Cool, so the wavelength is 6 what? What are you measuring distance in?
Distance 6 meters?
Yeah, 6 meters. W in the chat for Renisha. Right, so
Yay!
yeah boy. Using figure 6 on page 9 and or the other information given, calculate the period of the wave. Okay, no problem. So in the question, well, we just find the wavelength. What was the wavelength, guys?
6.
6, sir.
6 here.
And we need to find the period of the wave. So in the question, they said that the wave takes 0.95 seconds to move from P to Q. Is that nice? I like how they do this, boy. I like how they do this. So I have a question, guys. If it took 0.95 seconds to go from P to Q, that is how much of the full oscillation? How much is that?
Half.
That's half. So what would the
Half.
what would the period be?
Half of 6?
Nah. So here what I'm saying, guys. It took 0.95 seconds to move from P
Oh.
to Q. Now, let's look at what period is. Period is the time taken for one complete oscillation. But when you read the question, you see that this is 0.95 seconds. And now, if you look at the time in between, this is really how much seconds? I'm not saying seconds. This is really how much distance?
3 meters.
It's really 3 meters.
3 meters, literally. From 8 to 11.
And that is half what? That was our half of?
Half of our oscillation.
Half of
Exactly.
our oscillation.
So if I wanted to find the period, right, which is T, that would really be what?
0.95 multiplied by 2.
2, yeah.
Yeah.
Wait, so how you get it 3 meters?
All right. So over here, 8, and over here, 11. So you see this segment over here? What's the difference between 8 and 11?
3, so okay, thanks.
So like this 0.95 seconds, it's really 3 meters, right? But we just learned that a full wave is how much? How much meters?
6.
So you'd have to multiply this time by okay, so the 0.95 corresponds to half of the full wave. And so to get the full thing, you have to multiply that by 2. Any understand that? Or nah?
Excuse me,
Yes, sir.
more. I'll ask where you get the 2 from.
Where get the 2 from?
Yes, sir.
So guys, period is the time taken for one complete oscillation. That is what it is. One complete oscillation. Now, one complete oscillation happens in how much meters? Somebody tell me that. Kimura, one full oscillation takes place in how much meters?
6.
6. In 6 meters, yeah. And they're telling us that from P to Q was 0.95 seconds, right? And coincidentally, how much time did that take? Well, it took 0.95 seconds and it was what distance?
3 meters.
And we know that one full oscillation is how much meters?
6.
So okay, this will be how much of our oscillation?
Half of it.
Half. So we gotta multiply by
2.
you understand?
Yeah.
Nice. You
So
okay?
when you multiply,
Wait, Kimura, you okay? You're sounding a bit energy, a bit.
Well, well, yeah. 12 o'clock.
12 o'clock? What? Although that light
yeah,
would
it's
that light
12.
would 12 nothing.
12:06.
12 nothing. 12 nothing, bro. So I hope all you understand is 2 by 0.95. What's 2 by 0.95?
1.9 seconds.
Okay, how much will I figure this out? Be honest.
Maybe because this was like the other question we do before, except they had given you the total and we had to find for one.
Yeah.
Yeah, I would have figured it out as well.
I felt like I would have fall through with it after I was explaining the definitions and whatever.
But now you know the definition. Don't forget it.
No,
Don't
I
forget it.
won't. I won't.
Trust in it. Right, so now we had to find the frequency of the wave. So Renisha, what's the formula for frequency?
Okay, okay, okay. I got this one. I got this one. F is equal to lambda.
Nah.
Lambda. No,
Renisha, scaring my Loki. I'm a little concerned.
Take
so
deep
I'm not
breaths.
scaring
Take,
you.
no. Take deep breaths and then think about it.
Renisha, when you get the chance, that screenshot, all them definitions and thing, you can say it 10 times. If not, write it 10 times. You will remember.
You that penance what I was doing.
Yeah.
Okay.
The difference is you gave yourself penance.
Nikolai going on, right? So I asked Nikolai what the integral of sin x is, and he keep telling me the wrong things. So he gonna write this a million times. Nikolai, was he integral of sin x?
I'm not studying that much right now.
Someone fast, Nikolai. Someone fast, Nikolai. Nikolai, someone fast. Nikolai.
No, which one it was? Which one for the geometric or the
No, this is
arithmetic?
for integration. This is for integration, Nikolai. Someone fast. Have you at gunpoint right now?
Cosine.
If I get,
I can help him out.
if I can say it, he has to do it. He has to do penance.
Oh,
alone.
minus
know.
cosine x. Minus cos x.
My days.
Minus cos x plus c.
Because now I'm going to say, Paul, you know the feud music that is be playing bum, 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 bum. That's
Yeah.
literally what's going on.
All right, we had to move on. So frequency is 1 over period.
So
And
wait. I will say it.
all right.
Frequency is F is equal to V.
No. All right. So the formula we're
I
gonna
feel
use here.
like if Renisha learn her definitions, she would be able to know the formulas.
Yeah.
Wait. I was saying that before, but I wasn't sure what I was saying it for.
Oh my days. Yeah, where's 1 over 1.9? We gotta move on. Because it's a
0.5.
Wait again. So 2 decimal places. Only we need to get
0.53 rounded up to 2 decimal places.
Yes,
0.53.
0.53.
So I'm so sorry for wasting your time.
You didn't waste my time. It's okay.
Yeah, but still, why you never put the 5, like 1.95?
We can't forget the unit hurts.
Wait, 2 by 0.95.
So it's 1.9, yeah. That wasn't a 5. That's a S, I think, for seconds.
Oh,
Yeah,
okay.
this is because it's periodic time. Periodic time is, like time is measured in seconds. So it's 1.9 seconds. Yeah, boy. Everybody
So,
okay? Everybody get through the 0 point.
I feel it's probably because I'm sleepy or something. Yeah. What I know. I'm aware of them.
Okay. I wish you the best. I'll say our prayers for you tonight. Alright? So we had to move on, right, guys? We had to move on. What is the speed of a wave? How would I figure that out? Granted, I have wavelength and I have frequency. Anybody?
Wouldn't that be V is equal
E
to
equals
lambda?
F lambda.
E equals
lambda.
F lambda by lambda.
Right. So the frequency is 0.53 and the wavelength is what?
6.
Well, boy, what you get for your final answer?
So I can answer this one.
Sure.
So the answer we get in for that, we will get 3.18.
Boop, 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 boop.
Yeah.
The units.
Units.
Yeah, 3.18. And what's the units, Renisha?
Would it be S for seconds?
Nah, finding speed.
Oh, speed! Gosh, boy,
Yeah.
why I had to go and do this?
Which is the same as velocity.
Right. So we are giving sorry, we had to move on, guys. We had to move on. So speed is just meters per second.
Meters
Or
per second.
you could say ms minus 1. But
Sir,
You
I
know
have a
which one would
question.
have come to my mind first? The one with the MS minus 1.
those are correct. So you guys would I get it correct? How much of you guys would I get the full marks?
Me, sir, me,
Yes,
sir.
Okay, good.
Me too.
All right, so let me tackle this question, huh? Nikolai, let me do this question first, huh?
Okay, it's a
That's
student.
okay. We don't read all of that. We don't read all of that. That's small things. So the student measures the angle A in air, and angle G in glass, and records the results as shown in table 2. Use the data in table 2 to calculate the refractive index of glass. Okay, no problem. So we have to calculate the refractive index of glass. And they're telling us to take the refractive index of air to be 1. So Nikolai, let's label this quickly. What's the incident ray?
The incident rate is G.
All right, so this is the incident. And what would this be?
Refracted ray.
Kylie, you understand why I call this the incident ray?
Yes, sir, because the arrow going in from the ray box.
Right, correct. Cool. Yeah, Nikolai, we know that the angle A is 48 degrees. And we know that angle G is 27.5. And we want to figure out the refractive index of glass. No problem. So Nikolai, what's the formula to use?
Ni sin I is equal to NR sin R.
Right, so where's the incident ray?
In the glass.
Do we know what the refractive index of glass is?
No.
No, so do we know what Ni would be then?
No.
Nah, so how to write back Ni? Do I know what the angle of incidence is?
Yes, sir.
What's the angle of incidence?
27.5. Wait, isn't the refracted ray the outside one? And they want you to find the refracted ray?
They want us to find the refractive index of glass.
Refractive, that means they're going outside.
All right, so okay, so the refractive index is Ni. Is is
Okay.
N.
Alright.
Right. So let me explain it back again. So Nikolai, refractive index, they're not talking about here, no, Nikolai. They're not talking about there.
Okay.
Refractive index is given by N. So let me explain it. So Nikolai, on this side, we're working with the incident ray.
Yes, sir.
So this would be the refractive index. For the medium, the incident ray is in. So where's the incident ray?
In the glass.
Okay, if the incident ray is in the glass, then we replace that with the refractive index of
The glass.
Do we know what that is?
Yes, sir.
No, we don't.
Oh,
Watch.
no. My bad. Sorry.
They want me to calculate the refractive index of a glass.
Yes, sir.
So if you want, we could probably call it NG. Do I know what the angular incidence is?
Yes, sir. 27.5.
Do I know? Okay, NR. Where's your refracted ray?
1.
Right, but where's your refracted ray? Your refracted ray is where?
Yeah. In the air.
If your refracted ray is in air, what would NR be?
1.
Correct. And what would the angular refraction be?
48.
Right, so Nikolai, I had a find for NG. How are you doing that?
Divide by sine 27.5 to just get NG on one side. And you
I'll
have
can't tell me this hard. The answer is right there. I'm gonna follow okay with this one.
Yes, sir.
Yes, sir.
So plug that into your calculator. 1 by sine 48 is just sine 48.
I got 1.61.
Y'all they get 1.61 as well?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Cool. Cool badness. Alright, so Anolia, how much marks is that? At 3 marks? That was not a hard question. Yeah. That question was actually very easy. So Nikolai, do you understand that NI is just the refractive index of wherever the incident ray is?
Yes, sir.
So where was the incident ray?
In the glass.
So NI would represent NG.
Yes, sir.
Alright, people in the Zoom on YouTube, are they okay?
Yeah, I'm okay.
Sir.
Yes,
Yes,
sir.
sir.
Alright, let me see if I can find that question from 2023.
I think it's the second, is the third question.
June?
Yeah, mid-June.
This is January.
So we still going on do lines?
Yeah. I crazy, you know.
So I
Maybe
feel
I
like
should.
I wanna redeem myself on the lens question.
Okay. Do I have June 2023 as a question?
You know what I admire? How she's not giving up. That's good. We all have to aspire to do that.
Because I can't.
Exactly.
I literally set back myself already. I can't
No,
set
like
back myself no more.
you have to do what you have to do to succeed. I
Yeah.
rate it. I rate it.
No, but I just saying, because like somebody else after the first few times that I said nah and just call it a day, but she's still going, which is amazing.
Yeah,
Thank you.
that is a powerful mindset.
Right. So you had a 10, you're either saying it 10 times or you're writing it 10 times. Remember that.
I will.
Why don't I have June? And so make it someone June 2023. I don't know why I don't have that. Anybody can send it to me?
Okay, fair
Fast.
enough.
Like fast.
So you could, well, when we're going into a break, I'll just send it to you one time and we'll go back to it. I don't want to waste time.
No, we're not there, boy. Wait, I think.
It's
Give me
all
a
gonna
second.
send it. So I'll send it now.
Alright, send it to me fast.
Saying if I with everything.
Send it to me.
It's sending, hold on.
That's like somebody sent me the maths, the 2026 June maths, and it was 102 megabytes. I was so confused.
Yeah.
Ahmed, you in class? I know Ahmed in class.
You get on WhatsApp?
Yeah, I get it on WhatsApp.
I send it
So
The PDF
wow,
with itself.
within the first few minutes after we finished the exam, you just wanna wonder how them paper has end up on the internet already.
I don't. I have seen what Nikolai was talking about.
I think that was like in the beginning, like in question 2 or something like that. It's like a glass, it's like a tube, and it have like lines going like up and
So
down.
Ah,
is question 3 part C.
is 3C, but I'm not seeing what Nikolai talking about.
Yeah?
Nikolai talking about this?
No, not that.
No,
Yeah,
no.
It's like a tube. And it was doing with the same critical angle, but like when I was bad at physics, I couldn't see that. So when I find it, I'll just send it to you, but let me continue in the meantime.
Okay. Okay. And if you have any questions here, could use me. I have a bunch of questions I could use. All right, there we go. We continue. Let me get back on track. Questions out there. Anybody want to help me with another question?
I
Yes,
don't
sir.
mind, sir. Oh, never mind.
Yeah.
Well, this is more so like a review, right? Um, in an experiment to investigate the refraction of light through a glass block, a student produced the result shown in figure 2. Draw the path taken by the ray through the block. Now, in this question, you could see that we're going from, well, what's over here? Somebody could tell me what's over here?
Air.
Am I going to where?
We're
Water.
going to the glass block.
Oh, glass, sorry.
Yeah,
Sorry.
glass. And so, wouldn't this be the boundary line, guys?
Yes, sir.
And
Yeah,
if,
that would be the boundary line.
right, this is the boundary line. And this over here would be what?
The normal.
No.
Normal.
Now, if we are going, somebody remind me, if I'm going from air to glass, I'm going from what to what?
Less dense to more dense.
Less dense to more dense.
If I'm going from less dense to more dense, what do I do?
Goes towards
Even
normal.
towards the normal.
Go towards
Right.
the normal.
So when I'm doing this, I need to show that this angle here is a bit smaller, right? You need to do that.
Yes, sir.
Yeah.
Well, I mean, you're just connecting here to here. I mean, you're literally just connecting here to here. Like, you really don't have much to think about. Like, you're literally just connecting here to here. And Ollie would probably realize that, you know, you have a alternating angle network here. You're probably seeing that. But then that would be same. Are you seeing that or no? Are you seeing what I'm talking about?
Yeah.
Yes, sir.
Yeah,
The
yes, sir.
alternating angles. Yeah.
Yeah. But this question was easy. Draw the path taken by the ray tree block. Who am I talking to? The
There's any.
okay, I remember who I'm talking. I just forget his name. All right. So you would not have a problem drawing this, right? Yeah, now 1 mark, right?
Yeah, I'm getting that 1 mark, sir. We did that as a lab.
Okay, good. So use the graph to complete the table below. So they already have the graph for us, so I guess I could quickly do this question. After this question, I want to do the question with Brucey Shark, and then we're gonna move on to lenses. We might go probably to like 2 o'clock and call our night.
Sorry, I don't mind. There you go.
Is that normal?
So no problem. I don't mind staying until 2, you know. I
That's
stay
good.
Sir,
here until I
sir,
get that physics right.
sir. It was Jan 2018.
Oh, Okay, well, we can do that. Hey, I here to help all, you know. I will stay here and help all you if all you need me to. So I'm not going. Alright, so Mrs. Mark, I have to get back to me, but that's fine. I get a elixir, you know what I mean? It's fine. I now realize you TikTok even on.
We
Oof. Go live on TikTok, boy. I forget TikTok.
so I'll send the document one time.
I think I have that one though. Alright, so let me do this quickly. Use the graph to complete the table below. So we have a graph of sine theta 1, sine theta 2. Just curious, do you think sine theta 1 is the angular incidence or the angular refraction?
Incident.
I
Right.
think it's the angle of
Incident.
incidence.
And over here, what do you think sine theta 2 is?
Refraction.
The angle of refraction.
Now, just some foreshadowing. When you find gradient, isn't gradient the change in y over the change in x?
Yes, sir.
Yes.
Now, on the y-axis, we have sine theta 1, yeah, sine theta 1.
Yes.
And on the x-axis, we have sine theta 2. Now, granted that we're saying that this is sine I and this is sine r, you effectively have sine I over sine r. And that we know that will give you what?
The refractive index.
Yeah, refractive index.
Right, you must think about all of these things. So, okay, they want me to find sine theta 1 when sine theta 2 is 0.11. So we're going to go to sine theta 2 and we're looking at 0.11. 0.11 looks to be right here. Devani, let me know if you've seen
Yes,
that.
sir. Yes, sir.
Read off that for me. Tell me what I'm looking like.
That's looking like 0.155.
Not quite.
Or
This could be 0.15,
oh,
0.16.
0.165.
Well, let's see, that's or not.
Yeah.
0.165. All right, then we have 0.23. So we're going to go on sine theta 2. I'm looking at 0.23. 0.23 would be over here. What are looking like, chat?
That's
I will
looking
have asked.
like
I was gonna ask Renisha.
Okay.
Renisha, what are looking like?
All right.
Renisha, you could do it. You could do it, Renisha. You can do it. Do it. You do it, Renisha.
Trust in yourself. Don't
Zero
doubt yourself.
point. Zero point
Take your
three.
time.
0.36.
Nah. It was close though.
0.35.
Yeah, 0.35.
I was one number off.
Oh, what? Okay, watch right. So we have 10 divisions, and so we have 10 divisions, and that's equal to 0.1. So one division would be 0.01. And so like this is 0.31, 0.32, 0.33, 0.34, 0.35. Right, so that's
Okay.
0.35.
Okay.
All right, Leon, help me with the other one. So if it's 0.50 on sine theta 1, gonna go there. I'm gonna go on sine theta 1, 0.50.
Bring it across and bring it down.
So that again?
Yeah, bring it down.
Bring it down, right? What am I looking like?
Alright, 3.3.
All right, 0.33.
Yeah.
All right, 0.43, we're gonna go on theta 2. 0.43. All right, what am I looking like?
0.65.
This feel like so much work, but hey, Ollie, this is like It's the easiest 8 marks you'll get, but it's not really easy 8 marks.
So I could try again.
Alright. So Renisha, it was 0.77. So how to go on which axis?
The y-axis.
Yeah. So I'm gonna go 0.77. So this will be 0.75. So how much blocks are to move up?
Zero 0.75.
Alright, I wanna go to 0.77. Right now I'm at 0.75. So how much blocks I will have to go up? How much small blocks?
2.
Yeah, I'll have to go up 2 small blocks. So I'll be right here. Let me take our read off. Until again, is 8 marks?
Yes, sir.
Yeah.
They should really bring this one, sir.
Yes, sir.
I'm going to take still picture that he say, just do it. I'm gonna just do it and see what the results does.
Alia had to like use Renisha's inspiration, but Renisha don't give up. Like that's good. And this is 0. Point what?
0.1, 0.51.
0.
0.51.
Because there's one small block after 0.5. 0.51.
Yeah.
It's
I
just plenty.
remember that sir said the block went by 0.1.
Nah, 0.01.
0.01. Sorry.
0.87. I'm gonna speed up because I want to do more questions. We still have a good bit to do. This one kind of ugly. We're gonna do this one.
So everybody is unique in their own way, you know, sir.
5.7.
0.57.
Well, it kind of look like in the middle of, so like
5.7.
It's in between.
0.5, 0.575.
575. Yeah.
It's not exactly in the middle, but that's all I put.
It's
They
not
either
in the
take it-
middle.
So they either take it or leave it, huh?
You gotta take
Yeah.
that. And then
The
7.
last one that have both missing.
You make a mistake here, guys. You make a mistake.
So I remember you told me something about that, how we would have carried out that
Yeah,
situation.
well, we can't put for that, buddy. We can't put for that.
We
We
can't
also
do
You did
anything.
tell me
Then
in
give we no
between the
points
highest
to work
number.
off of.
Like the only advice I could give in a situation like this, here I go tell you
Leave
to
it
do, right?
up.
Like, okay, you could probably go after 0.87. Like, probably go like here. This is what I would tell you to do. This is like 0.95. Because what else is supposed to do? I just put like a reading that is greater than 0.87.
I think they want you to draw.
I believe they want you to do that because why would they leave a blank space in the table?
Guys, we gotta understand too that they can make mistakes too.
Oh yeah, that's true.
We
They could
can't
make
expect that they
mistakes.
say, all right, we put this down here, let's see what we do.
Next thing is the computer they're using that make that mistake.
We don't know.
Can't assume. So I like that sticker.
Yeah, like what do you want to do, like? Right, state 2 precautions that the student should have taken in conducting the experiment, Devani. Sama. What are 2?
They should ensure that. Wait, what was the experiment?
Well, the experiment was the Perspex block 1.
Oh, they should ensure that they're on eye level when taking the readings.
To avoid parallax error, yeah. That's okay. And then we could probably say they could check to see if the glass block is fine before, like they could inspect the glass block before they do the experiment, you know what I mean?
Yeah, to make sure it has no cracks or anything, so it wouldn't tamper with the reading.
So this is what I would have put. So I would inspect the glass block for any cracks or marks if it's a cleaning block. And then number 2, you want to place the pins far apart so you get like a liner. Because like, let me explain how this experiment is work. I believe you just shine a laser beam here, and you would see the laser beam on the other side. If you put like the needles real close, that already makes sense, right? You want to form a line, so put the needles kind of far apart. You understand what I mean?
Yeah.
Yeah.
Sir, the way
So
we did
I
it,
agree with what you're saying, but the way how the teacher that I had did it, he did it with just the pens alone.
Sweet.
Yeah, I know.
yes, sir, it was like a paper and we drew a square in it, then we placed the glass block in the square, and then we put pins on one side of the glass block, then looked inside of it and saw where it came out on the other side. And
So you guys didn't use a laser?
Nah, we didn't use a laser.
no,
No,
sir.
we
we
didn't
didn't
use
use
a
a laser.
laser. They give us a blank piece of
Just
paper,
pins.
and we was to trace the glass block on the paper and place the pins where it's needed
Yeah,
to
so,
be.
so we had to
That's
draw the boundary line and then the normal.
Yeah.
And wherever the
that's
pins line up, you had to draw like lines connecting to the normal, like that kind
Yeah.
of.
The
okay.
pins,
That's
the point
Yeah.
of the pens is to choke in the paper, and when you move the pens, is to draw the boundary line, the refractive ray, and the incident ray.
like that's so lame. Like we actually use a laser.
Sir, is the school in us, sir?
So no,
It's a
so you see,
school.
you see why we
So
Yeah,
we're
getting
on a
problems with
budget,
physics
a
now,
really
right?
tight budget
yeah, you
today.
see why we getting problems with physics, sir? You see?
Hmm.
Sir, you just see them videos with real chemistry, how it is, this how them chemicals and it's explode all kind of thing. And when you walk in your school, pen and paper, we just imagining.
And then when you Clorox and diluted peroxide, the brain fail.
Oh boy.
Yeah, boy. Like this is the
I
these are the
actually get a
experiments
whole
supposed to
admin
look, guys.
split.
These are the experiments supposed to look. You can actually see it for yourself. You actually see like the light bending. The laser.
So, trick question. Is only green is supposed to use, or you could use any other color later?
You could use any color. We don't discriminate.
Okay.
Yeah.
Yeah, have a hatred for green or?
I never say that, Nikolai. I just
Hold on,
asked
hold
a
on.
specific
Let me
question.
continue. Let me
Jeez.
continue. So then we to calculate the gradient n. Oh my god, literally spelling out for you. And what does n represent, chat? What is n?
Gradient.
No,
Gradient.
The
no, no.
No,
N
not
gradient.
is
gradient.
refractive
Please.
index.
Refractive
Refractive
index.
index.
Refractive index.
Refractive
You
index.
see,
Like
you
the
catch
like
me. You
the
catch
like
me.
the you're literally spelling it out for you, right? It's telling you that the gradient is n.
Oh,
It's telling you
So
it's the
there's where
refractive.
maths coming. There's where maths coming.
So here what? I decided to pick 0.33, 0.50, 0.43, 0.65.
And
So
you get 1.5, right?
pick some points here. When I had done it, yeah. Really, I just pick any point. You could pick any points here. You could pick any points here because those points come from reading off the graph, right, guys? So you
Yes,
could pick
sir.
any, you could pick any 2 points over here, chat. Pick any 2 points from a table.
so you wouldn't have to use like the triangle method or anything.
Okay, that triangle method is literally way to okay. The triangle method is literally way to do in regular maths, right?
Boy beef.
Like, okay, when you find ingredient, is the exact same way to do it in maths. Like the exact same way. When you find ingredient in maths, right? What are you gonna do?
Y2 minus Y1
Y2
over
minus 1 over x2 minus 1.
Exactly, x2 minus x1. So you could pick any one of these 2 points. So you have to understand sine theta 1 is y, right? Sine theta 1 is y, sine theta 2 is x. So if I pick this point, then I would say 0.11, 0.165, x1, y1. Pick another point, 0.35. Wait, that's the input. 0.23, 0.35, that was the x2, y2. Find ingredient. Real simple. And I understand what you mean by the triangle method, but you know how to do that. You could just do it like how you do in regular maths. Take 2 points, find ingredient. Exact same thing, right? It's the exact same thing as doing maths. And when you work that out, you should get 1.5. And in the next question, they're going to ask you what physical quantity does the gradient represent? And it's going to be the refractive index of the glass block. And in this question, they said, it is known that the gradient is related to the speed of light c1 in air and the speed of light c2 in the glass. I'm not sure if you guys would have remembered, but I would have given you some other formulas to remember. And I said refractive index is also the speed of light in air over the speed of light in the water.
In the medium.
Exactly.
Yeah.
Isn't this what they're giving us here? Like the speed of C1? C1 is the
Yes,
speed of
sir.
light in air, and C2 is the speed of light in the glass.
Yes,
So
sir.
we'd have find n to be 1.5, so 1.5 is equal to C1 over C2. Now we know for a fact that C1 is 3 by 10 to the power 8, and we want to find for C2. So if you want, you can cross multiply. If you cross multiply, you end up with 1.5 C2 is equal to 3 by 10 to the power 8. What would I do next to find for C2?
Divide both sides by the 1.5.
Right? And now
Divide both sides by 1.5 and you'll get 2 times 10 to the power of 8
that is it.
minutes per seconds.
Nah, that's meter per second.
Oh, meter per seconds. Sorry.
Yeah. So Nikolai, let me check the question out. It was 2018, right?
January.
Does anybody know how much the physics SPA is out of?
100.
130.
Is 20% was your final grade?
20%.
Yes, 20%.
No, I mean like okay, the final exam was about 100% on.
All I know, the total raw marks as
So,
in
so how
for
much you feel
paper
like we
2,
need again? Paper 2
40.
You need
to
to
pass.
get more than half, I would say.
My SPA was
Yeah,
17% out of 20.
This question?
Yeah, that before when I was bad at physics, I wasn't getting through that.
Okay. All right, so let's give it a try now. So they're saying if the refractive index from the cladding to the core is 1.03, calculate the critical angle in the core. Okay, no problem. So the refractive index from the cladding to the core. Does it have to do with any of the previous questions? I guess not. Okay. So at the critical angle, what do we know?
It's 90 degrees.
90 degrees.
I'm right, I don't want to know. So
We
I would
know
have
it's
been
90 degrees.
so I would have been going from air to the cladding. And it's saying the refractive index from the cladding to the core is 1.03. Okay, so Ni sin I is equal to Nr sin R. And at the critical angle, we know the refractive. Okay, we know that the angular refraction is what?
90 degrees.
90.
Okay, and we're going from, well, I see we're going from air to the cladding. So air, that would be Ni. So I would say 1 by sine, don't know what that is. We're going to call that the critical angle C. And this is 1.03 sine 90. What's this going to be? 1.03 sine 90.
1.0.
That's just 1.03. So C would be equal to sine inverse of this, suppose. But that wouldn't make sense because you can't find sine inverse of 1.03.
No, you can't.
So try n is equal to sin I on sin R.
So
I believe when I did do it, I think I divided 1 divided by 0, 1.03. I don't know.
wait, give me a second.
It's the actual critical angle. You're gonna be on 1 sine theta, see?
Give me a second.
N is equal to that.
I just derive it. I will just derive it.
But yeah, the
So
angle critical.
so they want the critical angle. And I know at the critical angle, I know that the angular refraction is 90. Know that. So it had to be NR. And well, sine I oh, I see. It's going from the cladding to where?
Yeah, 10.
Yeah. Yeah. So it's going from the cladding to A.
So you wasn't supposed to watch the one before.
Nah, watch. Look at it. So okay, let me correct it, right? So then the refractive index for the incident is going to be the 1.03. We don't know what the angular incidence is.
Isn't something supposed to be equal to 90 degrees?
Wait, and we know that NR would be 1 because it's going to A, and that'll be sine 90. And when you work this out, it's going to be, well, 1.03 here is equal to 1. And when I divide both sides by 1.03, I'm going to get 1 over 1.03. And so C would be sine inverse of this. I believe this is what you did.
So
What I get. I'll explain the question to everybody that might be confused.
I got 0.01.
I think you have a
Oh,
calculator in
yeah,
radians or something.
yeah, mine's still on radians.
All right, so let me explain back the question. It's a new mistake to make. All right, so let me explain back the question, right? Any volunteers or want me to explain it back to them?
Yeah, I don't mind. I mean, I had
Yes,
problems.
sir, please.
Yes, sir.
Okay, so look at where the arrows are. I'm not sure if you see any arrows here, but the incidence. Wait, and let me see if I could. Yeah, let me see if I could make like a nice diagram for this. So, is there a way I could do a nice diagram for this? Okay, I tried to explain it as simple as I could, right? So the incident ray, where's the incident ray? It's inside the what?
The core.
Inside the 40.
Right, so I'm gonna call this the incident, and I'm gonna call this refracted. Okay, cool.
The point at which they make the angle, that is the normal.
Well, I've seen it. The scene is looking like a 90 degrees here. I've seen that looking like a 90 degrees here. I have the cladding here and I have the core. But really, okay. I'm gonna try to explain it as simple as I could. Like, this is the incident ray here, and it's a refracted ray. The incident ray is where is it?
In the inside.
In the inside, right? And that's inside the cladding to the core. And so, if I write down the formula, Ni sin I is equal to Nr sin R, then Ni is going to be Okay, the incident ray is incoming, right? So the incident ray is going to be within the cladding. And so what's the refractive index for that's going to be? Somebody tell me, what's the refractive index for that going to be?
The sine
The
90.
1.03.
That'll be the 1.03. Do we know what the angular incidence is?
No.
No. But we know we want to find the critical angle. Isn't the critical angle where the angle of incidence gives you 90 degrees for the angular refraction?
Yes, sir.
Yes, sir.
I'm gonna replace I with C. NR, we know that we're eventually going to leave the cladding and we're going to go back into where?
The outside. The air.
Into
I'm going
air.
to go back into air. So what refractive index do you think I should use for the refractive rate?
1.
1.
I should use 1 because we're going back to air. And at the critical angle, what is the angular refraction?
Sine 90 degrees.
It's 90 degrees. So let's fix up accordingly. What is 1 by sine 90?
1.
1.
1. And I'm trying to find for C, so what should I do next?
Well, divide by 1.03.
Should divide both sides by 1.03. And so sine C is going to be this, and what next?
You'll have to find the inverse because you're dealing with the angle.
Yeah. No, you see how like I was able to like reverse engineer the question, like rethink it. I want y'all to get into that habit. Like as soon as I see sine C is equal to 1.03, I was like, nah, this can't be right. It's can't be right. Because if you recall, the sine graph goes up to what?
1.
So that'll be very invalid. So I was like, something had to be off. Yeah. What is sine inverse of 1 over 1.03?
I got 76.14.
How many of you guys getting that? For anybody that did the question before, did y'all get the 76.14?
I don't remember. I remember the question.
And well, I believe some of you guys will have. I think there's a formula. Sine C is equal to 1 over n.
So by chance, how you put the inverse in the calculator?
All right. You have a sharp or a Casio?
Sharp.
All right. Get my sharp. You have to press second function sine. You have to press second function sine, and you should see sine inverse pop up. I really want to do like a proper diagram here, boy.
So, but that makes sense though, because remember when you say that the critical angle does only happen from a more dense region, medium to less dense. Yeah. So that makes sense.
You know, I didn't think about that, but that's a brilliant point because I mean, it would never happen from here to here because over here would be air, right? Over here would be air, and inside here would be the cladding. Which one is more dense?
The cladding.
Cladding.
Yeah. So that's a brilliant point. You always go from more dense to less dense, and that's the only instance where the critical angle could occur. And well, on the inside, can anybody explain this phenomenon to me? What is this?
Incidence and refractive rays.
I would have somebody tell me. Like, watch. Somebody, I wait for somebody to tell me.
Total incident reflection.
Total, yeah.
Yeah, this is total incident reflection. That's what it is.
Okay.
Yeah. Something still not sitting right in the middle. Like, let me just check something quickly. That would be the boundary line. Nah, that's not sitting right in the. Okay, like, this is the correct answer though, but I want to understand it deeper. You guys should always strive to understand the question at a deeper level rather than just accepting it. I will try to do a better diagram for this, but this is the answer. And like she said, it's always from more dense to less dense. And could anybody tell me what's more dense? Is it the air or is it the cladding?
The
Cladding.
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 The cladding is 1.03. Yeah. Nice question. Nice question. Well, high energy to make?
Yes,
Yeah,
sir.
yes, sir.
Yes, sir.
Yes,
Yes,
sir.
Sir.
I don't know about that.
Yes, sir.
Yeah, I don't know. So I think I
The
go
whole
with 9.
syllabus tonight.
Whole syllabus? I probably wouldn't say the whole syllabus.
That's
but-
the spirit.
I'm joking.
All right, let me tackle this question. Right. Hey, looky, grills any bad breaths. Oh, let's check antics now. Go brush your teeth now, boy. I go eat you.
So I remember that.
All right, so let me
Comedy,
tackle this.
comedy.
Let me tackle the question quickly. Can anybody tell me the laws of refraction?
Angular incidence is equal to the angular refraction. Nah, I know I see that. I know I answered my point, but I didn't say that correctly.
So the incident ray, first one, the incident ray and refracted ray lie on opposite sides of the normal, but both lie on the
plane.
Same plane.
The plane
right.
of the
Then the other one is the normal always lies
perpendicular to the boundary line.
right, and then the other one says a light ray going from one medium to the other medium would experience a change in speed as a result of going from one medium to another medium, and this is described as Snell's law. And Snell's law is Ni sin I is equal to Nr sin R.
Yes,
So those are the laws you have to say. Right, so figure 3 shows the clownfish Nemo looking at point P. It sees the fisherman's net appearing as if it were at A. Calculate angle C given that angle ABD is 42 degrees. This is a math question only. So, if there was no refraction, isn't this how Nemo would have seen it?
Yes, sir.
But is that how you seen it? Is that how you seen it?
No, sir.
Nah. Right, so here what I'm saying, right? They put this on for a reason. If this is 42 degrees, well, we know that this is the what? What is this?
The boundary.
The boundary.
What's the angle between the boundary and the
90.
90 degrees.
90.
So this would be 90 over here, and obviously if this is 90, then that angle there would have to be what?
180 minus that.
Which
Yeah.
is 48.
Well, be 180 minus 90 plus 42. You guys all let me know what you get for that.
48, sir.
I'll get 48 degrees, right? And I have a question for you, right? If you observe something, that 48 degrees is really the what angle? It's really the what angle?
The refraction.
Refracted ray.
No. Yeah, the refraction.
The angle of refraction.
But you gotta be careful, you know. You gotta be careful. Like, okay, I know how it looks like, but like, okay, I will tell you, right? Open up all your eyes for a bit. And it's called C. What is it?
Critical angle.
Critical angle. Critical angle.
Yeah.
Hmm.
Okay. Here what I'm saying. Right? I know it's a bit confusing because of how the arrows are drawn. But if Nemo is looking up, we're gonna consider it a bit differently. We're gonna consider the diagram a bit differently because, like we just said, the critical angle happens when we're going from a what to a what.
A more dense to a less
And more dense to a less dense.
Exactly. From a more dense. So here what I'm saying, guys. Here what I'm saying. What is over here? What medium we have over here?
Water. Because he can be in air and still be
Water.
And over here we have
Yeah.
Air.
air. Okay, I wonder a little zoning on this, right? Look at it. Oh yeah, they're literally saying C. What is that? What? And you're literally seeing that the angle here is what?
90 degrees.
90.
Oh yeah, the arrow is stricken, yeah.
Yeah, it is. Because when you look at it, that's really a case of the critical angle because the angular refraction is.
More.
Now, Nikolai, like it right there. Watch. So if we're treating this as the angular incidence, right?
Right.
Then this will be the angular refraction, and this is the normal. What is the angle between the normal and the refracted ray?
90.
And as a matter of fact, you see in C. So therefore, Nikolai, that C really represents the what angle?
Critical angle.
Yeah, because at the critical angle, the angular refraction is.
90 degrees.
90.
Are you seeing that or not? I'm wondering if you're seeing that.
Yes, sir.
Yes, sir.
Yes, sir.
All right, cool. So we calculated. They wanted me to find AB angle C. Oh, 3 marks for that? What? I'm not serious. I'm not serious.
So we
Oh,
could
you see
take
that?
them marks, sir. So we could take them marks. Hey, I happy then give we 3 marks on.
That's crazy. No, Ollie, that's
Marks
crazy.
is marks on.
Right. So given that angle C, Ollie, no, like literally read it. Read it.
Given that angle C is the critical angle of for the air water boundary, calculate the refractive index of the water.
Right, so let me show you how we're going to tackle this, right? So again, we know that the arrow is kind of misleading. So what I would do, I would just like draw over the arrows, right? Right. Does it look a little less confusing now? I guess from the silence it does not. It still looks confusing.
As I understand.
Yes, sir, we understand, sir.
Yes, sir.
It's
Good.
Liam. It's Liam. It was Liam.
No.
Yes, it's Liam.
Yeah.
Liam
No.
was the
Wait, how you
Brahmanic
change?
side.
No, how you change the voice already, right? Like
That's
I
what I
know.
said.
So
I
what
ain't
I
hear
need
that
to
voice in a long time.
Wait, boy, it was Liam the whole time, boy.
No, sir.
Nah, boy, Liam, boy. I didn't think it was you, no.
It's not me.
I didn't know you was like that.
No, sir. It's actually not me.
Nah,
Nah,
he
boy.
voice. Nah, sir, he voice different, sir. He voice different, sir.
Wait, Nikolai.
Jabari was one of them.
I wasn't expecting that from Liam, though. I just wasn't expecting that from Liam.
Like he turned at a certain what's it time? 1. And he don't turn early.
Right, so let me answer the question now. So, guys, if I switch around the arrows for it to make more sense, because remember, the critical angle occurs when you go from a more dense to a less dense. So, if this is the case, then we're going to treat this as the angle I want.
Refraction.
No, like,
Incidence.
Incidence, right.
Incidence.
and we're going to treat this as the what?
The angular refraction.
What's the angular refraction, chat?
90 degrees.
Cool. This is real easy, guys. What's your refractive index? A, by the way.
1.
1. All right, let me fix it. So we know that Ni sin I is equal to Nr sin R. Now, the incident ray takes place in the water, does it not?
Yes, sir.
Yes, sir.
I can replace Ni with what?
Water.
1.3.
Yeah, 1.3.
No, like this, they want you to calculate the refractive index of water, guys.
Oh, okay.
Yeah, although it is
I thought we
1.3,
was even the
although
same.
it is 1.03, we still had to prove that is 1.03.
Right,
Okay, cool.
Right. And so, Nikolai, what is the angular incidence?
The angular incidence is 48.
Way by Liam, boy. I still disappointed in Liam. Like, I had to blaze him like how cool when it blaze that fella who say 6'7".
Take wants to make you, and the first thing you could do is type 6'7". But in this case, the soundboard.
And Nikolai, everybody in class, right? If we rearrange the arrows for it to make a bit more sense, then this going, well, what we have over here, guys,
Yeah.
That's A, right? That's
Yeah.
A. And so the refractive index, I replace that with what?
1.
1.
And what was the angular refraction, guys?
90
90.
degrees.
Yep. So we're gonna end up with NW sine 48 degrees is equal to 1. So if I want to find NW, it's gonna be 1 over
Sine
Sine
40.
48 degrees.
plug that into your calculator and let me know what you get, chat.
1.34. Well, 1.35.
Yeah,
And I see
1.35.
answer. And you was expecting an answer somewhere around there.
Yep.
Yeah, but then that means that water thick because it's 1.03 for normal water. I
Yeah.
believe.
1.03.
Wasn't it
No, it's
1.03?
It was
No, it was
1.30.
1.3.
What?
Nikolai, you tell me you mixing
Huh?
up the cloud and the cloud and then the last question was 1.03.
Ah, right.
Yeah, you I feel like you're mixing up this.
Right. My
So
bad.
I'll find that was hard or that was easy.
No,
No,
That was
that
cake.
that
That was
was
cake.
it was tricky. I wouldn't say it was easy, it was tricky because first of all, the arrow is trickier.
It
But
is, it
then
is. But just remember, guys, if you're talking about critical angle, it's always more than celestial. So you have to be going from water to air, right? All of them fool you. And well, over here, they're saying Nemo swims away and his eye is now a horizontal distance of 5 meters from point B. Looking at point B, he no longer sees the net, but now sees Bruce, the shark. I like what the writer is like, but now sees Bruce, the shark.
it sounds like they're
but
doing
alright,
a
so
short
But
story.
I did movie.
the climatic part of the story.
And there was never Boogle. There was only
So
the
you watched that
fireball.
movie?
Yeah, well, I watched it with my grandma. She
I
wanted
only
to watch.
saw the shorts of it. I never saw the
So
full movie.
that movie was bad. That movie was bad.
Yeah, say no balls, no balls.
There was never Boogle. There was only Firewolf. Right? If Bruce is at the same depth as Nemo, how far away is Bruce's eye from Nemo's eye? Explain your results. So let me ask you that question, right?
10.
Previously, this angle 48 represented the what?
The
Angle of incidence.
Angular incidence.
Right, which is, well, in this case is really the what?
Is a critical angle.
Critical angle, yeah.
It exceeded.
If Nemo swim past that, you're gonna get an angle bigger than the what?
The critical angle.
Critical
The
angle.
critical angle.
And if that happens, and it's going to dip below the boundary, and you're gonna have total what?
Total internal reflection.
Total internal reflection.
So like if here to here is 5, then what would here to here be?
5.
10.
So the distance from Nemo to Bruce is really what?
10.
10.
5.
Yeah.
10.
It's really 10. Yeah, it's really 10. I don't know my answer is, but it's just 10 meters, guys. Just 10 meters. I feel lazy to write. But effectively, I hope all you understand. If he swims further, the critical angle is going to be exceeded, and then you'll have total internal reflection, meaning that the distance from Nemo to point B will be the same distance as point B to Bruce, which is 10 meters altogether. That hard or that easy?
That was easy. Well, this one was easy.
Easy.
Easy, so easy.
I'll let check Bruce Grills, boy. Looking more like food stick up in his teeth, though.
That's a right goal. He replaced it with goal. Had to eat
Yeah,
with
I now
green.
realize this. You draw that.
So he had to eat with luxury.
So there's a real question.
Yeah, there's a real question. We just put in the teeth and the yellow
Can't
stick.
pass that to pay.
Will the shark actually come on an exam?
Probably.
Or
Hey, bro.
This is a Zessa, you know. Bruce is a Zessa. It's a Bruce Zessa,
Shame,
bad
shame.
boy.
So wait, the shark didn't have teeth before?
No, he didn't. He watch.
Now,
I had to fix up my boy Bruce, boy. I had to fix up my boy Bruce.
because you're not looking intimidating at all.
With all
Like,
the TT looking scared, he looking more scared of me than I am of him.
watch. Now he looking like a bad man. But before,
Now we need a white vest.
Real.
So where's them shirts people is?
Draw my vest, draw my vest.
What should them people, well, the young people is go with now? With the kind of skull or something?
What Godspeed?
Or
Yeah.
them graphic design shit.
yeah, boy. All right, let me continue. I want to move on to lenses. Lenses is real easy. Like, okay, raise your hand if lenses get you trouble. I can't really see it, but tell me.
Yeah, the only problem was with me was the relationship between the real and the virtual one.
So I just forget the equations and stuff.
Same.
The equations. The equations.
Equation to find equation to find like focal length and thing.
Well, let me mash this up now. This is real easy. It's real easy. Like, it's real easy. So easy. But of course, I'm gonna show you a practical example. So, if you wonder why we call it a convergent lens, is because, watch. I don't know if you realize, but the laser, after it passes through the lens, what does it do?
Converges to one point.
Converge.
Yeah, one point.
Where does our meet at one point?
And notice that this laser over here, it passes through the optical center and it goes straight through. It's undeviated. That's actually how we form the principal axis. For those of you guys that did not know, the principal axis just refers to a light ray that goes straight through the lens, and so that's why when you're drawing your ray diagrams, like take for instance this over here, and you would typically draw it like this.
Yes, sir.
Yeah, well,
Yes,
this is actually a real light, you know. That's actually a real light, because a ray of light that goes straight through and passes through the optical center is going to go undeviated. Yeah, and watch. This is our what?
Divergent.
Divergent.
Again, the light ray that passes straight through the optical center, it goes straight through undeviated. Do you understand?
Yes, sir.
And if you wonder how you know if it's real or virtual, let me explain. I'm a cook. So the guy has an image here behind the magnifying glass, and this gets projected into the real world, like on a wall or something. Yeah?
No, sir.
Yes, sir.
Okay. I'll ever make a projector using a magnifying glass.
So after CSEC, let me meet up and do something like that, now, sir.
Yeah, I'll do
Telling
something.
you. Because
Like,
your experiences and mine, it's not enough.
For real. For real.
it's sad how physics is taught in school, but if I was a physics in school and thing, I'm making like I bring in materials and we making a projector and watching a movie and
So I'd be skipping my class to come to your class, sir.
I like that. I like that.
I didn't matter. It didn't matter if I had you or not.
I like that because we'll actually doing real physics, you know, like a real physics, you know what I mean? Like not like nothing on paper and thing. I'll be seeing the laser, you know, making projectors and thing.
And if we was actually doing real physics, like we would have a better understanding, we would have never, be in this position.
It's
Exactly.
I still come here. I still come here.
And it's not only physics, although when you think about it, it applies to bio and chem too.
Mm-hmm.
Chem I could probably I don't really like chem, but that's true. That's true. All the sciences are most of the sciences are taught bad, real bad,
Yes, sir.
real bad, man.
So wait, who's that boy named for Admat, sir? Who say he jump over the fence or kind of thing?
Mikhail.
Yeah.
All right, let me show you something, right? Check this out. So here, what, right? You put your phone here. You take the lens from a magnifying glass, and you put it here. You put your phone here. You cover the box, and the image from your phone is going to be projected onto a wall. Real talk.
Yes, sir. Really and truly, we had to make something like that.
Yeah. How much of you guys didn't know you could do that before?
Nope.
So I still don't know.
No.
So I only know that because of 5-minute crafts.
Yeah. Here
And
what
1,
I'm
2,
saying,
3, go.
here what I'm saying, guys. If you put your phone here, right? and you put your phone on max brightness, the lens here is going to magnify the image from your phone and it's going to project it on the wall. I don't know how else to explain it.
So
And
the magnifying glass is a converging lens?
yeah, it's a convergent lens. Yeah, it's a convergent lens. Divergent lenses only produce virtual images. Yeah. And when you do in the diagrams, you can see what I mean, but here what I'm saying, all here what I'm saying. If you put your phone here, doesn't the magnifying glass actually project an image into the real world? Like on a real surface, on the real wall?
Yeah.
Yes, sir.
Yes.
Okay. So when we talk about real and virtual, what I'm really saying is a real image would be formed after the lens and it would be projected onto a real surface. However, if it's virtual, you'll actually see the image through the lens. I'm not sure if you're seeing that, but if you notice behind the man, you see now what? Behind the man, you see now what?
The real object.
Are you seeing that, right? Behind the man, what you seeing? What are you seeing behind the man?
The real object.
I only hear Nikolai. Nikolai is not the only person in class.
We seeing the real object like blurry and like it
Well,
has clear.
that's because of how we take the picture, right? But when you look through the lens and just see that same, you see that object, right? But it's smaller and it's diminished. But like you could only view that image through the lens. Is that like an actual image?
No.
No, sir.
No, you're viewing it through the lens, so it's virtual. However, over here, you're projecting an image onto the real surface, like a wall or something. So you actually, like, okay, with this instance over here, it actually taking the image from your phone and it's actually projecting it on the wall. So aren't you viewing it in real life, like you've seen it in real life, like on the wall. But over here, you could only see the image through the what?
The lens.
Well, the
The
lens.
lens. The lens. Okay. I hope I understand it a bit more now.
So,
Yes, sir.
Yeah.
isn't a virtual image also formed in a mirror?
Yeah. That's correct. That's
So
correct.
you can also go through the features. I think like I saw a question on that.
Wait. So like look at this question quickly. Look at this fast. The object is here and the image is here as well. It's both of them are behind the lens. Would that be a real image or a virtual image?
Virtual.
A virtual.
Virtual.
Yeah, because it behind. Okay, because watch it literally behind. It literally like it's the same thing. Right? Okay. Let me give a little crash course quickly on this thing. This is real easy. I've been saying that. Like my problem is like I kind of know like quick thing, like when I teach, I teaching people to understand, not just like pass on thing. So like okay, let me start off with convergent lens. So when you're drawing your ray diagram, you're starting off with your principal axis, right? The convergent lens looks like this. Do you guys know that?
Yes, sir.
Yes, sir.
Let's show.
Yes, sir.
It like a kind of teardrop kind of way.
I suppose so. And what do you call this over here?
Focus.
Optical center.
The focal point.
No.
Optical center, sir.
It's the optical center. It's the optical center. Okay, so let me explain something. There are some rules you need to know. Here, what? These are the rules. Number one, a ray of light passing through the optical center of a lens, it goes straight through without being refracted. Like what? It literally goes straight through. It literally goes straight through. Can you guys see that in both instances, the light ray is going straight through the optical center?
Yes, sir.
Yes, sir.
Yes, sir.
Right. And the other rule, a ray of light which is parallel to the principal axis after refraction appears to be coming from the focal point. That is for concave lens, but let me show you how that will look like for this. All right. I should have some diagrams done already that I could show you guys really fast. Okay. No, this is not what I want. All right. So a convex lens has a focal length of 2.5 centimeters. We have an object of height 2 centimeters. Draw a ray diagram to illustrate where the image will be produced when the object is placed in the following regions. So guys, what do I call this black line over here?
The principal
Principal access.
Right, principal axis. Okay, so remember in this diagram here, where the light rays would have converged to,
Yes, yes.
that is the focal point. The focal point is where the light rays converge into. That's why convergent lens, and for convex lens, it's where it diverges from. And this over here is the what? What's this?
The
The optical center.
It's the optical center. Cool. So I have the optical center here, and obviously I would draw this to scale. So when you measure the, okay, in the question they said it has a focal length of 2.5 centimeters. Can somebody read off the length from the optical center to F? What's the optical? What's the,
2.5.
exactly, because I told you the lens has a focal length of
2.5.
right, and that would apply on either side. So watch. Can you see that 2.5 is over here, right? And then we have 2f. Okay, if the focal length is 2.5, what do you suppose 2f is?
5.
5.
That's all. 5. That's all. So all you understand the basics, right? You put on your lens, you put on your optical center. From the optical center, you measure the focal length on either side. Cool. Now we're saying we have an object of height 2 centimeters. We want to draw a diagram between F and O. Where would between F and O be? Somebody tell me. Would it be over here?
No, sir.
No, sir.
Would it be over here?
No, sir.
It would.
Yes.
Because this is in between what?
The optical center and the focal point. I mean,
Exactly. That's where it is. And we need to draw an object of height what?
2 centimeters.
2 centimeters.
And I could place it anywhere between F and O, and the result will be very similar. So here are the rules, my friends. Here are the rules. By the way, this is the object.
Oh,
Be very.
okay, cool.
Wait, so guys, can you all see that they say they want me to place the object between F and O? So didn't I do that? This is F and this is O. Didn't I place it between F and O?
Yes, sir.
Right. So here's the first rule. A ray of light that passes through the optical center will what? If a ray of light passes through the optical center, it will what? It would go straight through. It going right through. Watch. So I'm gonna do that. That's the first thing I'm gonna do. I feel like I should ban Liam from the meeting, boy.
So it wasn't me. I know come back from food.
Yeah, the voice change.
It wasn't me. Send message here.
Yeah, man, looking too hot here by me, man.
Wait, what do?
The evidence stacked against you by me, boy. Nah, but
Got caught in 4K.
You could
Like,
lie.
Remember, this is on live, so we could go back in the recording. Just saying.
Yeah, so guys, this is my first rule. I'm going to draw a ray of light from the object that passes straight through the optical center. And if something passes through the optical center, it goes straight through.
So, for this, we have to learn how to draw it, or any test if you draw it, what they tell you to do, it will work.
You had to draw, you learn how to draw it.
So, like, if we tell you to draw between 2F and F, and we do that in test, it won't work out?
It depends on when they ask any question, they would typically specify. I need to use my fake
So most
calculator.
of the past paper questions I saw was easy, like it wasn't bad on this topic.
In general, it is very easy. I'm gonna use my fake Apple pencil. because the real one playing up. All right, so this is the first rule. The next rule, we're going to draw a ray of light parallel to the principal axis. So this is the principal axis, and I'm going to draw a ray of light parallel to it. Now I have a question. When this ray of light hits the optical center here, on the other end, it's going to want to converge to a point. Could anybody figure out what point it's going to converge to?
Focal point.
F.
It's going to converge to F.
Yeah.
I mean, you literally saw that over here. I literally showed you guys that it converges to the focal point. Now, let me ask you guys a question. Are you all seeing an intersection anywhere in sight? Will those two lines ever intersect?
No.
No.
No. So therefore, if it's between F and O, there is
No image.
no image. Right, so here what? I'm gonna erase all the diagrams and we're gonna run this quickly.
Oh,
Oh, look.
so when they intersect, I mean it creates an image.
Say that again?
When they intersect, that means it creates an image.
Correct. That is it. That is it.
So they won't tell me the object height and thing?
Say that again?
The object height and thing, they won't tell you that?
It depends. In the questions I've seen, they typically do. I don't trust Liam, boy. After that, and you know, like the Google like plot twist, I feel like I just
So
have
I want
to
to know. I want to know who Liam friend is because in the chat he say he friend say we
He
are
watch on
teaching him.
YouTube.
He was what?
Liam. I don't
He
trust
watch
Liam.
on YouTube.
Don't trust Liam after this, boy.
Mom, sir.
You see, Liam,
Nah.
it's like a wolf in sheep clothing.
So say the word.
Nah, we will leave him for now. If we do anything else, we know it's Liam. But... Right. So we're gonna repeat the exact same procedure. So now they want me to place the object where? They want me to place the object at
F.
what? At F. So guys, the first rule, a ray of light that goes through the optical center, what will happen to it?
What?
Okay, so here what?
Pass it through.
Here what, guys? Here what? There's literally just two rules here to remember. Literally just two rules. These are the two rules you need to remember. A ray of light passing through the optical center of a lens goes straight through without being refracted. That's the first rule. And then the other rule, a ray of light which is parallel to the principal axis after refraction, well, in this case, it would go towards the focal point. There's just two rules to remember. Just two rules. Just two. So the first thing I'm going to do, I'm going to draw a ray of light passing straight through the optical center, originating from the object. Very first thing I'm going to do. What do you guys think I'm going to do next?
One's supposed to be passing parallel to the principal axis to the optical center.
Right, so I'm going to draw a ray of light parallel to the principal axis. Now, when it enters the lens, after it's going to want to do what?
Well, converge. Well,
converge where? Converge where?
The
focal point.
The focal point. So it's gonna look like this, guys. And it's just repeating this whole process, you know, like this ought to be hard.
So you think this question might come?
Probably.
Was there? Wait, how long this question never came in the exam for?
I see it recently. But let me focus on that. Guys, them two lines looking what?
Parallel.
So we say the image is infinitely large, image is formed at infinity, and it's a real image. Why do we say it's a real image, guys? Well, this one a bit weird to understand, but point is, the lines are parallel, and it's after the lens, so it's real. Anytime you have an image after the lens, it's real. If it's before the lens, it is
Virtual.
right. Let's move on to between F and 2F. So where did I move the object to now?
between F and 2F.
Between F and 2F, yeah.
I'll get with the motion. So what's the first thing I want to do? What's the first rule?
A line passing through the optical center from the object. Isn't it undeviated or something like that?
Yeah, undeviated. Just go straight through. What's the next thing?
A line from the object to the principal, parallel to the principal axis. To the, where's called that line, sir? The normal?
I don't know. It's called a line, but I don't know. All I know is just draw it is like the line of symmetry for the lens.
Oh.
They already have a name for it. But like
Then
it's like the center is like the mirror. It's like the mirror line of the lens.
oh,
But
then after that, it converges between F and 2F.
no, guys. The focal point is either where a lens convergent to, a convergent lens, or it diverges from divergent lens. So here what? All I'm gonna do next, I'm just going to draw the ray of light conversion at F. That's all.
Oh, okay.
Are you understand or not?
Yes, sir.
Yes.
yes, sir.
So, wait, one question just to clarify, right? Whenever the object is at a random place, right? Random location on the principal axis, right? And when it touches the mirror line of the converging lens, it always points, well, it always converges as to the focal point.
Yeah, because the focal point is where it would converge to. That's the focal point of the lens.
Okay.
Yeah. I can understand this, right? F is where like the light ray is gonna converge to. That's literally what it is. That's the conversion point.
Yes, sir.
Sir.
Yes, sir.
Okay, was there an intersection?
Yes,
Yes,
sir.
sir.
Okay. I wonder this image looking like it's right side up or right side well upside down.
Upside down.
Upside down.
It looking upside down, but it looking a bit what? Smaller or bigger?
Larger.
Bigger.
Larger.
So this image is upside down, and it is larger, and it is also what? Since it's on the other side of the lens, it is what?
Yeah.
Real. It's real. Okay, let me answer that question, right? When you guys try to make the projector or the magnifying glass, you're gonna realize that the image gonna be upside down. You'll see. You'll see what I mean.
And
And
so
this,
another way, sorry to interrupt you, sir. Another way that I just remember it is that real images are always inverted and virtual is always upright.
that's a great to remember, right?
So, and that kind of makes sense because, like, when we see images, we actually see them upside down. But
But the eye, but
I
the mind,
sense, yeah, signal say brain to flip it. Yeah, that's so
crazy.
cool, bro.
It's just cool. It's cool. And you could use all of this, like bio people. You had to know about lenses when you correct it, myopia and hyperopia. What do you
So
call it?
repeat what someone, wait, who said that?
So Lani said that a way he's remember it is real images will always be upside down. Virtual images will always be upright.
No, but I heard somebody said about the eye.
Yeah, so like the human eye, we actually see, okay, the brain, the signal it actually gets is an upside down image. But the brain actually like makes it up, it makes it right side up.
The
Yeah,
brain is basically autocorrect at first.
yeah. It's really powerful.
So, question, but anyone before we now do at the focal point, and it was a real image, but it wasn't.
Okay. Yeah, this was a real image. Like, okay, this one is really weird because there's no perceivable point of intersection, but it is parallel. So like this and this is parallel. Here what? Once it's on the other side of the lens is real. And it's the same procedure you're gonna spam for every single lens question. So like here what? I'll wait. Who's this? I'll wait to do a question on now. Just so I can see the exact same thing we're doing. It's the exact same thing. What's the name?
Kylie.
All right, Kylie. Okay, Kylie. So here what we're doing, right? Here are your rules. Number one, I'm gonna draw a ray of light from the object that passes straight through the optical center. That's the first thing I'm gonna do. Now, if a ray of light passes through the optical center, will it be refracted?
No.
No, it's gonna go straight through. Then the other rule, I'm going to draw a ray of light that is parallel to the principal axis. This is the principal axis. I think you can see parallel. Now, after it exits the lens, it's going to want to converge to what point? Since it's a conversion lens we're dealing with.
The
It's going to want to
focal point.
converge. It's going to want to converge here. Are you seeing a point of intersection between these two lines?
Yes, sir.
Now, if you compare any height, which one looks bigger? The object or the image?
The image.
So the image looks bigger. Did it form on the same side of the object or it formed on the other side?
The opposite side.
So it's real. And is it right side up or is it upside down?
Upside down.
Yeah. So let's do it for another question. And by the way, guys, you should know that magnification is just the image height over the object height. It's also the image distance over the object distance. Just put it out there. Right, so Kylie, let me tackle this one now. So in this round, I place the object where? Where did I place the object?
At 2F.
I place it at 2F. Let's apply the rules we just learned. So what's the first rule? What's the first rule?
Draw a line through the optical.
Like so, right?
Then draw a line parallel to the principal line.
Principal axis, right? And after it passes through the lens, it's going to want, since it's a convergent lens, it's going to want to do what?
Converge to the focal point.
Kylie, we cooking.
Yes, sir.
Ah, boy. What are we talking about? Let's go, bro. Let's go. Easy stuff. Are you seeing a point of intersection?
Yes, sir.
Now, if you realize, okay, I didn't draw that perfectly. My bad, my bad. If I did draw it perfectly, you'd see something really cool. Now, I'm not sure if you're seeing this, but like, wait. Okay. Oh, wait to check this, right? So this is the image, by the way. This is the image. If you look at this, right, the image and the object looking what?
The same size.
Yeah, it's the same size. And if you also notice, both of them are the same distance from the optical center. Seeing that?
Yes, sir.
So, in this instance, again, did it form on the same side as the object or it form on the other side?
The other side.
So that's real or virtual?
Real.
Right? Real. And is it upside down or right side up?
Upside down.
Upside down. And it's the same one.
The same size.
Same size as the object. Like, so what I'm trying to say, Kylie, you don't have to memorize anything, you just have to spam the same concept for every single question you're dealing with. And you get through. You get through.
Yes, sir. I understand.
Let me do the last one, beyond 2F. Let me see what happened in here. So, again, you probably fed up on this. What's the first thing I'm gonna do?
Draw a line through the optical point.
Right. I hope you realize how easy this thing is, This is real easy. Cool.
Then draw a
What next?
parallel line to the principal axis.
Bruh. 1 second. Technical difficulty. Right, what next?
Then it converges to the focal point.
Right. Does this image look Bigger than the object or smaller than the object?
Smaller than the object.
Right. If it's smaller, we call it diminished. It's diminished. And if you realize, the object is beyond 2f, but the image forms before 2f, also implying that it's smaller. So it's a real image, it's upside down, and it's smaller, so we say it's diminished. That's all. That's all, Kylie. That was harder, that was easy.
Easy.
What would the rest of you need Zoom? Well, let's use the same procedure over and over again, right?
Yes,
Sir.
sir.
Yes, sir.
So, like, all you had to do, draw a line from the object passing straight through, bam. Then they're going to draw a ray of light parallel, and they're going to pass through the focal point, whereby it intersect. That's all. Let's move on to convex lens now. By the way, I don't know these formulas, eh? Take a screenshot. These are the formulas that I remember. 1 over f is equal to 1 over u plus 1 over v. Magnification is equal to image height over object height. The magnification is also equal to the image distance over the object distance. Take a screenshot. Fix it. Alright, we nearly finished with this whole topic, bro. Let's go.
We're ready, Shagun.
Ready, Shy, you there? Hey, boy, ready, Shy, boy. Renisha has betrayed us. Hey, boy.
I know she knock out. I just know she knock out.
Only put on the camera and thing now. So I can see like if only falling asleep and thing. I'm curious.
Sir, I don't sleep, sir.
Aaron, where you come from? Aaron is my son.
You don't know. So after that maths, I can't sleep anymore. I don't sleep anymore.
Boy, Aaron, I went to sleep 5 o'clock yesterday. 5 in the morning.
So if I was you, I
Sir.
wasn't sleeping.
Excuse, sir. I
Yeah.
had to take care of my eyes. So as soon as 12 reached, I went in my bed.
That makes sense. That makes sense.
Like
How about the rest of you? How about the rest of you? All right.
Nah,
Well,
today I catch up on
Yesterday,
all my sleeps.
yesterday I had a 7-hour exam, so right now I'm not gonna lie to you, I literally, if I close my eyes, there's a day I out.
all right. Well, let me jump into this thing fast now. So, Alia, this was the summary. You have convex lenses, and these are the convergent lenses. Convex, convergent, convex, convergent, right? Right? And we just dealt with them. As you could see, after it passes through the lens, it wants to what? It wants to what?
Converge. The
It wants
focal
to
point.
converge at F.
Focal point, yeah.
Now we're gonna look at concave divergent lenses. Ooh. Now here what? As the name suggests, it's going to diverge. But where is it gonna diverge from? That's the question. We have to figure that out. You actually had to backtrack. So as you can see, the focal point for these types of lenses is actually to the back, because with concave lenses, the light ray is actually what? Do they converge or diverge?
Diverge.
Right. So anybody want to tackle this with me?
I don't mind. Well,
All right.
you know my scene, sir. You know my scene.
Right. So you look away for a bit.
Yeah, of course.
So you gotta
I'll
get
look at it, I'll look at the feeling.
Ahmed, you here, boy? Unmute your mic and thing now, son.
Yes, sir.
Yeah, boy. This man is always
Yes,
called
sir.
uncle, boy. I got deal with you on a fine, you know. Yeah, boy.
Ricky. Wait, what is this? Was it Rick or Ricky?
When I catch you, Ricky, when I catch you, Ricky. Yeah, boy. Ahmed, you going good, boy?
Yes, sir.
Session going good?
Yeah.
How does it feel to be on the inside? You're part of it now. I suppose that's a good thing. Can I quiet? I don't know. I just need the gas
Yes,
up.
yes, sir.
I just need the gas up now to keep going. Where do you think this energy just come from? All right, so Let me do a random example, right? A random example. Or you tell me, where do you guys want me to put the objects? By the way, what kind of lens we dealing with here? Convex or concave? Convex or concave?
Concave.
Convex.
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 Oh, what is looking like?
Concave.
It looking like
Concave.
I know
Concave.
that.
it looking like a what?
Like
Looking
a
like a
kidney.
cave. Looking like a cave in
Hourglass.
We know it's not
Hourglass, yeah.
concave.
Hey,
concave.
sir. I was gonna doubt myself just now. Do you want
What?
to say concave?
Concave. Hey boy. If it did say if it did say concave, I'll be convex.
Okay.
Comedy
I
at
see. I
its
see. I see where
finest.
Sir is going with this. I see where Sir is going
Comedy.
with this.
Anyways. Lock in, guys. Lock in.
That's it.
So, where you want me to put the object?
After the 2F.
After the 2F, no problem. So always the same rules apply, eh? It's just like the focal point will behave a bit different. Alright, so what do you want me to do? What's the first rule?
Where the line undeviated through the optical center.
Everybody okay with this first rule?
Yes, sir.
Ladies, are they okay with this?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, Liam, not Liam, say yes, sir.
Say lah, yeah, Madura.
I say like ladies, are you understand? She hear Liam. Yes.
Sir, AI, sir, Madura, sir.
No, Liam, I see my commute.
No,
But
die AI, die
when
AI.
you turn buttons now, everything is AI. No problem.
Alright. So, here what, right? This is going to be a bit different. But entries typically draw a line parallel to the principal axis.
Yes, sir.
Am I going to do this nonsense?
No. Well, no.
No. This okay. You would do this if it was a what type of lens?
Concave.
A
I mean,
concave.
convex. Convex.
Convex, yeah.
Convex. Now let me show you what you have to do now. You have to take your ruler, you have to line it up with the focal point, like so.
What a
Go and
diverge
draw.
outwards.
Bam. That hard or that easy?
That easy, sir.
Alright. Well, let's see now intersection anyway.
Yes, sir. One time.
Yo.
Ollie, I see an intersection right here. An easy
Yes.
image. Let me ask you that question. The image looking bigger than the object or smaller than the object?
It's diminished.
Smaller.
If it's smaller, it's diminished. It's diminished. Right? It's smaller, it's diminished. And is it right side up?
Yes, sir.
Yes, sir.
Yes.
Well, let me ask you that question. Is it okay? Is it formed behind the lens or in front of the lens?
Behind the lens.
Behind.
So if it's formed behind the
Virtual.
lens,
It's virtual, sir.
it'd be a virtual. It'd be a virtual. Remember? I remember the example I showed earlier. You will only be able to see it through the lens. You'll only be able to see it through the lens, Ollie. You'll only be able to see it through the lens. So it's not real. It's virtual. Okay, are you okay with this example or not?
Sir.
Yes, sir.
Alright, now you do another one. So a concave lens has a focal length of 4 centimeters. As such, complete the ray diagram to illustrate the light ray after refraction. So if I measure the distance from here to here, what should it be?
4 cm, sir.
4 centimeters.
4 centimeters.
Let me see. Is it 4 centimeters?
Yes, sir.
Yes, sir.
Okay. Where do you want me to place the object?
At F or like 1 centimeter before F. Anyone.
Right, where's the first step?
Where a line cuts through the optical center and is undeviated. It cuts the optical center and the principal axis.
Well, to be fair, guys, the principal axis is just a ray of light that passes through the optical center, you know.
Yes, sir.
Alright, what's the next step, Nikolai?
There's a straight line parallel to the principal axis to the mirror of the concave lens.
What next?
Then we put our ruler by F.
Like this? Like this?
Other way, other way.
Oh,
I
Like
was
this?
supposed to do that reverse. If I was to explain that, like it would have been reverse.
I don't know. Probably say like align the ruler with the point of intersection between the parallel ray of light and the lens, as well as the focal point behind the lens. Yeah. Oh, let's see that intersection.
Yes, sir.
Yes, sir.
They're probably getting fed up because I the exact same thing you do over and over and over, and nothing had changed. Literally nothing had changed in chat.
The
So
only
like,
thing I haven't given me problems is those numbers. Like I know how to calculate the magnification and the focal point and everything. It's just a reminder of the numbers, what if it's real or virtual or anything like that.
okay, no problem. So guys, what would I say about the image? I would say the image is
Virtual.
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 virtual. What else?
Upright.
Diminished and upright.
Diminished.
A little better. I get full marks on this section, otherwise I'll cry.
So the only how I get any full marks is if it come.
It will come. It will come. Like waves on optics had to come somehow. All right. So over here, I place any object beyond 2F. Beyond 2F. So somebody else. I also need to come on the scene and help Mois. Nikolai help me enough. Somebody come fast.
I think the
You
object is
see?
junction actually.
All right. So Lani, what's the first thing I gotta do?
You good fair.
Oh, so I say Liam, you know, so I think you should get Liam a chance to redeem himself. So.
Do not redeem it.
Do not
I
redeem
said do not redeem it.
This is average.
Anyways, yeah, Lani, help tell me what to do first now.
God, I say I doesn't know how to explain it, so I just know what to do.
Okay, so I will let Marshall help me. Marshall. But Lani, I trust you. Marshall, tell
I
me what to
do.
do.
Just say you draw the line through the optic and the principal axis.
So you're drawing a line from the object straight to the optical center.
Yeah.
What
Then
next?
you draw a parallel line with the object and the center of the lens.
What next you doing?
And from the bottom of the object, you draw from the bottom of the object.
This is what you mean, right? This is what you mean, right?
No.
Let me run it back again. Because that's the correct thing, right? So here we had to do. You had to draw a ray of light parallel to the principal axis. And remember, this is a divergent lens, so it's going to diverge. But how do you figure out where it's going to diverge from? Well, it's going to diverge from the focal point here. So you're going to take your ruler, you're going to line it up like so. How many of you okay with it?
Yes, sir. So it's only by the focal point.
Yes, so the focal point tells you where the light rays converge to or diverges from.
Okay, that makes sense.
Cool. Now let me ask that question. Do you see a point of intersection there?
Yep.
I see one right here. Now look in. What? If you were to describe the image, what you could say about it?
Upright, virtual, and diminished.
Cool. Help me with this one. So between F and 2F. So where would I put that? Tell me when to stop.
Wait, so go back. My mic was stop. Wait, you went too fast. Yeah.
No, like, okay, it's between F and 2F, so it'll be somewhere between here and here.
Yeah.
So I could probably go over here.
Yeah.
Where's my first step?
You draw your line from the object through the optic center. The optical center.
Like so?
Yep.
What do I do next?
Then I draw a parallel line from the object to the center of the lens.
So like we know it's gonna diverge, right? We know it's gonna diverge.
Yeah,
Oh, well, what is it gonna diverge from?
the focal point.
This focal point?
No, the one behind the lens.
Oh, every once in a while, as I encounter a student, I say or as opposed to oh. Yeah.
Wait, Celine's still here? Or she gone?
So that again?
Celine, who did say that as well?
Oh, I know Gabrielle to say that. So you see now an intersection, Marshall?
Yep.
That's a real name, Marshall?
Well, my first name is Shania, my last name is Marshall.
Oh. I was gonna call him Montano. Right? So this is the object over here. And well, this should be a what?
The image, the virtual image.
Again, the image is diminished, it's virtual, and it's upright.
Yeah.
It's the same thing, you know, like for every single case, it's the same thing. So
So
that's what I was saying. Yeah, talk to me.
So all the images formed for diverging lens virtual.
Yeah. So like have it here. For concave lenses, no matter where you place the object, you'll get an image with the following properties. Maybe virtual and upright and diminished. Yeah. You understand?
Yes, sir.
So, let me do a question. So Kylie gonna help me with this. So Kylie, draw a ray diagram where the object is at 2F. So I already put it over here. You see that?
Yes, sir.
Then they wait at F before F, whatever. And they tell me that the focal length is 3. So when I measure the distance from here to here, what should it be?
3 centimeters.
Yeah, true?
Yes, sir.
Alright, cool. And the object height is 1 centimeter. No problem. What's the first step?
Draw a line through the optical point.
What next?
Draw a parallel line to the middle of the lens. Then you go at the focal point behind the lens and connect it.
If this come again, any marks for sure, right? I hope.
Yes, sir.
Bro. 1 second. Good notes playing up. I thought you know the meme. Don't try to play a fool with me, Pukesh. You know what I'm talking about?
Yes, sir.
That's how people do this. Indian man buffing him up. Alright, so Kylie, easy or hard?
Easy.
Alright, rest of people here. All you have is on unlock on
Yes, sir, for sure.
Yes, sir.
Yes, sir.
Yes, sir.
Alright, let me just give a little test now. Quick. I run through it quick. I run through the motions. What kind of lens is this?
Convex.
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 Right. And it's also
Diverging.
Real. Well, let's get rid of
no, that's not what I mean. I mean con what?
Virgin.
Conversion.
Right. This would like from this I could only get what kind of images?
Real
Real
images.
images.
Right? There would be some points in time where it is bigger. There's gonna be some point in time where it's the same size. And then some points in time where it is
Diminished.
Diminished.
Yeah, smaller, diminished. All right, cool. If here what? If they ask you for a ray diagram, which is what they would ask you for, with a ray diagram, you need to put down what you call that? What you call that pink line I just draw?
Principal
Principal axis.
Principal axis.
What is it called this?
Optical.
center.
If I tell you the focal length is 4, then what is the distance from here to here would be?
4.
4 centimeters.
And what would the distance from O to 2F be?
8.
8.
A little bad boy, big up for yourself. Right? What are the rules?
Line from the object to the wall passing through the optical center in the principal axis undeviated.
Then what?
A parallel line.
Parallel to the principal axis. The focal point.
What kind of image is that?
Real image.
A real image.
And it is what? Upside down or right side up?
Inverted.
Upside down.
Upside down.
Right. Tell me fast. What kind of lens is this?
Concave.
Concave.
Divergent.
Divergent line.
Divergent lines.
Right. What is this?
Principal axis.
Principal axis.
Principal axis. Focal.
This is the optical center. If I tell you the focal point here, and well, the first step is to do what?
Draw a line from the
Draw a line through the optical
optical center.
Bro, stop playing up now. Alright, what next?
Draw a parallel line and extrapolate it back.
Come on. We know this.
Virtual, upright, and diminish.
Right. Ollie, big up on yourself, bro. Have it on lock. Let's go. Let's go, bro. Let's go. Right? WW's in the chat. Have anybody on YouTube, buddy? I have to have anybody on YouTube, buddy.
60 something. Last time I checked.
67. No, it has 61. Alright, badness. So, what's the main formula? I don't remember. 1 over what?
1 over F is equal to
F. 1 over U plus 1 over V.
Right. If I want to find magnification, how I could do that? What are the two different ways I could do that?
Image
difference
height
over the object
over
distance.
object height and image distance.
V on you.
So it's image height over object height or image distance.
Over object distance.
Over object distance.
Question. If we're dealing with a virtual image, right? Would I put V as positive or negative?
Negative.
Negative.
Yeah, negative. Negative. So if we're dealing with a virtual image, we will put V as a negative. Hopefully I find a question like that. Alright, let me run it. Let's go. Oh, they think guys are robots?
Nah.
Yeah, sure.
Really?
Yeah.
Nah, just build different, bro. Just build different. We tackle this
So
question.
you're not tired?
Tired? Oh, what? I love what I doing. I happy to teach. I me tired now.
Robots don't sleep.
Alright, so who have more discussion? You volunteers. You don't blushing it? You don't smile it? I could ask you don't smile and I'm thinking
So, let me run it now.
Alright, Nikolai. An object of height 7.2 centimeters is placed 18 centimeters from a convergent lens of a focal length 12 centimeters. Determine the image distance. So Nikolai, they give me object height here. So cool. And 18 centimeters from a convergent lens is F. What's in, boy? What's in? Wait, I don't know what's going on with good notes. So they're saying it was placed 18 centimeters from a convergent lens. Therefore, that is your what distance?
Focal distance.
No. That's what I want you to think. The focal length is actually 12.
Ah, so that's the object. That's the what?
It's the object distance, chat.
Ah,
It's talking a bit weird, right? But it's saying, watch, when you read the full thing, you understand. An object is placed 18 centimeters from a convergent lens. So, Nikolai, if you recall, we'll use 1 over f is equal to 1 over u plus 1 over v. F is the focal length. What does u represent, guys? What does u represent?
The object distance.
Object distance.
What does v represent?
image.
Image
Image
distance.
distance.
Cool. So, what is the focal length?
The focal length is 1 over 12.
Yeah, the focal length is. Now, let me explain something, right? When we're doing these calculations, we're supposed to be working in our units. Well, let me just confirm,
SI
right?
units.
SI unit.
Yeah, you're typically supposed to be working in SI units, but let me just see if it play impact here. I don't see it posing much of a trouble. Yeah, I could leave it at centimeters, it's not a problem.
So for all the solutions I see in all the questions that I'm answered, there's never changed any meter. So
Yeah. Oh, ChatGPT, like real. Oh, yeah, check this. That's real bad.
Whoa.
Yes, sir. I see that today.
Not real bad.
When I asked ChatGPT for physics formulas.
I didn't know it's do that. How does do that? Alright, well, let me continue. Yeah, so we don't have to convert anything to meters. Right? So, tell me what to do, Nikolai. The 1 over 12 is equal to 1 over
18.
right, plus 1 over 1 over v, right, Nikolai? Nikolai, you there? Good to Nikolai.
Yes, sir. Yes, sir. My mic wasn't working
Alright.
just now. I well talking and didn't know my mic wasn't working.
If you're confused, like they're literally saying, watch, they say the object was placed 18 centimeters from a diode from a convergent lens. So the object distance is the 18, the image distance is really the 12. What's in? What? I'm gonna backtrack a bit. I feel like confused people. So any question, they're saying an object is placed 18 centimeters from a convergent lens. What is that? What's that?
a convex lens.
Convex.
Right, but that's the what distance?
The object
The object
distance.
The
distance.
object distance.
Right, so by the object, I'm gonna put 18 one time. I see in here focal length 12. So I'm gonna replace F with what?
12.
12.
And do I know what the image distance is?
No,
No.
fine.
That's what they want me to find. So here what? Nikolai, what do you think I should do?
Put V as the subject of the formula.
Right, so I should probably move across this first. So that'll be 1 over 12 minus 1 over 18. Nikolai, where's 1 over 12 minus 1 over 18?
I get 1 over 36.
1 over 36. Taking your word for it.
So why we didn't just carry the why we didn't just switch the V and put the 12 on the other side?
Because of this really easy, Nikolai, watch. Nikolai, all you have to do now, just reciprocate it, and you get V is equal to 36.
And then be minus because it's another fraction.
No. No, Nikolai, watch. Nikolai. If I tell you that a quarter is equal to a quarter, and that makes sense.
Yes.
If I flip both sides, that goes into 4 over 1 equal to 4 over 1. Is that still valid?
Yes, sir. Oh, yeah, it didn't affect the other ones. when we put it as a fraction.
Nah, we've done this before. So guys, anytime you have a single fraction on either side and you have a fraction, you could just reciprocate it. Oh, they get 36?
Yes, sir.
Yeah.
Yes, sir.
Everybody gets 36, right?
Yes, sir.
Yes, sir.
Let's find
Yes, sir.
magnification now. So well, I just find the image distance. The image distance is 36. So what find magnification?
Image
U over
distance,
V.
object
Object
distance.
distance over image distance.
Well, it's image distance over object distance. Is the image over the object? Where's the
Oh,
image?
right.
36.
36.
What is you?
18.
18.
So the answer is 2, right?
2.
Sir.
So what question? If the object had a height of 7.2, what height would the image have?
Twice or 7.2.
Twice.
That'll be 14.4. Ah, bam. Look, we call the question. Right? Right, so the image height would be 7.2 by 2, 14.4 centimeters. Easy, right?
Yes,
Well,
sir.
if
So
a
how we
question,
gonna be multiplying by 2?
all right, so if I tell you I'm magnifying something by 2 times, right? Then that means the image gonna be how much times bigger?
2 times.
Right. So we found the magnification to be what?
2.
Remember, magnification is the image distance over the,
Object distance.
or it's the image height over the.
Object height.
Now, I prefer to use distance because here what? I just find the image distance and I have the object distance. So I use that. 36 over 18, 2. So I have a question to Kylie. If the object had an original height of 7.2, I'm making it 2 times bigger. What will be the image height?
7.2 by 2.
Right. You good?
Yes, sir.
And guys, since we're dealing with a convergent lens, we know that it'll be a what?
A real, sir.
Real image.
Real image.
Easy. Very, very easy. Right? I swear I had one question. All right. I don't feel satisfied. I feel like we should do one more question like that. Let me see if I have any questions here I could find that look nice. Ah, look at question here. Who can help me with this question?
Yeah. Oh, wait, I done do one already.
Oh wait, is that paper 3? It's looking like a paper 3. Yeah, is that paper 3? Oh yeah, is that paper 3, buddy? Yeah, paper 3. I'm gonna find out paper 2 question. Alright, let's do this one. Alright. So who wanna help me with this one? Call this last question for the night. This live starts 6 o'clock. No, but like 7, 6, 7. Like yesterday.
Oh my gosh.
Well, that's the truth. Like it's at around 6 or 7 p.m. Right? Any volunteers?
Yes, I will try it.
Yes, sir.
Liam, come redeem yourself. Fast.
Mm-mm.
Fast.
Read it out.
Yeah, read it out.
Copy figure 3 and draw the ray shown as it emerges on the other side of the lens and its relation to the focus through the principal axis and the focal length.
Key. Well, they didn't really specify anything.
So you draw back that same thing there.
Can't cheat. What?
And first thing you do is draw the principal axis. That's a horizontal line through the middle of the lens. You could draw F1 and 2F. Well, F and 2F. F will be the focal length.
Now here,
Well, the focal
whatever,
point.
whatever you decide,
Mm-hmm.
you gotta be careful, right? Like, okay, if you want to do like a proper diagram,
Yeah.
I would recommend like specifying like what is what. So, what you want to pick for your focal length?
2.
2, okay. And I would put it decide as I did this, and because then they would never specify any
Yeah.
where F is equal to 2 centimeters, and this is the optical center,
Yeah.
right? And I'm gonna call. Don't forget to label this the principal axis.
Mm.
Right? If you want, you could probably put labels for this too. But that's optional. Right.
Yeah.
So where's my first step?
The light ray. It
Right. So we have
would pass through the lens and move away from the focal point. Diverge.
right. So it's going to
Diverge.
I wasn't. I trust all you'll get these marks, because it's not hard.
So we are getting these
Yes, sir,
marks.
sure water.
Come on, man. Hey, fed up. When last I hear from Akil, right? And you know who Akil is? I don't think
Yeah.
I know who that is.
I just see him in the group.
Yes.
Listen.
Through the optical center now.
It's a sketchy diagram, but
The image could be virtual, upright and diminish.
yep.
Same size as the object.
Same size.
Side. My bad.
So we will say virtual,
Upright.
diminished.
Upright.
Well, if a question like this come in the exam, well, I better get out 5 marks. I come and falling on your sleep.
So like food, so we are
All right. Writing words or what? You see this?
1
What?
mark for that.
What?
And all them lines? Nah.
Yeah, counting for big handwriting.
Don't waste an ink, boy.
That's crazy. Magnification.
Image height over object height.
CSEC on the better to do, boy.
So they're trying to manipulate us. That's what.
You guys are the manipulated variables.
Image height is HI and object height is HO. And next one is magnification is V on U, where V is the image distance and U is the object distance.
Bio people should understand this way. Bio people just have to be doing this in the labs all the time.
True.
You know, I do biology and keep. You know, 1 and unit 2.
So
I actually do all the sciences and keep. It was fun. Kind of stressful. Yeah. I'll again, I 1 mark, right? I hope.
Yep. Yes, sir.
Well, unfortunately.
Right. An object AB is placed 20 centimeters in front of a convergent lens of focal length 10 centimeters as seen in figure 4. Here what? I would have completed that diagram to begin with. Alright? Tell me what to do. If I want to complete the diagram, what should I do?
So your conversion line.
So from B to the optical could be 20, so
Probably do this. I mean, are we dealing with what type of lens here?
Conversion.
Conversion.
So I draw that. What's my next step?
The parallel line to the
Converge the focal point. Image.
They're looking identical, though. They're looking identical.
Yeah,
That's
basically.
actually. They're looking identical. Like, how do you calculate the position of the image formed and state on what side of the lens it is located? Right?
One is 1 on
So,
F is equal to 1 on V plus 1 on U.
guys, does it matter if we say 1 on V plus 1 over U or 1 over U
Nah.
plus 1 over V?
No, it
No.
completed.
Good.
They make 1 over V the subject. They
Lily,
minus
you
1
should,
on U.
Lily, you asked me if you should continue to do physics. It's up to you. If you like physics, you do it. Somebody on TikTok now talking to. If it's one thing, or like, can't do something in your life that you don't feel like you want to do.
So,
Right, so an object AB is placed 20 centimeters in front. So this is the what? Is the object what?
object
object
distance.
distance.
Yeah, object distance.
And that is you. And they tell us the focal length F is 10. So 1 over 10 is equal to 1 over 20 plus 1 over V. What should I do next?
Make V the subject.
Subtract 1 over 20. Yeah.
Right, well, I'll get
1 on 20. 1 on 20.
yeah, because that will be 2 on 20 minus 1 on 20.
That's equal to 1 over V, and V is 20.
Yeah. Yeah, so it's right. It's right. It's identical. Calculating magnification. Magnification just be, well, I would say V over U is 1. How much about what? What?
Three marks.
What?
Ever.
What?
I taking them 3 max in it. Hey.
What? What did
I
you
hope
like
it
see
comes
here,
soon.
boy?
So you
Bro,
better say be you better
bro,
be in what for
they
the
give,
right thing.
they give you one.
Oh no. No.
They give you 1 mark for this, and then they give you 3 marks for this. CSEC physics too easy, boy. Too easy. On an average, I get real easy. Too easy.
Yeah.
All I had to get little distinctions, boy. Calculate the magnification of the image form. I read in the back just to make sure I'm not tweaking, boy. Yeah, it's 1. It's 1. Is the image form real or virtual?
Real.
Real.
Yeah, real.
Yeah.
V positive.
Somebody asked me why V is equal to 20, right? Okay, so from the question, they told us the focal length was 10, right? Focal length was 10. They told us the object distance was 20. So U is equal to 20. And we have to find for V, right? So I plug that in over here. So I say 1 over 10 is equal to 1 over 20 plus 1 over V. I want to make V the subject of the formula, so I'll move across the 1 over 20. Now 1 over 10 minus 1 over 20, that is going to give us 1 over 20. And that's equal to 1 over V. Anytime you have a single fraction on either side, you're allowed to reciprocate both sides. And so that will turn to 20 over 1 is equal to V over 1. And you'd imagine if you have 20 over 1 is equal to V over 1, that's just simply 20 is equal to V. So V is equal to 20. So V is equal to 20 centimeters. Yeah, hope that helps. And you can see from the diagram too that is the same, it'll be the same height. Just like on the other side of the lens and flipped. Oh, for part 1, we were supposed to say on which side on the lens it was located, right? So it would be formed what?
On the opposite side?
Upside down.
And if you want, you could say image is upside down to reflection knowledge now. Squeeze out 5 marks. Squeeze out 5 marks. Boy. What time? We good?
Yes, sir.
Oh yeah. We do the whole ways on optics chat. Whole ways on optics. How you feeling? How you feeling?
Really
Out
good,
of
sir.
time.
Boy. That was fun stuff. So as promised, I got into the Green Day cover. Are you ready?
Yep.
Yes.
No.
Alright. Nikolai, see you can't sing with me, no?
Nah,
Oh, serious, Nikolai.
nah.
So what song you
One thing
singing?
I real bad at is singing. Nah.
Let me put like my emo here. Wait, take a second.
I believe it. I mean, not
So you singing Boulevard of Broken Dreams?
Wait, my emo here. Wait. I don't like, you know what I mean? Three here to the side here. Make me look really emo.
OMG.
Wait.
Or
I'm looking like a real emo, eh, guys? I'm looking like a real emo dog. I'm looking like a real emo.
Yeah, sir, when you had your head down and your hair was looking like that, I was good to ask you that same question, you know, sir.
Wait. I was an emo for a great part of my life, you know.
What?
Yeah. I was an emo for a great part of my life.
I could see that.
Oh, I think
Say okay.
I know what you're talking about. The image that you show you.
Wait. I'm
Nah,
scared.
yeah.
Wait.
You don't have to lean back a little bit, and it will be perfect later.
All right. Let me pull it up there.
Right. Hold on. Let me take a picture.
All right. Wait. I'm gonna pull up the
Yeah,
Boulevard
get
of
that in
Broken.
4K, sir.
They had to
One
look
second.
down a little bit too, you know.
Wait.
You had a fake cry too, sir.
All of that, I want reduce to the point.
Put some mark on the face.
Wait.
Don't forget
With the
back
eyeliner.
I walked a lonely road, the lonely road that I ever known.
Yeah, take all that video.
Yeah.
Hey, all on YouTube.
Wait.
Absolute cinema.
Yeah, boy.
Absolute
Sir,
cinema.
don't do that on your neck. Make a crack noise, you know. Sir,
Hey.
don't do that thing.
I know that old boy. I know that old boy. One to you, boy. I know that old boy.
Hey, sir, I never say
sure?
that word. All I saying is you're doing
Boy.
that. Next thing something happen.
Uncle Green Day boy.
Sir, I need you for maths paper 1, advanced paper 1, and physics. You know.
True talk.
Yeah, we need this. Yeah, die on Windows.
Chem too, sir.
I too. And around the. But yeah, I can't tell any notes. It's a real. Let me make a TikTok now. Look at TikTok. The survivors. How much hours are physics in the way?
Like 8.
Yeah, like 8 hours.
7 hours and 40 minutes to be exact.
Yeah, so
Oh,
basically,
okay. We do the whole waves on optics. You typically do this in like months. You know what I mean? Typically do all of this months. Right. Anybody else got on the camera? Hey, look, my son Ahmed, boy. Hey, what's your plan, boy? What's am I seeing this man? I don't know what Ahmed does look like. Yeah, boy. All right. So these are the survivors after 7 hours and 40 minutes of straight vibes, physics vibes, right? So I got anything to say, people?
Like and subscribe. Stop watching
It
it
was
when you're not doing
great.
anything.
Hit those post notifications, guys. You don't know.
Unsubscribe. Only
Yeah,
check or affiliate on our boy. Check or affiliate on our
some
boy.
real good information. Real good
Tell them,
physics
Nikolai.
and
Tell
vibes.
them. The real sleeping boy. They're sleeping. They're
If you know how
sleeping.
much, sir, if you know how much I think them miss out, sir. 8 hours of pure physics? Nah.
Well, we will see them tomorrow for the 12 hours. If you think we was bad with 8 hours, we're going to do 12 hours tomorrow. Can't do the whole syllabus. Can't try a madman thing.
So everybody got done.
Yeah, boy. But anyways, much love, guys. Go on, take some rest. Go and get some rest for
Yeah.
tomorrow. It's
Same to
everybody.
you,
Take
sir.
care.
Later,
Alright.
sir.
Bye.
Good night, everybody.
Yes, sir.